This is all rush. I mean, only 2 hours of sleep now, and I've been coming in at 5 the past couple of days. I'm not going to go home now.
I was in on the ground floor of an exploration of the entire solar system.
Us scientists are sitting here just kind of staggered by the whole thing and having a lot of fun. But if people start forgetting the name of the planet by Friday or Saturday, that's why.
Okay. Meanwhile, the Voyager cameras have shown scientists something they have not seen anywhere else during the spacecraft's grand tour: shadows cast by clouds. Yet that is just what this picture shows at Neptune. It is believed that shadows are due to a 30-mile gap between methane clouds high in Neptune's atmosphere and a blue cloud deck far below them. Such a situation clearly is a rarity. CNN will have live coverage of the close encounter period with Neptune, a look at what's going on, the people, the spacecraft, and, of course, all the discoveries yet to come. That'll begin at midnight Eastern Time. I'm Dan Blackburn, CNN Live at the Jet Propulsion Laboratory in Pasadena.
Strong thunderstorms in southern Illinois, also into India.
A 25-watt light bulb is more powerful than Voyager's radio signal. Infinitely more powerful once that signal finally hits Earth.
How many things do you know of? Think of them. Washing machines, automobiles, television sets. What do you have that has worked or could work unattended without the intervention, the direct intervention of a human hand for 12 years? As complex as this is, we take enormous pride in having done that. That is one great accomplishment.
So here we are in 1989, and it's Neptune at last, a 4.5 billion-mile trip. Look closely to see the ring discovered just a few days ago, and we get a good look at a storm the size of our planet. And there's the quirky moon Triton, orbiting in the wrong direction. There will be more from Neptune. And then the grand tour is over. Voyager will leave our solar system, having shown us places we've wondered about since coming out of the cave and staring up at the skies. But Voyager will be drifting out there among the stars. And who knows, maybe it will surprise and amaze again, showing us more worlds we never imagined existed.
Well, Norm, I want to ask you this. What would thrill you the most tonight as the pictures come back to see?
Well, I think based on all the things we've seen so far, I've been very impressed with the atmosphere, the incredible beauty of the atmosphere, the large spots. We found rings. We thought there might be rings. We found rings, complete rings. But I think the thing that I'm personally looking forward to the most is getting a close-up look at that kind of crazy backward moon, Triton, where our best pictures are going to be coming back in just a few hours, and we're really looking forward to that.
I gather that you can't learn anything from the Voyager trip so far about the possibility of human beings or beings of some kind in space. But are there any provisions made if you end up running into them?
Well, we just in the off chance that Voyager sometime in the next 1,000 years might run across another civilization, we put a small plaque on the side of the spacecraft. And the plaque is inscribed with sort of a code, which if they can decode it, the civilization that finds it, they can play this record, and on it are audio sounds from the Earth and pictures of people, trees, animals, kind of an image of what Earth might be like.
Well, you're going to bet on it one way or the other. What's your bet?
I'm not betting that they're going to find it while I'm alive.
Well, we wish the Voyager well on its poetic journey into the beyond, and we thank you, Norman Haynes, for being with us, and we'll be back.
As the Voyager 2 is winding up its 4.4 billion-mile journey through the solar system. The probe will pass only 3,000 miles over the cloud tops of Neptune. 4 hours later, after radio signals make that long trip back to Earth at the speed of light, scientists will have confirmation of a successful flyby. In the meantime, they're analyzing new discoveries. Dan Blackburn has more.
The first stop on Voyager's grand tour was Jupiter. And interestingly, that now is the planet Neptune seems to most closely resemble. That's because the great dark storm system on Neptune is quite similar to Jupiter's famous Great Red Spot.
The Great Red Spot is a huge anticyclonic storm system, which means it's a high-pressure region. And then we see smaller spots, white spots, which can be seen from the Earth, and then dozens of smaller spots that couldn't be seen at all. And I think it was the abundance of these small, rapidly rotating storm systems, which was really quite surprising.
Jupiter also had the solar system's most surprising moon to date, volcanic Io. Voyager cameras revealed that Io has 8 active volcanoes, one of which hurls out debris at the rate of 200 miles an hour, 50 times faster than Earth's Mount Etna. And there is more.
The surface of Io is covered with a lot of sulfur and oxygen, and something like 1 to 2 tons of that material per second is stripped off by Jupiter's magnetic field as the magnetic field rotates past Io.
Io's dust then creates Jupiter's equivalent of the northern lights. Voyager also discovered that Jupiter has a tenuous ring system with a halo effect.
An extended halo of fine particles that is believed to be the result of the charging, the electrostatic charging of the tiny dust particles and then their interaction with Jupiter's tilted magnetic field. So it is very different in character from the other ring systems.
Of course, the best-known rings surveyed by Voyager were those at Saturn, the ringed planet. Saturn's rings contain chunks of ice ranging in size from small pebbles to objects as big as large houses. Voyager discovered the surprising braided F ring at Saturn, which is held in place by 2 so-called shepherding moons. And these spoke-like features, which scientists believe are caused by the presence of dust particles floating above the rings. Saturn itself has enormous winds, blowing at more than 1,000 miles an hour, and it seems to have a unique heating system.
Inside of Saturn, helium is forming into raindrops and raining down toward the center of the planet, and it was the falling of the helium raindrops inside of Saturn which generated the heat which kept Saturn warm.
Saturn also has a huge moon, Titan, with a thick atmosphere and smog similar to that on Earth. Titan bears a resemblance to Neptune's Triton, but actually may have extraordinary oceans.
We now believe, based on calculations, that ethane, which is a light hydrocarbon, is actually present in the form of oceans on the surface of Titan, having been made in the atmosphere out of the methane.
The most recent stop on Voyager's grand tour was Uranus, a planet with a strong magnetic field uniquely tilted 60 degrees from the planet's axis, sort of like having Earth's magnetic north in the vicinity of Los Angeles. Like Neptune, Uranus is mostly gaseous, hydrogen, helium, and methane.
It has no solid surface to stand on. Certainly it's not a place where man could live easily. There's just no oxygen, no water really in those portions of the atmosphere, and no place to stand.
Uranus had 15 moons. One of them, Miranda, appears to have thawed and refrozen, something which astounded scientists. Another, Ariel, may have had glaciers, but not of ice as we know it.
Too cold for water ice to flow, so if it is a glacial type flow, it must be water that has mixtures of other types of materials in it to cause it to melt at a much lower temperature than water ice.
Uranus also has a series of rings, which may resemble the ring material around Neptune. Voyager left Uranus 3 years ago en route to Neptune, where now the spacecraft's grand tour is nearing an end. And more discoveries are all but certain in the wake of Voyager's close encounter. Dan Blackburn, CNN at the Jet Propulsion Laboratory in Pasadena.
Sunday, pull the storms across Michigan into the mid-Atlantic and
3,000 miles above our planet. Voyager is going to get within just 3,000 miles of Neptune before using the gravitational field of that giant planet to send it out into interstellar space. Of course, the folks on Neptune, they're just watching our 6 o'clock show now because it takes 4 hours for the images traveling at the speed of light to make it from Earth to Neptune and vice versa. So even though the Voyager craft will pass over Neptune, reach its closest point at 10:56 tonight, the images will take over 4 hours to get back to Earth, so scientists won't be seeing them until about 3-4 this morning Central Time.
Also, I think the people on the flight team who take those kind of results and take them and run them through all the various computer programs that have to recompute all the pointing directions and the image motion compensation corrections have been up for night and day for the last several days. Have also done a very fine job. Let me just read you some of these times. These are the most recent times off the most recent navigation results. The ring plane crossing, which is on the inbound leg, will occur at 11:59 p.m. tonight. This is the Earth receive time for all of these events, and it's Pacific Daylight Time. So at 11:59, essentially 1 minute before midnight, the spacecraft will cross the ring plane. That essentially means it's crossing through the equatorial plane of the planet. If there were rings out as far as our trajectory, we might have expected problems. The rings are significantly in closer to the planet than we are, so we do not expect any problem with rings or particles at that point. Neptune closest approach is 1:01:39 a.m.
on Friday morning. That's 1 minute after 1 o'clock in the morning and 39 seconds. Our closest altitude to Neptune is 3,048 miles, or 4,905 kilometers. Right after closest approach, at 1:07:35 a.m., we will enter sun occultation. That is, we will pass behind the planet as seen from the sun. At 1:08:03, we will enter Earth occultation. We'll then be behind the planet for nearly an hour. We will exit Earth occultation, that is, come back into view of the Earth at 1:56:49 a.m., and we will exit sun occultation at 1:57:37, about a minute later. We then continue on. We cross the ring plane again on our way to Triton at 2:20:56 tomorrow morning, at a distance of 104,000 kilometers, which is safely away from any material. Triton closest approach will be at 6:16:09 Pacific Daylight Time Friday morning. We will enter Earth occultation at 6:45:20. We will enter sun occultation at 6:45:39. We will exit Earth occultation at 6:48:18. This is a very short occultation. It's only around 3 minutes. And we will exit sun occultation at essentially the same time. All in all, I think the orbit, the spacecraft is performing admirably. The ground stations, including all of our various cooperating antennas around the world, have been doing exactly what we wanted. So everything's right on target.
Well, this is the day. I hope you've all figured out when you're going to sleep. I haven't. As of 9:20 this morning, if I could have the first slide, please, we were still in the solar wind. We were somewhere up here, ahead of the bow shock, presumably, although we have seen some rather unusual conditions in the region overnight, starting at late yesterday afternoon, which is posing some bit of a puzzle. But I think we do feel confident that we're continuing, at least as of a few minutes ago, to see the supersonic solar wind. So that really suggests we're still here. We should be getting close to the bow shock. That would suggest the field strength at the equator is unlikely to be larger than about 0.4 Gauss. So it's the kind of numbers that we've been talking about the last few days, but any minute we'll have our first contact with the Neptunian magnetosphere. All right, I'd like to just give you some highlights of what's coming up. This is, as I said, the day. I don't intend at all to go through every single thing we're going to be doing, just to give you some computer graphic impression of some of the things which will be showing up during the next 24 hours on the screen. Not everything will be coming back, as you know, from the timeline you've been given. Some will go on some of the best images of Triton, for instance, will actually come back a day later. This is about 1 o'clock this afternoon. That square that you see is the wide-angle frame, so we're now close enough that Neptune will actually fill the wide-angle frame. Could you focus that a bit? I think it's not quite focused. And, of course, in the wide-angle camera, we have additional methane band filters so that we can make now high-resolution images of Neptune, a resolution something on the order of 100 kilometers per line pair, 66 miles or so per line pair. So that's about 1 o'clock this afternoon. You'll be seeing these wide-angle images of Neptune. Then about 45 minutes later, we'll have our best image of Nereid. The best image is not all that great because Nereid is really very far from Neptune, about 55 miles per line pair. That's 145. That would be the best one. Then between 3 and 5 o'clock today, we'll be doing and there will be images coming down at the same time, but the principal activity will be an accurate measurement of the temperature of this particular spot in Neptune's atmosphere. That's the spot where we'll be doing a radio occultation, and I'll show you in a few minutes why that spot is important. we want to compare the temperature measured by the infrared instrument with the temperature profile determined by the radio occultation experiment. So that's between 3 and 5 o'clock. There'll be a series of images associated with that long infrared observation. 5 to 5:30, we'll have a set of images on the north hemisphere, northern limb of Neptune to try to study, again, the scattering properties of the atmosphere. Those will be narrow angle images, and we'll have really quite spectacular resolution. And then we will also have some retargetables. This will be about between 5:45 and 6:45 late this afternoon. 2 sets of retargetable images of the rings. Resolution about 5 miles per line pair, 2.5 miles per pixel. These will be will be among the best, highest resolution images of the rings of the outer ring arc. And during this time period between 5:45 and 6:45, we've also managed to insert into the sequence a high-resolution image of 1989 N2. So that will be coming down during around dinner time. We also have the stellar occultation of the rings, Sigma Sagittarius, where the photopolarimeter will actually track the star. This is around 9:30 this evening, and going behind the outer ring arc and the inner ring arc both. So that's an important activity for measuring accurately measuring the profile, the density profile of the rings. At 11 minutes after 10, approximately tonight, we start color images of Triton. These will be our last images of Triton before our closest approach, and will be in color. The resolution will be something on the order of 10 kilometers per line pair, 6 miles per line pair. So these will be really beautiful images, even though we'll get much better ones in a few hours. These images this evening will already undoubtedly have a lot of geological interest. Like I say, I don't know when anybody's going to have time to sleep. We have a ring plane crossing at about midnight, the ring plane being right about here. So we cross the ring plane, and about the same time, we expect to see the maximum intensity in the trapped radiation environment, and we also will possibly detect with the plasma wave instrument some of the fine dust that we often find in the equatorial plane of these giant planets. That's at just almost exactly midnight. Then at this, the telemetry then is off and remains off for the critical experiment that we do. This shows the spacecraft at the ring plane crossing. We head then for the radio, so we turn off as we go through just as we go through the ring plane, and this is the critical period for the radio occultation. This is this latitude right here is where we've been measuring the temperature that I mentioned earlier, so that we can make the comparison with the temperature that radio science measures at this point. Because we actually don't turn off the transmitter, we just turn off the data transmission. The transmitter remains on, dedicated to the radio occultation probe of the atmosphere. While we're behind Neptune, we will actually point the antenna of the spacecraft in a series of segments toward the limb at just the right angle, so that the radio beam will be refracted by the atmosphere in just the right direction to arrive at Earth. So we expect, in fact, to continue receiving signals from the spacecraft throughout this entire period that Voyager is behind the planet. And that allows us to probe most deeply into the atmosphere with the radio beam, perhaps as far as deep as 2 to 3 atmospheres in pressure, perhaps down to the top of the lower cloud deck, but certainly we hope below the top cloud deck of methane ice. So that's a critical activity. Of course, you won't see anything on the screens during that time. It will all be coming down as uncoded, pure radio data. That's between about 1:08 tomorrow morning and 1:57, all in local time. Then, of course, we do have a series of images as we approach Triton. This is not exactly the configuration for the images that will be coming down in real time. We will be getting some real-time images of Triton between 3:40 a.m. and 5:25 a.m. Those should really be spectacular. Following that, we'll have another series which will go on tape recorder for playback still later.
Then at 0650 tomorrow morning, we do the same kind of occultation of Triton's atmosphere. That is, we watch the sun with the ultraviolet spectrometer. This is the slit of the spectrometer as the sun cuts across Triton, and so we can measure very accurately the methane atmosphere which is there. And we'll also, from Earth, be measuring the effect of the atmosphere on the radio beam, just as we did at Neptune. This occultation, Neptune occultation, lasts almost an hour. This occultation lasts a whole 3 minutes. You'll hardly notice it in terms of the downlink data. So that's just some of what's ahead. As I say, this is it. This is the 24 hours we've been waiting for. Okay, I would now like to show one last thing. Caltech and JPL have designed a supercomputer. It's called the Hypercube. It's actually 128 computers arranged in an array to operate concurrently, giving the power of a supercomputer with actually just an array of many regular computers. As I say, it was designed and built here at JPL with a lot of input from Caltech campus. And the Digital Image Analysis Lab has been working with the Hypercube group here to do the complicated calculations you need to take the images which come in, which have to have a lot of correction done to them in order to project them so that they look, if you like, real life. And I have this morning the first product, and they'll be working on more products, the first product that's come out of this activity. This is really the first time that we've had the capability to do this kind of image reconstruction in this kind of time scale. You need basically a supercomputer capability. And so this film you're going to be seeing is essentially the first of the products. So if we could have the film. There will be 6 rotations, so we'll be able to see it several times, each rotation taking about 6 seconds. Now this is a single image which is rotating, so it's not dynamical. In other words, you're seeing the same thing over and over again. You're not seeing 6 separate Neptunian days. Eventually, of course, we should be able to do this with the atmosphere evolving rotation by rotation. That's what we're really aiming to be able to do. But you can already see, of course, the small dark spot and the great dark spot. There are also some blems on the camera which show up, which haven't been removed like that thing. But you can also see the streamers, the cirrus, which is associated with the great dark spot at this particular latitude. You can also see that there's a cirrus streamer up in the northern hemisphere. Your eye begins to pick up some patterns with this kind of a presentation that aren't necessarily so obvious when you sit and stare at the images one at a time. And of course, once we can actually make this into a time-lapse movie where the atmosphere is actually moving, and we have that data, it will really be a very valuable tool as well as a very beautiful thing to look at. Okay, I think Brad Smith's up next.
Good morning. We found ourselves this morning in the position of trying to analyze the images that came in yesterday afternoon and last evening so that we would have something to say about them this morning, while at the same time being terribly distracted by extremely high-resolution images that kept showing on the screens and diverting our attention. We are getting very, very close to the planet now, and almost every imaging frame that comes back is extremely exciting. I have a number of slides I would like to show this morning, so I think it's best just to get right into them. And the first is a very high-resolution image taken of the Great Dark Spot. Again, this was all possible courtesy of Andy Ingersoll and his group of forecasters, who really did an outstanding job on the Great Dark Spot and allowed us to put the images exactly where they should go. You can see a lot of structure now in this image. A lot of structure in the high cirrus-type clouds, but still not much down in the spot itself, and that may take more detailed processing than we've been able to do at the moment to bring out any structure that might be down in there. This is the highest resolution image now that the narrow-angle camera will take of the great dark spot. It's over near the limb. The very, very smallest clouds that you see in this image are only 25 kilometers across, and this image, I believe, was shuttered only about 20 hours before closest approach. So this is the highest resolution image. You can see the limb of the planet up here. It's quite foreshortened because it was close to the limb, and it's just showing that all of these clouds are breaking down into very, very fine structure. That essentially is the message in this image, which has now been map projected to bring out some of that structure. And it's making it extremely difficult for the dynamicists. The dynamicists are trying to track these individual clouds, to look at a particular cloud and then see where it is a few hours or maybe 10, 18 hours later, and having difficulty locating them, because what we're seeing here are not clouds that are rapidly moving. The air around them is rapidly moving. This is in a very high velocity region. There are undoubtedly very strong shears, but these can be considered analogous to the lenticular clouds that you will see hanging over mountains. They seem to be just stationary over a mountain, but the air that's going through them is going quite rapidly. And what's happening is that as the winds blow through this region, they get deflected upward. Now, whether that is due to the great dark spot itself, we don't know that, but it quite probably is, that there's something about that dark spot that deflects these winds upward as they go up, carrying volatiles like methane in them. They reach an altitude where those volatiles condense out and form clouds. Then as the wind moves on, it descends and it goes down into a warmer region, and these little ice crystals of methane sublimate, they disappear, evaporate. And so the cloud appears to be stationary, even though the winds are moving very, very rapidly through this region. The next slide illustrates the problem. Again, these are map projected, but these images are only 2¼ hours apart, and yet you can see there are some major changes that have taken place in only 2¼ hours. This cloud right here, for example, which isn't even seen in this image. Is it this that's moved to here, or is it just this one is faded out and a brand new cloud has been created in its place? And those are the kinds of problems that we're having, and it's the reason that we're a little bit slow this time in getting actual velocities from the cloud motions. This is now a high-resolution image of the smaller dark spot, the one that's been called E2. Those of you who were around early this morning may have seen an extremely high-resolution image of that cloud filling the field of view of the narrow-angle camera. We'd like to say we predicted that, but I have to be honest, it just by chance happened to fall right into the center of one of the frames that was taken while the infrared instrument was scanning up and down on the planet. But it's an absolutely magnificent photograph, and should have a processed version of that available for you tomorrow. What this is showing is what we suspected, that the bright cloud in the middle of this dark feature is high. It's convection. It's moving upward. This is a false color image where we use ultraviolet as an additional color, and in general, whatever looks very blue is deep, and what looks somewhat pinkish color here is high. So it's just a demonstration of height for the particular clouds in the center of that dark spot. There are other ways of getting height. This is a false color image which has been generated using the wide-angle camera It's an orange frame and a short wavelength methane filter and a longer wavelength methane filter, all together to produce false color. Normally, these images are analyzed not by creating an image, but by studying the numerical values that come out of such an image. But it does provide some graphical evidence of height. And in this particular image, if anything that's white is very high, and what's perhaps pinkish is intermediate in height. And you see it has a sort of a orangish brightening around the limb. The reason for that is that material near the limb is reflecting light before it has a chance to be absorbed by methane. And the reason for that is that there's just very, very long path lengths through the atmosphere near the limb, and the probability that it would reflect a grain of ice and bounce back up is much higher near the limb. Well, there are other ways of measuring height, and this image appeared to us yesterday afternoon, and what we are actually seeing are cloud shadows. These are some of the very high cirrus-type clouds, and you can see right along the edge of each one is what is almost certainly a shadow caused by these clouds. Now, this, to the best of my knowledge, is the first time that Voyager has actually been able to show or see cloud shadows on any of the planets that we've looked at. So this was quite a surprise for us, and quite a pleasant surprise, because it allows us to make some estimates of the heights of these clouds. And I guess we've got a bad slide up there somewhere. Yeah. Okay, maybe you can just kind of push it down in there. Okay, this shows about where those clouds are. They were down in the South Polar region. This is the South Pole, and the sun is shining in this direction and casting shadows along the southern margin of the clouds. Well, by looking at these images, it's possible to make some estimates of height, because we know exactly what angle the sun is shining at, and we can measure the projected distance of the cloud to the shadow, and that gives us a measure of how far it is from the cloud down to this more or less uniform haze layer or lower cloud level upon which the shadows are cast. The measurements so far are really quite preliminary, but the number turns out to be quite extraordinary, something of the order of 50 kilometers between these very high clouds, these cirrus-type clouds that we've been talking about, 50 kilometers from there down to this lower cloud deck. And there were some estimates from the team this morning that they could be as high as 75 kilometers. And here is just another view of a different part of the planet, but again showing some of these little high puffy clouds casting shadows on the lower cloud deck. Well, turning from here to the rings, I have okay, we need to push that one down too, if you would. It's a better piece of artwork, what I had showed you yesterday, trying to show the relationship between the more or less continuous ring, the outer ring, which is composed of several fairly bright segments, and then a longer and more diffuse region. And as of yesterday, I believe this was the region within which we had not seen any ring material at all. But we did take wide-angle frames last night, and I'll show you one in just a moment, in which we have now seen material extending further along here and further along here, and now there's only about 10% of the ring in which we have to date been unable to see anything. So I think that it's almost certain now that this is a complete ring, and that the amount of material over here is just so very, very thin that over a certain range anyway, about 30 degrees or so, cameras have not yet been able to record any material in there, but certainly it has to be there. This is 1979, 1989 N3 and 1989 N4. This now is the one of the images that was recorded this morning. Here again, I mentioned yesterday, there are artifacts that appear around bright objects in the field of view. This is 1989 N2. This is trailed out because of its orbital motion. This is a star, and here you can see the outer ring. Now this is the trailing edge, fairly sharp, but with material which extends on, and this is the leading edge, getting more and more diffuse as you go along, and here is the inner ring curving around like so. And as had been suggested in some of the images that we took, that we acquired over the past few days, this ring also seems to show some structure. Certainly not nearly as varied as the outer ring, but it's not perfectly uniform as we go around. We have two new satellites, and here they are. This is the planet, 1989 N5 and 1989 N6, and out here 1989 N3. And you can see quite easily just from these photographs that N5 is quite a bit fainter than N3, and N6 is even fainter than N5. And if I can have the first view graph, this will now give you a listing of the satellites as we understand them right now. So this is the temporary name. Eventually this IAU committee will put formal names on these objects, but that won't happen until later this year. The orbital radius, the distance from the center of the planet now. The orbital period expressed in hours. The orbital inclination, that is the angle between the plane of the satellite and the planet's equatorial plane. For almost all of them, a value very, very close to 0, but this last one showing an appreciable inclination, certainly a measurable inclination of roughly 4.5 degrees. It certainly shouldn't be taken as 4.5. We just didn't have a little half sign to put in there on the machine that set up the graph, but 4.5 degrees, probably plus or minus a half degree, so that needs to be pinned down further. And here are the estimated diameters of these objects. Now, they have not been resolved. The smaller ones certainly have not been resolved. And so what we did was just to assume, and I think it's a reasonable assumption, that they all have roughly the same reflectivity, and so by measuring their brightness, that gives us an estimate of what their diameters are. So we go from 89 N1 up around 420 kilometers in diameter, all the way down to the most recent two, which are about 90 and 50 kilometers respectively. And I will make copies of this, or the Public Information Office will make copies of this so that you can pick them up afterwards if you like. Well, we can have the view graph off now. These are a couple of images of N1. We're actually beginning to resolve it. I'm showing you two of them to show that the shape is not due to some peculiar properties of the Vidicon or due to image smear. It is really out of round, and it's probably getting up to about the largest satellites that you can imagine that won't pull themselves into a spherical shape. And if you were going to try to draw some conclusions, what does all this mean? One conclusion that you might draw is that this object, because it is out of round, has remained rigid since its formation. Now, we don't know when it formed, but had it partially melted, it probably would have pulled itself into a more spherical shape. So it's probably reasonably pristine since its formation, whenever that was. This summarizes, in the slides that follow, summarize some of what we know right now about Nereid and 1989 N1. In comparison, you'll notice that if our estimates are correct here, Nereid is not the second largest satellite in the Neptune system, but it is instead 1989 N1. The albedos are similar. Nereid is around the 10% level, 10% reflectivity, whereas N1 is very dark, reflecting only about 6% of the light that falls on it. There have been questions over the past few days, does Nereid vary in brightness? There were ground-based observations made a year or so ago which suggested that its brightness varied over something like a magnitude and a half, which is a factor of 3 or so in brightness, and that is not observed. The brightness amplitude variations are less than 10%. I don't know exactly what the number is for N1 right at the moment, and neither did the person who put the slide together, but it's apparently a small variation. We don't know what the period of Nereid is, but we would be surprised if it was synchronous. That is, the inner satellites are more likely to keep always the same face toward Neptune. Triton does this, but Nereid is in this very peculiar orbit that takes it way out from Neptune, and it would be surprising if it did always keep the same face toward Neptune. Almost certainly N1 does, and so we show a estimated rotation period for it being about the same as its orbital period. Notice that Nereid has this very long orbital period about Neptune, approximately 1 year. These are some of the geometric albedo, essentially reflectivity measurements that have been made as a function of wavelength for Nereid, all running somewhere up around 10 or 12% here, and no trend with wavelength. That is, this would be blue or violet in here, this would be, well, sort of a blue-green, let's say, and this would be out in the green region. And so it's fairly neutral. And this is consistent with this darkish material that we see in the outer solar system. It is dark and quite neutral in its color. That is, it tends to be a dark gray color. We don't yet have color on 89N1, but you can see, shown here, that it is definitely darker than Nereid. And just one more slide showing how Nereid gets fainter with increasing phase angle, the phase angle being the angle between the sun and the observer as seen at the object in question, in this case Nereid. What this does illustrate is just further illustration that this satellite is not varying in brightness, because these are taken at different times, but they fall along a fairly nice straight line, whereas the ground-based observations that had suggested light variation would have had it ranging from the top to the bottom of the screen up here. This now is our fairly recent false color image of Triton. False color in that we have used ultraviolet for the short wavelength, violet for the intermediate, and green for the longer wavelength. And the purpose of the false color is to show what tends to be bluish or whitish, and you can see along these margins of along the dark areas, the reddish areas, this blue color which is persisting. This little region in here, for reasons we don't fully understand, is darker in ultraviolet. That makes it show up somewhat more orange in this particular image. And you can see the detail beginning to just become finer and finer. This image is, I think, our most recent image now of Triton. And it's taken through a violet filter, and we've put a map grid over it so you can see just about where the South Pole is. This is the equator up here, so the equator is running sort of along like so, and the terminator is along over here. And again, finer and finer detail. There are some members of the imaging team who believe that they are seeing craters, but they certainly haven't convinced me of that yet. But again, we don't have to wait very long before we really know. And then this is the color image, which goes with the violet that I just showed you. And again, one can see the reddish color of the darker areas up around the equator, and the overall pinkish color of the bright regions, which, as we've said a number of times now, we believe is due to processing, chemical processing of the volatiles, the methane and others perhaps, due to high energy particles. The final view graph, I guess, because we can have that up here now. I've just indicated, will indicate for you when some of these high resolution images will be getting down on the ground for these new satellites and Nereid. So we will have some fairly good images of 1989 N1, 4 of them coming down Thursday about noontime tomorrow. And, sorry, today? Oh, right. Okay. Well, it's a shorter wait than I thought, okay. I'm glad you told me it was Thursday. I thought it was still Wednesday. Okay. Nereid coming in this afternoon. This will be the very highest resolution images of Nereid. And I warn you, don't have great expectations, because Nereid was just way, way out in its orbit at the time these images were taken, and they aren't very many pixels across. The highest resolution images of N2 will be coming in this evening, 3 images. Then the very highest resolution image of N1 will also come in this evening, but I put down that it's a partial image, and that is that before the whole thing gets played out, the window goes away and the tape recorder has to stop running, and so I don't know, maybe it'll be 2/3 of a frame. We're not exactly sure, but not to worry, because those who want to hang around until the early hours of tomorrow morning, we'll replay it and get the entire image down. So this is the schedule. This is the time that they should appear on the monitors. That's all I have, but we can make copies of this available also to you afterwards.
Before we take questions, I have a couple of announcements I'd like to make. For those of you who aren't staying all night with us, I suggest that you arrive early tomorrow for a number of reasons. Parking is one, and other logistics. Among a large group of distinguished guests that we have visiting the laboratory tomorrow will be the Vice President, Mr. Quayle, and we expect a large turnout. There will be a speech by Mr. Quayle on the steps of the tall glass building across the mall from the auditorium at 8:40. That's open to photo coverage, still photo and television cameras. Then he will appear down here in the auditorium at about 9:10 to 9:15. We're not sure the exact time. At that time, he will take questions from the press. And in addition to that, we are going to start a rebadging activity today after the press conference. So please check with the PIO folks out in the newsroom. You will have to exchange your badge for a new one. And be prepared to show your press credentials. Also, we're going to have a rather short question period today because our panel has a commitment elsewhere. Maybe we can talk them into coming back later in the day, but we will have to keep it short. Patrick?
Could I ask, please, have we yet any precise evaluation of the density of Triton's atmosphere, please?
We do not. Linda?
Hello? Hello? Okay. Linda Doran, San Gabriel Valley Tribune. Do you have any determination yet whether the moons that you've discovered so far could be in a position to be shepherding the rings.
There are two satellites associated with the two rings. Those are N3 and N4. There have been no other satellites observed in the vicinity of those two rings.
Yes, right down there in the first row.
Horst Rademacher, Frank. Oh, doesn't work. Does it work? Yeah. Horst Rademacher, Frankfurter Allgemeine Zeitung, West Germany. I have a question for Ed Stone. A couple of days ago, you told us that you were going to take ultraviolet images or ultraviolet measurements from the southern hemisphere to look for auroral activities. Did you find any? Number one, and number two, you mentioned that at the very beginning of your presentation today that you found some anomalies or anomalous results near the bow shock that you are going to fly through. What are these anomalous results?
We don't know we don't understand what the magnetic field certainly had some significant changes to it, and this afternoon we're going to have a discussion to try to understand it. It's unlike anything we've seen before. That's the impression that I have, yes. No indication yet of any aurora. Again, I hope to hear some more this afternoon from everybody. It's not booming bright, that's clear.
Bob Bazell on the aisle.
This is a question for Brad Smith, and this is logistics, not science. We have a schedule from the Public Information Office that indicates we won't be getting any real-time pictures from 11:24 p.m. tonight until 3:40 a.m. tomorrow, because other equipment on the spacecraft will be playing back. You just mentioned that we'd be getting a picture at 1:50, and now I'm even more confused than I was before.
And you've confused me as well. I don't know the answer to that. That's the information that I took down from the timeline. That there would be a tape replay at that time to send that image down. So
Generally correct that there will be no real-time pictures coming in from about midnight tonight till about 20 to 7 tomorrow morning?
No, there will be real-time images before 20 minutes till 7.
I don't have anything listed. This is not complete. This is the next day. This is not complete. Well, it doesn't sound... You said no real-time images from when to when?
11:24 p.m. to 3:40 a.m.
I think that's not correct, but I don't have the material with me yet.
Well, we would, those of us who need these images would really appreciate it. Correct.
We'll try to sort that out, Bob. We'll do it today. Lee Dye.
Lee Dye, LA Times. Brad, if N1 is larger than Nereid, why was Nereid detected from Earth and not N1? Is it just a matter of albedo?
It goes way, way out away from Neptune. It goes so far out that in a typical field of view of an astronomical telescope, Neptune is out of the field of view when you're looking at Nereid. N1, on the other hand, is so close that it's just simply lost in the glare of Neptune, and that's why we couldn't see it from the Earth.
Tom?
Tom Elias, Scripps Howard Newspapers. Is this working?
Yeah.
Okay. For either Dr. Stone or Dr. Smith, I wonder, why are we seeing cloud shadows here and not on other planets? Does this suggest anything at all about a planetary surface by any chance? And about Triton, do we have any new ideas about why we're getting blue?
Go ahead. What it's saying about the Neptune atmosphere that apparently has not been seen on the other planets is that there are very high clouds and then a relatively clear region down some considerable distance to a cloud deck below that. As I said, perhaps 50, maybe even 75 kilometers. It's just an indication of a structure in Neptune's atmosphere that we have not seen in at the other giant planets. With regard to the blue color, we've talked that around a bit more. There may be some other explanations, and we're pursuing those, but the explanation that I gave, that it could be due to Rayleigh scattering by very, very small ice crystals, seems to be still reasonable.
Jonathan?
looking at Triton, we're seeing it looking way down in the southern hemisphere, so it's really hard to tell what's going on in the north, but I am reminded from that little bit that we're seeing, are you seeing what may be a marked hemispherical, north-south hemispherical asymmetry, like sort of as distinct as that on Iapetus, for instance, or are we maybe just seeing a, you should pardon the expression, Triton equatorial band?
We can't answer that because we're just seeing what we are seeing. Clearly, the region in the south is bright. The darkest regions start a little bit below the equator and move up northward from there. But we haven't yet had a look further north. We will see further north as we approach Triton early tomorrow morning.
As far as you can tell from looking closely at those images, as far as we can see up at the top, looks like dark all the way to the edge.
Yeah, but we can only see up to about 20, 25 degrees north at the moment.
Lee?
Lee Siegel, AP. Norm, a couple things. You didn't mention a close encounter distance for Triton, if you could give us that, and when the second entry into the second Earth Sun occultation, is. And finally, on behalf of one of our newspaper members, what would happen if a speck of dust hit Voyager?
Well, it depended on how big it was and how fast it was moving and where it hit, I think. But we've probably been hit before. We don't want to encounter a whole lot of those. So it really is problematical what would happen if it was going fast enough and had enough mass. It could do some damage.
Norm, I could add that actually if it's really dust, if it's micron-sized particles, micrometer-sized particles, we have in fact sensed exactly those particles every time we've gone through a ring plane at one of the giant planets. Dust doesn't bother the spacecraft, BBs would.
Lee, relative to your first question, I just gave that sheet of paper that I had written all the things down on to the Public Information Office people to have transcribed. I do have the distance of Triton closest approach on there, so it'll be available. My recollection is it's in kilometers, it's like 39,700 and something. Here we go.
I think that's it, isn't it?
All right. 39,872.
To the center.
That's the center, right.
From the surface?
From the surface, you have to subtract, what, 1360?
1360, roughly.
1,360 kilometers.
Also in the last row on this side.
Richard Harris from National Public Radio. For Dr. Stone, yesterday, as I recall, you were predicting that the spacecraft would pass into the magnetosphere of the planet around midnight last night, and apparently it has not yet. What does that tell us about the strength of the magnetic field? Or
well, it's a combination. It means the field is not as strong as it might have been, and that perhaps the solar wind conditions are somewhat stronger than we thought they might be. I mean, the solar wind, after all, is like weather. And so the combination of a stronger wind and a weaker than expected or weaker than possible magnetic field would all result in a later bow shock crossing. You may remember I did give you a chart showing you a whole range of crossing times depending on how strong the field was.
Gilbert?
I wonder from a celestial mechanics point of view, I'm sorry, Govert Schilling, working for Dutch newspapers. From a celestial mechanics point of view, could there be any influence from the inclination of the new moon N6 on the confinement of the material in the ring arc, or would it be too far away?
I think it's too early to say. What is critical, the exact locations of moons and arcs are critical. They can't just be inside. They have to be precisely at some particular location inside. So I think it's too early to say. One has to know very accurately exactly where the moon orbits and exactly where the ring orbits. And the team is working on that, but they haven't yet pulled it all together. I wouldn't want to exclude it at this time.
Rick Gore?
Brad, that inclination on the new satellite, 4 degrees, 2.5 degrees, what implication does that have, and why would it be inclined?
Well, when satellites form around a planet or are captured or whatever, they may start off at any particular inclination, Then there's a process by which planets tend to force material into the equatorial plane. Now, it may have started at a high inclination and still has some residual inclination left over. It may be maintained in that by some interaction with the other satellites. But there's a tendency for things to be pushed into the equatorial plane. And that has implications for tonight, by the way. Any debris that's around the planet tends to force it into the equatorial plane, and that means that so-called ring plane crossing would be the most hazardous time for the spacecraft.
Over here on the center aisle.
Yes, Olivier de Goursac from the Figaro and the CNES magazine. Do you have an exact diameter right now for Triton? And a possible density you might think of something from the interior of the satellite? Because it seems icy, or if you... but do you have correct values right now with images by the number of pixels you have? And could you at least give us a kind of diameter?
The radius is approximately 1,380 kilometers. That may be better determined now than it was a few days ago, but it can't be far from that number. As far as density is concerned, we have to know the mass first, and that will come out of the encounter tonight. So we will have a density shortly.
Glenda?
Is this on? Glenda Chu from the San Jose Mercury. I have two questions. One is, I understand that the magnetic field people at about 8 o'clock last night believed that they had crossed the bow shock and were very excited about it, and in fact believed that the magnetic field was maybe 5 or 6 times stronger than previously believed. It sounds now that you believe that that did not happen, and in fact that other instruments didn't confirm that. And I wonder if you could elaborate on what appears to be happening there with this weird phenomenon. The second one is, I understand also that there's been some confirmation due to albedo measurements of methane ice on Triton on the surface, and I wonder what that says about the possibility of there being other forms of methane on the surface, such as liquid and so on.
Well, first of all, indeed the magnetic field did change, and that's part of this unusual property that I was discussing, which we still don't understand. But the solar wind itself, which moves at 400 kilometers per second, or about 1 million miles per hour, did not change. And certainly the classical signature of a bow shock, which is a supersonic shock, is there's an abrupt change in the solar wind speed. And so there is a puzzle, which we hopefully will be sorting out as to what was happening. But I think we don't have a classical shock in the sense that the solar wind has gone subsonic. In terms of the methane ice, there was ground-based data which told us there was methane ice. I think that's not a new result. And the temperature there is much too cold for liquid methane.
Yes, over on this aisle.
Heather Cooper, Pioneer Productions in London. I have a question for Brad. Brad, I appreciate you're having problems measuring the wind velocities, but is there any indication you're getting these high-speed jet streams as you found on Saturn?
There are winds which have velocities which are comparable to what we've seen on the other planets, that is, in the range of several hundred meters per second. But how narrowly confined they are at the moment is we don't have information on that. That requires a lot of measurements and getting around this problem where the clouds seem to change on short time scales.
Yeah, I just got a note that the film which I showed this morning, it was the first time really I'd seen it, and I want to make sure that the people who really did the work get the credit. And the people who did the work to get the film put together is the image analysis group here at JPL under Gary Solomon, who's the group supervisor. And that's the group that was using the Mark III hypercube along with the digital image analysis lab. I'm sorry if I didn't get the story straight when I showed the tape.
In the second row, over on this side.
Bob McDonald from Canadian Broadcasting Corporation. I have two questions, one for Norm. Yesterday you told us that your accuracy and trajectory was plus or minus 33 kilometers. Are you any more accurate today? And can you give us an analogy of just how accurate that is in some way? And the other is for Dr. Stone, your experiment to maintain contact with the spacecraft while it's behind the planet through this refraction, you've never done that before. Is there something you're expecting to get from that experiment that you haven't tried before on the Voyager mission?
Yesterday, I think I told you that our uncertainty in the estimate of where we were going, that is, if you think you're going to spot X, our uncertainty is a little circle around that, was about 33 kilometers at the Neptune aim point. As of today, it's about 30 kilometers, which basically says that's about as good as we're going to do it, which isn't bad. It's within 20 miles of the point we aimed at, 3 billion miles away. So it's not bad shooting. The time of flight uncertainty is, we are about a little more than 4 minutes early. We did not try to correct that with maneuvers. We had the ability to modify the sequences to take into account the fact that we're 4 minutes early. So we didn't try to change the time of flight, we just let it go. But our uncertainty in that estimate is down to a little more than 1 second now. So we believe that time is accurate to about 1.2 seconds.
Yeah, we did at Uranus, in fact, exactly the same experiment and did maintain contact throughout the track around the limb, and that allows us to probe much more deeply in the atmosphere than is possible if we just use the entrance and exit of the occultation event. I'd like to add one other thing. I see this note I got that was an 8-node hypercube, not a 128 node. I certainly didn't get all the information, did I? Only 8 nodes, so if we had the 128, they could do it in real time, I think.
And today is Thursday.
And today's Thursday, yeah. Just think what it's going to be like tomorrow after we haven't had any sleep.
Back in the radio area, Terry.
This is Jim Banky of Florida Today. You've mentioned when some of the high-resolution images are coming in. Could you say of the images yet to come, which ones you're looking most forward to seeing? When will they arrive here? And could you reveal what some of your Voyager science team people will be doing tonight? Is everyone staying up all night tonight?
Well, for the imaging team, I can't say that everyone will, but many will, because next to most interesting images of Triton will be coming down in the early morning hours. We are continuing for a while to keep getting higher resolution images of Neptune, and what's interesting among them, they're all interesting because they're all showing things that we hadn't seen before, particularly with a wide angle. It's going to be a very exciting evening, and most of us will be up there watching everything that comes in.
First row on the far end.
Carlos Byers, Houston Chronicle. When you're discussing the winds on Neptune and the different velocities, what are some of the maximums that you're looking at there? And secondly, Brad, you think what are the prospects for more satellites?
Let me pick the satellite thing first. Steve Sennett, who is with the navigation team and also a member of our imaging team, is the one who has been spending most of his time looking for satellites. He has so many other duties to perform. That's why we're a little slow getting this information out. I think his comment to me yesterday was we're reaching the bottom of the barrel, but still there are many images where the very faintest suspects have not even been identified yet. So one would certainly not want to say at this point that we've seen all the satellites we're going to see. On the other hand, we have no active suspects at the moment. And I'm sorry, the first question dealt with the wind velocities and what...
Various levels that you're seeing, any input on that at all?
You mean differences in velocity, or are we talking about heights in the atmosphere?
No, on velocities. If you've been able to develop anything at all. We know that they're very high, but I was just wondering.
Yeah, the velocities are high. We're talking typically of velocities that we've seen on each of the major planets in the outer solar system we've looked at. The velocities seem to be up in this range of a few hundred kilometers per second. And that's rather peculiar because there's an enormous range of energy that's being dumped into these atmospheres from Jupiter on out to Neptune. The velocities all seem to be up in that same range. Now, what's interesting is how narrowly confined, how narrow are these jets. We saw some extremely narrow jets on Jupiter. Whether we'll see such narrowly confined jets on Neptune hasn't been determined yet.
Also in the first row.
Let me come back to this magnetosphere thing again. You said there is no shock where the solar wind gets subsonic. Did I understand you correctly?
Well, we haven't found it yet. It's almost certainly there. But we haven't gotten there yet, as of at least 9:20. It may have happened since.
Kelly?
Stone, do you expect that Voyager will be passing close enough to Neptune to go through its ionosphere? And if so, what manifestations would you anticipate?
No, we're some 3,000 kilometers up above the North Pole, so we don't expect any serious problems with the spacecraft at all from an atmospheric point of view.
Yes, right across the aisle.
3,000 miles, sorry, 5,000 kilometers, yes, thank you.
Tom Siegfried, Dallas Morning News. Could you tell us, Dr. Stone, at the exact moment of the closest encounter, what instruments on Voyager will be doing what right at that point?
At closest approach? At closest approach, all of the instruments will be on. The tape recorder will be recording the data because there will be no downlink telemetry. The transmitter will be left on, but without any modulation. So for the radio science occultation experiment, but all the experiments will essentially be recording data for later playback.
What about the cameras? Where will the cameras be pointing?
Well, I think at the moment of closest approach, I don't believe there are any images being taken at that moment. No.
Too fast.
We have a question from the other JPL viewing area.
Don Dixon, Orange County Register. Could you estimate the magnitude of the rings as observed from Voyager's current position? Would they be greater than 6 magnitude?
They would not. I think they would not. They're in terms of stellar magnitudes, the limit for the Voyager cameras is something of the order of ninth magnitude or so. They're just barely showing up in the narrow angle, perhaps in the wide angle. I don't know. It's a difficult thing to say. If you were riding aboard the spacecraft, you might just barely be able to pick them out with your eye.
The far last row, over on the end.
Is there any thought that the solar maximum or solar flares is accounting for the anomalies that you're seeing in the magnetosphere?
Well, I think it's too early to say. We had very quiet solar wind conditions for the last several weeks, and so it's a puzzle at this point. It's just too early to say.
I understand that we're going to have to conclude about 20 minutes after 11 or about 11:25 at the latest. Is that right?
Yes.
Okay. So we'll take all the questions we can. David Chandler?
David Chandler of the Boston Globe. Dr. Smith, you said that the image that you showed this morning was the highest resolution we're going to have of the great spot. Do you have any estimate yet as to the speeds of the circulating winds in that spot? And since you've got your highest resolution image, what's your sense of whether it's going, how closely you're going to be able to nail that down?
What we see clearly are these high-level cirrus-type clouds. That isn't necessarily telling us what is happening down in the dark spot itself. There's certainly not been any. There's not been any structure in there which just really stands out. It's going to take a bit of rather sophisticated image processing to bring out any structure that may exist in the spot itself, and we have not had time to do that yet.
Do you think it's going to be possible to get those speeds though?
If we can indeed pick out recognizable features, then we can measure the velocities. Yeah.
Lee?
Dr. Stone, is this on?
Could you just briefly, what's Neptune's gravity? Could you quantify it for us? And second, could whichever one of you or all of you would like to wax philosophical for a moment about how you feel after 12 years and being here at the last planet?
I don't know the gravity. I can't tell you off the top of my head. We can look that up, but I don't know what it is. 1.14 times Earth. There's the answer. Thank you.
You know, Lee, we're all caught up in the encounter right now. You know, it's all going to sink in the next few days. That would be the time to ask the question.
Kevin?
In looking at yesterday's image of the Great Dark Spot and also the images you showed today, I begin to see something that looks very much like overlapping ellipses, with the overlap regions darkened relative to the rest. Could you say something about that?
Well, we've noted that patterns do tend to form, and the structure of that spot changes dramatically. In that sense, it's very different from the Great Red Spot. And there are features which seem to overlap others. All I can say is we've noted the same thing, but haven't been able to draw any conclusions from that yet.
Yes, in the last row.
Dr. Stone, in your presentation, you called attention to a little circle that had been drawn on Neptune. I'm not sure I understood what the significance of that circle.
That's the field of view of the infrared measurement that's being made of that particular spot in the atmosphere, which is the spot where the radio occultation, the radio beam comes out of the atmosphere after occultation.
In the back, on the other side, standing.
KGIL radio. I know you probably don't want to look beyond Neptune at this point, but realistically, beyond this encounter, how long do you think, knowing what you know now, the Voyager craft will stay together and remain viable?
Well, if nothing breaks, and that, of course, can't be predicted, we have enough power, fuel, and so on to keep tracking the spacecraft for another 25 to 30 years, at which point Voyager 1 will be some 130 times as far from the Sun as the Earth is. May well be in the interstellar medium by then.
Also in the back.
Peter Bond for the Independent newspaper in England. I understand that the Great Dark Spot is comparable to a hole in the atmosphere. You're looking deeper. But I also understand that on the false color image you showed, the center of the spot showed white, which you said was for a high level atmospheric feature. Could you clarify that for me, please?
We now have evidence that there is a cloud layer at some particular height in the atmosphere of Neptune, and that there are these bright white clouds that may be 50 or more kilometers above that surface. Probably what we see as the Great Dark Spot is down at that lower layer, maybe 50 to 75 kilometers below. It isn't necessarily a hole. It may be a low-pressure region, or it may actually be a high-pressure region. In order to determine which it is, we need to measure its vorticity, whether it's cyclonic or anticyclonic, and that has not yet been done.
Standing on the left side.
Carl Hodge, the Arizona Republic. Will there be a time, even before the images come in, when you can say that you have indeed reached the predicted closest encounter? When will you know for sure you're there?
I think you could safely say that 101.39 or whatever it is will be our closest approach.
We'll know by looking at the clock, I think.
Right, right.
That's right.
Trudy?
Trudy Bell, IEEE Spectrum. Are there going to be any other images that may reveal more about the structure and the behavior of the scooter? Or have you been able to do any analysis on the ones that you have that give any more idea about it?
It has been targeted for high resolution imaging. I don't know right at the moment how successful that targeting was, but certainly it was targeted for high resolution imaging.
Yes, right next to you there, Ed.
Dr. Smith, Roger Hutchins from England. We're seeing in dramatic detail the resolution growing on the storm features you've been seeing for months, but we're not seeing an increasing comparable resolution in other structure in the atmosphere. I know you haven't got all the data in yet on analysing the haze layers, but can you give us an idea as to whether it's giving you a clue about the nature of the haze layers, bearing in mind that Uranus also didn't resolve as we got a lot closer?
Yeah, certainly that's one of the objectives of this investigation. Many of the images that will be useful are taken fairly close to encounter, and actually some when we have passed Neptune and looked back. And there are images which have been selected sort of specifically to work that problem. But as I've indicated, not all of the data are in yet, and I have no information at the moment about the structure other than these two fairly distinct layers that were demonstrated by the cloud shadows.
On this aisle.
Terence Murtagh, BBC Northern Ireland. Yesterday afternoon in the briefing they indicated you were planning on the outbound to get an image of Triton with the limb of Neptune in the foreground. Any indication at what time we could expect to see that?
Sorry, I don't have the information. Perhaps we can get it for you.
David?
Neptune's color is very similar to that of Uranus, and for similar reasons, but many of the photos that have come out in the last few days seem to have a significantly deeper blue color. Is that a real difference between Neptune and Uranus, and if so, what does it tell us about its composition?
Well, all of the blue color, regardless of whether we've got the right color or not, is due to two effects. One really scattering, and the other, a more dominant effect, the absorption, selective absorption of certain parts of the spectrum by methane gas. It's not all that easy to define true color, because the filters that are used on the Voyager spacecraft have different sensitivities to particular spectral regions than the human eye does. The human eye begins to lose its sensitivity in going from blue down into violet. So we don't see violet as well as a camera might, and that tends to boost the violet color, or the deep blue color of these images. We could, of course, make corrections for that, but in the very short turnaround time that we have for producing materials for press briefings, we just haven't been able to do such an elegant type of processing. Oh, is it different? No, I would, just from looking at the spectral reflectivity, Uranus and Neptune are almost the same.
Toward the back on the left side here, Ed. Right there, the blue shirt.
Andrew Yee, Science North. Dr. Smith, can you say anything about the composition of Nereid based on the color and albedo information?
No, not precisely. The reflectivity is 10%. It's very similar to the reflectivity of some of the darker satellites that we're seeing around Uranus. It is just more of this dark material which seems to like the outer part of our solar system. Some of the best estimates, guesses that we can think of as to what it is that they're volatile materials, the ices that tend to form in the colder parts of the solar system that have been darkened by radiation.
Govert? Good.
Dr. Smith, I just wondered about the light blue color on Triton. Isn't that just what you would expect, being there's such a big, huge blue planet in Triton's sky? Couldn't it be some sort of Earth lights like the same we have on the moon?
If it were in a particular position, that I suppose could be an explanation. One was seeing a reflection of blue Neptune in the images on the surface of Triton, but where it happens to be, no. If we were seeing any reflection there, it would be black sky. So what we're seeing is really on the surface, and it really is a blue color.
We have time for just 2 or 3 more questions. Glenda?
Glenda Chu. I noticed on the old timeline for this afternoon that there's something called a phase function that is supposed to determine the amount of heat that's coming out of the interior. I wondered if that would be enough in itself to make some kind of determination of what is in the planet's interior, and if not, do you expect to get that kind of information from this encounter, and when would you know what is in there and what form it's taking?
Phase function. These are images, you say?
I don't think it said whether it was an image.
We'll have to check it out. I don't think there's anything immediately in the images that's going to tell us much about the interior of the planet. That has to come from an analysis of higher order gravitational terms that in the gravitational field.
First row, down here.
Luther Young from the Baltimore Sun. I have a question for Dr. Smith. Is the ring arc scenario probably dead now? And if it is, do you have any philosophical observations about the theory that was created to explain ground-based observations?
Well, I mean, look, the arcs, just the reason that people talk about arcs is because they saw an event happen on one side of the planet and they didn't see it happen on the other. And the most logical conclusion is that if there are rings, they're not complete. They don't go all the way around. Now, it was a handy term to use at the time. It was necessary in the literature. It was necessary for one astronomer to communicate with another. Did you see an arc at this point, etc.? What's going to happen now? Well, my guess is probably that that term will sort of go off into the sunset, although we do have to consider that this outer ring is a very peculiar ring. When you forget about all this extremely thin material that may now close all the way around, that still leaves a section of that ring about 35, 40, 45 degrees long, which is just very different from any other part of it. So in a sense, it's a semantical argument, and I can't predict what kind of nomenclature, what kind of terminology will go on into the years ahead.
We'll take one more question. Which hand did I miss before? Marguerite?
Marguerite Corriveau, Ozali Films in Montreal. This is a question for Brad. Concerning the clouds that you were looking at, you showed us 2 comparisons where you said it was very difficult to follow the structure of a particular cloud going from one image to the other. I wonder, do you have planned a series of images that can then be put into a time-lapse movie that will allow you to follow such structure more easily?
Essentially, we do that, although we don't actually prepare a movie. We make measurements on frames, and that all gets fed into a computer. The computer does the thinking for us. But what we're seeing, if you were looking down on the Great Dark Spot right now, just sitting up above it and looking down and watching it for a few hours, I think what you would see is not so much clouds moving around, but one that forms and disappears, another one that forms and disappears. It's because of these waves, and they're not giving us a measure of the velocity. It's just telling us that there are very high-speed winds going through there, that they're being deflected up and down, quite probably by the dark spot or something associated with it, and they tend to come and go rather than move. We've got to look for other types of features if we expect to actually be able to measure the winds.
That's all the time we have. Thank you very much, and please don't forget the rebadging exercise. We'll try to make it as easy as possible.
As well known, Voyager's closest brush with the planet Neptune was successful for another few hours when radio signals finally arrived in California from nearly 3 billion miles away. At midnight Eastern Time, the 1-ton craft was scheduled to sweep to within 3,000 miles of Neptune's north pole, then swoop to within 24,000 miles of the largest moon, Triton. Pictures received Thursday showed another ring of debris encircling about 90% of the frigid blue planet, plus more views of the complete ring discovered earlier. Other photos show 2 more previously undiscovered moons, bringing the planet's total so far to 8. Scientists hope to learn a lot more about the strange moon Triton, a pinkish satellite with a transparent atmosphere that may feature glaciers of frozen methane, natural gas.
My name is Rex Ridenauer. He's a mission planner with JPL. We have to wait for these photographs to arrive, the closest ones ever, but we are getting a couple of new photographs in, and if we could take a look at them here, maybe you could explain what it is that we're about to see.
Okay. And this is, I believe, we're going to put up the latest image here shortly. It turns out that for the last whole day we've been getting all sorts of spectacular pictures of not only the planet and its atmosphere features, but also the ring arcs, which we now think are complete rings, and also the large moon Triton, which is moving around backwards around the center of the planet compared to what we would normally think. And this first image, a great deal of effort went into making sure that we could predict where this was going to be as we're close to the planet. This is just before we went over the ring plane. And
what's the significance of this?
Well, this is the very middle of the densest part of any of the rings that we've seen at Neptune. And this is what was causing us to think there were ring arcs for the last 5 years since they were discovered. Okay, and this is a very close picture of Triton, a couple of them that just came back. We wanted to take these just before we crossed the ring plane going over the top of Neptune, because there's always a possibility that we modeled things wrong, and we wanted to make sure we got something good just before we went through all these hazardous zones around Neptune, because there is a small probability that we wouldn't have ever gotten anything else.
Rex, this is Triton. And
this is Triton.
And we should make it known that although Neptune, we've never seen it before, like we will be seeing it in several hours, most of the scientists and engineers here have really been very excited, more so it would seem, about Triton than about Neptune. How come?
Right. For years, Triton's been just as much a priority as Neptune because of 2 basic things. One is it's the only large moon in the solar system, and by large I mean something like the size of our moon, that goes backwards around the planet opposite the rotation of the main planet. And the only way that can happen, based on what we understand about how the solar system was formed, was that must have gone through some sort of really cataclysmic collision or disruption in its orbit. And the best hypothesis is that it actually entered Neptune from somewhere else and just got rammed into by moons around Neptune, and then somehow lost enough energy to get captured in an orbit around Neptune. That's one. This is also Triton overexposed, and that's primarily most likely for a navigation fix on where the actual picture was taken. Now, the other thing interesting about Triton is that for years we've known that it appears to have an atmosphere because of the signals we see from the ground, and it also seems to have a coating of methane, which is natural gas, and probably frozen because it's so cold out there. And so the real excitement coming up this morning is going to be close-up pictures down to maybe a half mile in detail of not only the frozen surface that it looks like from these pictures that you can see some geography, but it also looks like it's coated with something very white. And it may be a mix of mountain peaks or something, craters with frosty coatings all over. And then on the other side of the planet, where it's even colder, this frozen natural gas has not had a chance to stay white. It's turned black over the years because it's been bombarded. And we're excited to see both sides of the planet, the moon here, in the next few hours.
What new discoveries might be made as it approaches Triton?
New discoveries might be that we don't know yet from these features we've seen so far whether it has any signs of this cataclysm that might have almost broken it apart in the past. It may have been a near collision that just splattered it all over the system, and there may be lots of evidence now of geology. It looks like we're going to see some, and that'll be the most spectacular, is what the geology looks like.
But we still have to wait for Triton. For now, we're waiting for the shots from Neptune, and I know you folks are very excited about that.
Well, the spacecraft right now is just about to start turning its cameras on Triton again, and those will be even more spectacular.
Rex, thank you very much for joining us. Rex Ridenauer, with a mission planner with JPL, joining us, as the excitement is certainly building here at JPL. Greg Lamont, CNN Live, at the Jet Propulsion Laboratory in Pasadena.
Important enough for this multi-million-dollar project. They have a number of other projects which they would like to prefer. The Cassini probe, for example, and Mars rover sample return. They do want to fly to Pluto, but in connection with what they call the 1000 AU mission. They have a super mission in mind for the years beyond 2000, which goes out of the solar system, out to 1,000 AUs, or astronomical units. And in doing so, it will fly by Pluto, sending back pictures from Pluto and then go out for the next 50 years. It's going to take it 50 years to go out 1,000 AUs. But that's a very long-range mission. We are still maybe 20, 30, 40 years away from that. And I haven't heard of any concrete plans for a Pluto probe before that.
All right. Michael Abacher?
We should probably point out that 1 AU is equal to the distance from the Earth to the Sun, something like 93 million miles. Neptune is approximately 30 AUs away. So when you think about that, that's 3 billion miles, that 1,000 AUs is an incredible distance. Pluto, unfortunately, was not in the right place at the right time to be included on this journey, and it would have been nice if it were so that that Voyager could continue to Pluto, although we should also point out that Pluto is now closer to us than Neptune is. Everyone learns
because of the shape of its orbit.
Because of the odd orbit that Pluto has, and its angle to the ecliptic, that Pluto sort of sneaks into the orbit of Neptune for a 20-year period. So from now until 1999, actually, Pluto will be closer to us than Neptune. The image just changed.
Derek Pitts, I noticed you looking at the image.
Well, we just had an image shift from the last image that was received from Voyager 2. We were looking before at Triton, and now it looks as if we have a very close-up picture. And I'm not exactly sure what this one is yet. Jessica, do you
think
have
I know what it is. That's Neptune again.
So we're right up
Yeah,
onto the
Neptune
cloud tops of Neptune?
These clouds are, I believe, about 30 miles. The methane clouds are 30 miles above the blue surface, the blue layer of clouds, and that's what's causing this shadowing effect, what it looks like here, a three-dimensional effect, because the methane clouds are so extremely high above the blue top layer. They had some wonderful pictures in this afternoon of this nature also.
It's about 78,000 miles away from the center of Neptune. So that picture was taken a considerable time before the closest approach. We always should remind people that we are talking about a time difference of 4 hours and 6 minutes.
Now, is this then a photograph that's being sent from the tape recorder that's on board Voyager then?
No,
that's
right.
why it's come up now?
Yes. Right now the tape recorder is being played back. At least, it was, 4 hours and 6 minutes ago.
A question I have about this image is these clouds that we're looking at, are these the clouds that appear white?
That's right. These are the methane white clouds.
The ones that scoot by real fast.
Right, and they believe now that they are approximately 30 miles above the blue layer that we see underneath.
We have as a guest here on the telephone James Glick, the former writer of science issues for the New York Times and author of Chaos, Making of a New Science, which explains a principle that many scientists feel is actually what is organizing our solar system. Welcome to Neptune All Night, James Glick.
Oh, thank you.
Could you briefly describe how chaos, I don't know if explaining how chaos can work can be done briefly, but what has been surprising about finding the storm in Neptune's surface, and how do you explain this in terms of chaos, and in terms of weather we might understand here on Earth?
Well, one of the very big surprises has been the discovery that Neptune is a very turbulent, dynamical place. It's surprising because it's so far away from the sun and it's so cold that astronomers had thought it was going to be pretty dead. What we're talking about, of course, is weather, otherworldly weather, and on Earth, the weather is very much driven by the sun. It heats the ground, which heats the air, and most of the motion that we're used to in the atmosphere here comes from that kind of heating. Our imagination about what the solar system is like has been very much preconditioned, of course, by our experience here on Earth. But it's turning out that things are not the same on the other planets. And Jupiter, of course, we've been watching these beautiful pictures tonight, has this now famous turbulence, the eddies that you can see, these whirls that look like turbulence in a stream, and the Great Red Spot. The Great Red Spot is described as a sort of storm, just like the spot on Neptune is now being described as a storm. But storms on Earth are very transient things. They come and go in a couple of days. The spot on Jupiter has been there for 400 years, which is 400 years that we know of, that is, since Galileo first saw it, and for all we know, for millions of years. It turns out that chaos specialists have managed to explain the spot as a dynamical process, not a storm in the sense that we know it on Earth, but a sort of giant whirlpool that sits amidst the chaotic turbulence of the atmosphere of these planets.
What might, if a human being were standing on Neptune, what would that storm feel like? Would there be winds? Would there be some sort of, do you have any speculation about it?
Well, it is very much like a storm on Earth. That is, it's swirling winds in a cyclonic motion like a hurricane, except in the opposite direction. But of course, it's many times larger than any storm on Earth. It's we've heard different estimates, but big enough to swallow up the planet Mars or big enough to swallow up the Earth. It's too soon to say whether this is a storm like the one on Jupiter that seems more or less permanent, or whether it's transient over a period of weeks or months or years. I don't think there's enough evidence yet, but it's this gigantic vortex that is stable in the sense that it's in the same place, and yet chaotic and turbulent in the same sense that any storm on Earth is chaotic.
Any further insight into your knowledge of chaos?
Well, of course, the solar system, the heavenly bodies, for a long time were the epitome of order for scientists. It was the regularity of the motion of the planets, the predictability of their motion, that really gave science its start. It's only recently that we've also begun to appreciate little bits of chaos in the solar system. And another example, very different from these storms.
Well, thank you very much, James Glick, for illuminating for us the storms that are going on Neptune. With pictures from space and voices from Earth, this is Neptune All Night. Universe beyond. Scientists in California should know in a few hours whether Voyager performed well during the climax of a spectacular 12-year journey. At midnight Eastern Time, the one-ton craft was scheduled to sweep to within 3,000 miles of Neptune's North Pole. Pictures received Thursday showed another ring of debris encircling about 90% of the frigid blue planet, plus more views of the complete ring discovered earlier. Other photos showed two more previously unknown moons, bringing Neptune's total now to 8. Scientists hope to learn a lot more about the strange moon Triton, a pinkish satellite with a transparent atmosphere that may feature glaciers of frozen methane. That's natural gas. Dan Blackburn has more from Pasadena.
The first stop on Voyager's grand tour was Jupiter. And interestingly, that now is the planet Neptune seems to most closely resemble. That's because the great dark storm system on Neptune is quite similar to Jupiter's famous Great Red Spot.
The Great Red Spot is a huge anticyclonic storm system, which means it's a high-pressure region. And then we see smaller spots, white spots, which can be seen from the Earth, and then dozens of smaller spots that couldn't be seen at all. And I think it was the abundance of these small, rapidly rotating storm systems, which was really quite surprising.
Jupiter also had the solar system's most surprising moon to date, volcanic Io. Voyager cameras revealed that Io has 8 active volcanoes, one of which hurls out debris at the rate of 200 miles an hour, 50 times faster than Earth's Mount Etna. Voyager also discovered that Jupiter has a tenuous ring system with a halo effect.
An extended halo of fine particles that is believed to be the result of the charging, the electrostatic charging of the tiny dust particles, and then their interaction with Jupiter's tilted magnetic field. So it is very different in character from the other ring systems.
Of course, the best-known rings surveyed by Voyager were those at Saturn, the ringed planet. Saturn's rings contain chunks of ice ranging in size from small pebbles to objects as big as large houses. Voyager discovered the surprising braided F ring at Saturn, which is held in place by 2 so-called shepherding moons. And these spoke-like features, which scientists believe are caused by the presence of dust particles floating above the rings. Saturn itself has enormous winds, blowing at more than 1,000 miles an hour. Saturn also has a huge moon, Titan, with a thick atmosphere and smog similar to that on Earth. Titan bears a resemblance to Neptune's Triton, but actually may have extraordinary oceans.
We now believe, based on calculations, that ethane, which is a light hydrocarbon, is actually present in the form of oceans on the surface of Titan, having been made in the atmosphere out of the methane.
The most recent stop on Voyager's grand tour was Uranus, a planet with a strong magnetic field uniquely tilted 60 degrees from the planet's axis, sort of like having Earth's magnetic north in the vicinity of Los Angeles. Like Neptune, Uranus is mostly gaseous, hydrogen, helium, and methane.
It has no solid surface to stand on. Certainly it's not a place where man could live easily. There's just no oxygen, no water really in those portions of the atmosphere, and no place to stand.
Uranus had 15 moons. One of them, Miranda, appears to have thawed and refrozen, something which astounded scientists. Uranus also has a series of rings, which may resemble the ring material around Neptune. Voyager left Uranus 3 years ago en route to Neptune, where now the spacecraft's grand tour is nearing an end. And more discoveries are all but certain in the wake of Voyager's close encounter. Dan Blackburn, CNN at the Jet Propulsion Laboratory in Pasadena.
I've seen rain there for a good while, especially in California. Temperatures...
The planet managed to resurface itself at some level down to some depth. Did this occur 3 billion years ago, 4 billion years ago as a result of melting when Triton got into orbit around Neptune? Everything since then has just been volatiles blowing around on the surface, or has there been more recent activity? I think there's going to be a lot of speculation about that.
So it's very clear, even at this kind of resolution, that it is a planet that has been resurfaced.
Yeah, you asked what kinds of volcanism. Well, in the case of the terrestrial planets, molten silicate, of course, lava at 1,200, 1,400 degrees. What we've learned is that as you move out in the solar system, the basic processes seem to carry over, but the ingredients change.
Right.
So in the case of Io, sulfur and sulfur dioxide are the materials that we believe drive the volcanic systems, heated by silicates in that case. In the outer moons, particularly out in the Uranian system, Ariel's volcanism models that have been proposed include ammonia mixed with water ice, lowers the melting point temperature of that by enough so that even in those very cold environments you could have plastic material in the interior. We know that methane exists on Triton, and nitrogen in Titan's atmosphere was abundant, along with a small amount of methane. So if nitrogen is there, this thing is so cold that the nitrogen and methane will condense as a solid. And those two mixed as a solid could be a very soft and pliable material. And in fact, we haven't come up with what the energy source is to drive this material if there are active processes going on. But we have a lot of thoughts as to what kinds of materials you could invent, which would be soft enough to be flow like glaciers, or even erupt in a volcanic sense. We've coined the term cryovolcanism. That's when you have volcanism that occurs at the temperatures of things like liquid nitrogen.
Yeah, I think that the energy source that Larry mentioned is going to be the big problem here. We have at least a theoretical abundant energy source early in Triton's history with the capture hypothesis, the tidal evolution of the orbit, which would produce tides, and that could produce very violent types of events in principle. And the question is, how long did that heating last? Is there any residuum of it now? There's no obvious current energy source other than the sun, other than the ancient energy source at Triton. So one thing I think is interesting is we had the same question about Europa surface. Galileo may get the answer to that. We also had that question about Enceladus' surface. In both cases, we were denied the pictures for one reason or another at the kilometer and sub-kilometer scale that might tell us the detailed history of the last few 100 million years to 1 billion years. And with any luck, we got our fingers crossed, we're going to get those tomorrow morning for Triton. This may help unravel some of the mysteries for some of the other icy satellites as well.
So it's kind of ironic that Voyager's last encounter with the big world, we might go back and solve some of the mysteries early on.
Voyager's done it again. Everything we see surprises us.
That's great. Any Any anticipation of what we might see in a few hours when the first
Well,
of the high-resolution mosaics?
The high-resolution mosaic, which occurs just as Voyager 2 passes over Triton's northern hemisphere, just by serendipity, happens to lie on precisely where we'd like it to, and that is the transition between the bright and dark area. There in the top part of that particular image there.
This is the color image that
this
was
boundary goes,
shown today.
This, the south polar cap is right here. I'm sorry, the south pole is right here. The object rotates this way, so in a westward sense. This boundary between the dark northern plains and the bright southern hemisphere is roughly at the equator. And so as you can imagine, one model might be a polar cap that extends all the way to the equator. The high-resolution views will actually be in the opposite hemisphere, but it looks somewhat like this. And it will cover from this point, a point something like this, down to something like that. So we will have high-resolution views. I think there are 10 images which will cover this transition zone. Those will be the most exciting in terms of the debate of, is this a young, fresh surface, an old surface? Was Triton captured and melted very early in its history? The tidal dampening down of the orbit into a circular orbit can be fairly fast. Now, the early bombardment of the solar system, the inner solar system, lasted somewhere between 1/2 and 3/4 of a billion years, we estimate. In the outer solar
last bit of
system,
accumulation
right,
material.
sort of the sweep up of all the residual junk. As you go farther from the sun, it takes longer, and some models claim that it never really swept up. But so Triton could have been captured extremely early. In other words, if it was during this period when the protoplanets were zinging around and accreting together to form the giant planets, if it was soon thereafter that Triton was captured, and then orbitally the orbit evolved and the melting occurred, then we might expect to see a very cratered surface, at least as cratered as the plains on things like Ariel and the moon, our moon.
Do we have enough resolution now to make that statement one way or the other?
I think that, personally, I would say that from the image you're looking at, we already know that it's not a heavily cratered surface of the sort of Oberon or Mercury, and so we're looking at something which is more in the Enceladus or Europa class.
Which hardly had any craters at all.
Right, or the Earth's moon, the Maria, in the Earth. So things that could be a few billion years. Now, whether or not it could be a few 100 million years or a few million years or a few years or a few days, we'll have to wait and see.
Yeah, putting that absolute time scale is difficult in the outer solar system, though, because models range over a very, very large degree as to how old, as to when even Neptune formed. Some models would have it forming fairly recently.
Yeah.
That will, the very highest resolution pictures may be the key to that. Trying to tell the exact age of one of these surfaces when you're sort of in between extremes is very difficult. If you're at one extreme or the other, either no craters or lots and lots of craters, you know pretty much where you are.
Okay, the other thing is that even at this resolution so far, we can't see, this one has each pixel is about 10 kilometers. And in images of Io, another moon, which in that case turned out to be extremely active geologically. And by the way, at this resolution, the dark caldera floors of Io convinced a lot of people they were looking at craters.
That's right.
So there's a lesson to those who will learn. At this resolution, the limb is quite smooth. And you would have seen some of the mountainous topography just starting to show up at this resolution. Next resolution will tell us that. If that's the case, even though it could be an ancient body, if these ices of methane and ammonia, or ammonia is incorporated and methane and nitrogen are incorporated into these materials, this could be a big, sloppy, soft bog of sort of hydrocarbons. So in that, it's young because craters are formed and they simply slough away and rebound. Sort of like a giant pudding surface.
In terms of changes or activity, there's another possibility of activity, and that's the atmosphere. Triton's very unique because it has an atmosphere, and in fact, data taken from the ground 10 years ago paint a different picture of the kind of colors and brightness that we're seeing now, don't they?
Well, we know that methane exists there. To the extent that methane absorption is due to gas or due to solid methane is debatable. Now, as you've heard, the fact that the southern hemisphere, which is illuminated by currently by the sun, is so bright, sets the temperature down so that the surface pressure, if it's due to methane alone...
So you're saying even though the sun is shining on the southern hemisphere, it's very cold because it's very bright, so most of the light is reflected away.
So we're down, if it's methane alone, we're talking about something like 1/10 of a microbar. And as I recall, that's not unlike the extremely tenuous SO2 transient atmospheres on Io. On the other hand, if nitrogen is there at those temperatures, we're talking about something like 1/6 to 1/60th of the pressure of the Martian atmosphere, about 1 millibar. And under those two sets of circumstances, we could have very different surface environments.
Like day and night.
Like day and night.
Yeah, I think the atmosphere and the interaction with the surface may play a major role, at least in the superficial appearance of the planet. This is one of the things. I mean, mountains are mountains. Cover them with snow, they look rather different. And we may find that things like the color changes and things of that sort may be due to even very small amounts of volatiles condensing and evaporating at different parts of the planet. What we're seeing, in addition to that, indicates that perhaps even more major activity has gone on, and trying to figure the depths of how much material is built up over geological time. It would be similar in many ways to trying to unravel the history of the Martian polar caps, for instance, a problem Larry Soderholm is very familiar with and still isn't totally solved despite all of our trips to Mars.
So that's really another analog for this kind of modifying a surface to a large degree by volatiles.
Yes.
Martian.
Yeah. But also, in terms of back to the snow on the mountains, one of the interesting problems with this polar cap is we've learned some lessons both from Mars and from Io. In the case of Mars, the polar cap seasonally, one cap is heated and it sublimes along its margin, and the CO2 then is being condensed at the opposite pole, which is in the seasonally dark at that time. In the case of Io, the poles are rather dark, and what's happened is the bright material, the condensable, appears to have gone to the equator. Now, why is that? Well, it turns out that once you get it to the equator, it becomes quite stable, because even though there's more sunlight there, it's reflecting it so well that it's actually colder at the equator than it is at the higher latitudes.
So it's self-insulating.
So it's, in a sense, yeah. We can have a combination of those two factors here, in which you really could have a bizarre sort of phenomenon in which you have a polar cap which actually grows when you heat it. Okay, so as this stuff is subliming, instead of the gas being sublimed out, the frost subliming along here and migrating to the poles, maybe what it's doing now is subliming in here and condensing here and actually growing northward. This area up here could actually be warmer, would actually be warmer than this very bright frost. And as I recall, our colleagues on the imaging team have measured and corrected for the limb darkening function in Dunstan photometry that indicates this stuff is getting very close to 90% albedo. That makes it very cold.
So reflecting 90% of the light that shines on it.
Whereas this stuff up here is about half that. All right, so this is warmer by basically the fourth root of the difference in those albedo, or the ratio in those albedo.
We've been awake too long to do that kind of mathematics at this time, I think.
It'll get worse.
It'll get worse. So
it's guaranteed to get
an intriguing picture forming on Triton, and maybe the fulfillment of the expectation we all have about Voyager, but we're going to be surprised about some things.
Absolutely.
We have some other images of some of the other moons, and 2 new moons were announced today, and through some clever reprogramming of Voyager, we were also able to photograph 1989 N1, and these are some pictures that were released today, taken, I guess, yesterday, of 1989 N1. Isn't this a puzzle? This is a fairly large body, but it's not round.
Well, it's about the size of some other bodies we've seen, such as Miranda, Enceladus, and Mimas. And we have quite a collection of these kind of intermediate-sized bodies now. The things we can tell from initial analyses of images like this are, number one, the object is reasonably large. It's about 400 kilometers in diameter and fairly dark, around 5% reflectance. That's not dissimilar to what we've seen in other small satellites in the outer solar system, such as the inner moons of Uranus, such as Puck.
That's a dramatic difference between the 90% reflectivity of Triton, and here's something which is 5% reflectivity.
And we see this over and over again in planetary geology. When you see a dramatic difference like that, it usually means something has altered or happened to one of the bodies. Typically, we think that most of these bodies formed originally out of materials that were about equally abundant in ice and rock. And the rock probably had a component of very dark material in it, such as are found in primitive meteorites or dark organic materials. That initial mixture should have been dark, very similar to these small moons. When you see something that you think was made out of that initial mixture, which now has a bright surface, it means something's happened. And that something usually has to do with geology, the outgassing of volatiles, condensing of fresher materials on the surface.
So
the shape of these bodies also points to the same story, which is that they've been highly battered, fragmented, but probably not melted and probably not having fresh materials extruded or put on their surfaces.
So again, pointing to the oddball of the system being Triton, the one with the unusual brightness, and the dark albedos being the norm rather than the exception here.
Yeah, well, I'm not ready to this thing looks really unusual, N1, and the more recent images that we were looking at earlier in the day, it shows these large, sort of flat, facet-like...
We may have one on the still store.
...things on it.
We're getting a much larger picture of this moon. In fact, it may already be in the... It may already be in the on the tape recorder on the spacecraft, but you see, as Larry's pointing to here, is that the shape of this is quite irregular. The phase angle here is something we're going to have.
22 degrees.
Yeah,
I think
so it's really got a fairly irregular shape. Now, there's nothing impossible about keeping a shape like that if the material has been cooled.
Yeah, this thing's the size of Mimas, major.
Yeah, well, it's a large object, and the other thing is. The imaging, the last image, which we have labeled V1 Wow.
V1 Wow.
V1 Wow of this object will that will be roughly half the field of view of the camera.
Wow.
So about the same apparent size as the images of Triton that just came in a half an hour ago or so.
And those were incredibly spectacular.
Those were spectacular.
And we're undoubtedly in for some surprises there. The overall levels in those pictures, the brightness levels will be low because the object is so dark. But we will have a larger phase angle, so we expect to see more of this rough topography on N1, and we'll see what its geologic history has been. One thing I will bet with Larry is that it'll look different than Triton. And the differences will be interesting.
I don't know if anybody will take you up on that bet.
No question. All right.
Okay. Well, thanks very much. We've had a prediction of the another great, profound thing we'll be seeing that we look forward in the next few hours for the high-resolution mosaic to come down from Triton. We'll be back a little bit earlier for our next show. We'll start at 11:55 Pacific Daylight Time. We're going to have Ed Stone and a real-time receipt of the picture of the signal from the spacecraft at ring plane crossing. As you know, the rings are rather mysterious, they're irregular, and potentially dangerous to the spacecraft. The signals that are coming down now are somewhere between the orbits of Saturn and Jupiter on their way to the Earth, and we'll receive them in about 11:58 p.m. So join us very soon. I'm Rich Terrell for Voyager Updates. Thank you very much.
Silema Femen. Oitenis poteste
Des voix, des nuages, des mers, par-delà le soleil, par-delà les éthers.
Paz e felicidade a todos.
各位好嘛，祝各位
Tu te meus avec
健康
agilité.
快樂。
Et comme un bon nageur qui se pâme dans l'ombre, tu sillonnes gaiement l'immensité
สวัสดีค่ะสหายในธรณีโพ้นพวกเราในธรณีนี้
हमारे
ขอส่ง
दोस्त जो खला में बसते हैं इनके लिए दोस्ती और खैर
في
सगाली
النجوم يا ليت يجمعنا الزمان.
हमारी दिली ख्वाहिश है सारी दुनिया में अमन रहे
Mai Lagnia.
जिंदगी के हर
Liebe Freunde, Eid. Als Vorsitzender des Denkmalhauses
Sampai bertemu lagi di lain waktu.
Österreich, das freut mich, Ihnen auf diesem Wege
Hello from the children of planet Earth.
With pictures from space and voices from Earth, this is Neptune All Night.
And the voices that you are hearing before Neptune All Night are those voices that are on the disk that is aboard the Voyager 2 that are recording the sounds of some 148 languages of planet Earth, from Sumerian to Hittite to English, Russian. And you're listening and watching to this live broadcast with the pictures from the Jet Propulsion Laboratory and from the planet Neptune, the Voyager 2, and with a panel of experts here in Philadelphia to talk about all that we're seeing and hearing tonight. There's been excitement. There's a number of the scenes of Triton and the rings as well. Meanwhile, we have time to take a call from Philadelphia here for our experts. Good evening. I'm sorry we don't yet hear you, even though you're here in Philadelphia. And while, there we go.
Oh, hello.
Hello.
My name's Mark. I'm from Wilmington, Delaware. And me and a friend, we were elected to take a summer thing on researching wormholes. I'd like to know if Voyager can be used to pick up radiation or energy coming from a wormhole in space for location and later use in time travel.
We'd like to take that question. We'd like to speculate. Our science fiction writer, Judy Moffat.
No, I'm going to pass on that one.
You're going to pass on that one. Derek
I'll be
Pitts?
glad to start a little bit on that. I think one of the first things we need to do is establish that indeed there are wormholes that exist for us to be able to rotate the spacecraft toward or be able to manipulate it in such a way to find these things.
Now, why don't you first of all explain what a wormhole is?
Well, a wormhole is a theoretical location in space through which one might be able to travel, but at this point is generally guessed to be a place where energy in some form might return to the universe as we know it from the opposite of the wormhole, which is the black hole, where material is speculated to go in and disappear, and wormhole might be the place where that energy might come back out again.
Okay.
So we have to think about that as a, see if they really exist first.
Thank you, Derek Pitts. And in the next hour, we'll have George Tirebiter here on Neptune All Night. With pictures from space and voices from Earth, this is Neptune All Night, going out across the country to you this evening. And a reminder that we'll be going back to the Jet Propulsion Laboratory at 5 minutes to the hour. We're going to a phone call to Billy in Plainsville. Welcome to Neptune All Night.
Hello.
You have a question for the panel here in Philadelphia.
Excuse me?
Do you have a question?
Okay, this is not Billy, this is Rich.
Oh, well, Rich.
Yeah. My question was, I understand, I was watching how the Voyager was guided around the planets, used like the slingshot.
Yeah.
I was told about that. How would they guide it after it reaches the end of the solar system?
Derek Pitts, you want to take this one?
Sure. Once it passes by Neptune, it will and continues to pass by Triton, it will essentially be on its own for travel. The velocities that have been imparted to it by its path around these planets throw it out in the directions that we spoke of earlier. In the case of Voyager 2, we'll be sending it north out of the solar system toward the constellation Camelopardalis, and it will essentially continue in that direction unimpeded unless its motion or its path should be deflected by some other mass that might come into its path. Presently, we do not know of any other masses that will come into its path other than those very distant stars that we spoke of earlier. The closest one, or the one that it will come to first, Ross 248, which is about 10 light years away. So essentially, it should continue uninterrupted in its direction.
Jack Horkheimer?
Well, it could possibly get clobbered by a comet, because there are a lot of dark bodies out there that we don't see, because for every comet you see from Earth, there are millions of them that we never see. So if when it reaches the Oort cloud, I would think there'd be a fairly good chance that sometime or another this might get a little nick in its fender, so to speak. I mean, after all, when we went by Saturn with it, it did appear to get some dust in the slewing assembly, because that slewing assembly got messed up for several days, and it got jammed. Well, to slew the cameras back and forth. As a matter of fact, that was one of the problems when with the craft, was that one of the pieces of machinery that was working with the photographic equipment that got, they believe, some meteoritic dust in it, and caused the system to jam up. And at the time, I remember very well, some people at JPL were quite frantic about whether or not they would get the pictures they wanted.
Oh, one other thing we might add to that, it is possible that we could do some redirecting of it using the hydrazine thrusters, but the amount of fuel that's left, as Jessica has pointed out, is fairly low, and we won't be able to do much directing.
Well, I think what they want to say that hydrazine for is to make sure they can aim the antenna back towards Earth, right? Yeah, right.
Incidentally, the departure speed out of the solar system is 10 miles a second, and that remains rather constant. So after it leaves Neptune and goes out of the solar system, it'll travel at about 10 miles a second, or about 3.13 astronomical units per year. So everyone can calculate their distances from that. For each year, the distance is 3.13 astronomical units. And 1 astronomical unit is 93 million miles.
Joyce, Georgetown from the Franklin Institute. You see something on the...
Well, I just wanted to mention to anyone who is watching with us now that the pictures on the screen are not any of the bodies that are at Neptune or any of the moons around Neptune. These are actually images that were taken years ago. I believe these are all moons of Jupiter here that we're looking at, and they're just sort of interspersing different pictures for us so that we can look at some nice colorful pictures and results of what Voyager has done for us in the past.
And an interesting point to go along with that is that some of the scientists at JPL right now are using the information that we've learned from visits to Jupiter and Saturn as models for understanding, or trying to get an understanding of what the moons of Neptune and Neptune itself are like. So they provide now areas of study for us to look at.
There's the ring plane of Saturn on here now.
Now, the Voyagers have, particularly Voyager 2, has visited 4 planetary systems and a total of 60 worlds. If you count all the moons, it's 60 worlds. It was 58 today, but henceforth it'll be 60.
You know, this brings up an issue about these worlds. There are new moons that have been discovered around Neptune, and I understand they've been named N1, N2, N3, which sounds almost like a Lawrence Welk countdown to start the orchestra.
Right, that's right.
But maybe during the course of our phone calls tonight, we can take some suggestions, again, to Ira Flato.
I'm here with Rex Ridenour, who is a mission planner on the Voyager mission. Welcome to the program.
Thank you.
Now, it's taken many years to plan the mission. When did you first realize, or you've had to have some problems during the mission, and you've had to overcome some problems. Tell us about some of those problems, even at launch time. What happened right from the very beginning?
And here I'm speaking for the past teams that have been on this project since it's so long, but it turned out that for Voyager 2, about 9 months after launch, really because they were so busy worrying about Voyager 1 after its launch, it was launched second, its receiver, Voyager 2's receiver, automatically switched to the backup because of a fault protection algorithm on board, a routine that tells the spacecraft nobody's communicating with it.
So there was a malfunction in the receiver.
Yeah, and in the process of thinking we didn't have have a link, it switched to the backup receiver, and that failed. And then that failure made it go back to the original receiver, and that one also partially failed. So we've been operating ever since for about 11 and a half years on a very tenuous receiver, a receiver that's just barely able to work.
Mm-hmm.
But over the years, we've been able to handle that.
Mm-hmm.
And then at Saturn, another problem occurred where the platform that actually points the cameras back and forth was being operated at a very high rate for many minutes, and the lubrication oil flew out to the outer rim of the gears, and the gears all seized. And we thought we had a stuck platform. And over several weeks, it was finally rejuvenated, and ever since it's been handled with kid gloves, no more high-rate slewing. Everything's been very, very carefully planned with anything to do with that platform.
And then you've been fortuitous in that the planets have been helpful in lining up. I mean,
yeah, the entire mission could not occur in this particular way unless the planets were aligned the way they are.
And they gave little gravity boosts as the Voyager flew by.
The very
to go to the next
essential
planet.
key of this mission is that in the early 60s, a technique was developed whereby we could calculate what these planets would do to the spacecraft, any spacecraft. And it turns out you can now access the entire solar system if you're willing to wait long enough, and you have a spacecraft that will last long enough, as long as you
over
can target.
150 years for this, right?
That's right, and this particular alignment won't line up again for another 165 years or so. But we could do the same sequence, Earth, Jupiter, Saturn, Uranus, Neptune, if we were willing to take a completely different trajectory, but that would most likely take longer because this is kind of an optimum one.
I want to jump a little bit to your one of the jobs that's uniquely yours is deciding what Voyager does after it leaves Neptune, right? I mean, is it going someplace else?
Yeah, there's a plan. It seems to be operating so well along with its companion Voyager 1 that we expect with the resources on board that we can go until about the year 2015, which is another 25 years.
But that's going to be outside of the solar system, right?
Right. What we're hoping is there's 4 spacecraft that have enough energy to leave the sun, Voyager 1 and 2, Pioneer 10 and 11, and they're all going in a nice spread out fashion away from the sun. And we hope to, using those as a system after this encounter, detect when the spacecraft go through the boundary between the sun's solar wind and the incoming solar wind from all the other stars around us. And that's called the heliopause. We expect that might be between 5 and 10, 15 years from now. It should be something like a shock wave, like we expect to see tomorrow or maybe late tonight at Neptune.
So what can you learn from that? Is that just a nice place to be, or is it?
Well, it's mostly it's not an imaging mission like we're seeing now, where
so no pictures are coming.
No
back.
pictures. We won't use the imaging like that. It's mostly what we call a fields, particles, and waves mission. It's of high interest to the people that study the solar magnetic field, because we see structures we think are like this on other stars, and we'd like to know how big ours is so we have a calibration point.
Now, theoretically, I mean, I've been reading that Voyager 2 is headed towards Sirius the dog star. In 80,000 years it could get there.
Yeah, that's right.
I mean, is there any thought that there's something interesting along the way that it might see? If something shows up for its cameras to take a picture of it, could it see it and send it back? Nothing.
No, in fact, we couldn't even image Pluto right now, which is comparatively close. And we've already calculated we could never image Pluto during the Voyager mission. It's so small. So anything like an asteroid way out there would not be seen. It's mostly just to go through this heliopause is the primary mission.
And so you'll be listening to Voyager for years and years and years?
Yeah, and we'll have sort of a backseat to everybody else like Magellan and Galileo and Cassini and Kraft, the big projects at the lab coming up. But we will get some coverage enough to fill in data for the next 25 years. And it should be relatively dull compared to this mission, but it should be exciting for some specialized fields of research.
Fascinating. Thank you very, very much, Rex Ridenauer, a mission planner here at JPL.
Eating was a real pleasure. Of course, it's impossible to knock your milk off the table up there, kiddos. There's no way to get in trouble with Mom. You just leave things float around, and when you want them, you just grab them out of thin air, and you can eat standing on your head or however you please.
There's our guru here. This is the story during his demonstrating what happens if you ever drop a cat. It always ends up on its 4 feet, no matter what attitude. And
we've had a lot of discussions about how this works, how you can move around.
He's
like
not
that.
shoveling the air. It's actually he's.
You want me to do it here?
The one on the right, of course, is a magnet, and the one on the left is just a pencil, and we had no idea they were going to decide to mate.
We're still waiting the results.
Gordo practicing his landing technique, get ready for re-entry. Looks like we're lost in space there.
That's right. Well, we get up in the morning and, you know, brush our teeth and comb our hair and the rest of that stuff here.
Some of the crew equipment we had was limited, so we had to share it.
You're not allowed to laugh.
This sequence we call Hair Wars. As you might expect, the commander won.
Of course. I'm not dumb enough to get the hairbrush away from the commander.
This next scene is not staged. This is a real teleprinter message.
We set a new record on this flight for the amount of teleprinter messages sent up. Every single rev on the night side, they send up a new detailed plan for the scientists here to accomplish on the next solar pass. And that was an actual message, all full of fine print, that fortunately for me, all I had to do is take it up to the upper deck and pass it out to the people who really had to read it.
We recorded a new space first on this flight. We ran out of teleprinter paper after 5.5 days. It's the first time this happened. And Story Musgrave changed out the paper roll in space for the first time.
But the hairbrush one wasn't staged either.
Some of the great moments from manned space flight, not necessarily what's going on at the Voyager 2 at the moment. As far as we know, nobody is aboard. But
We just wanted to wake folks up.
We wanted to wake people up, yes. You're watching Neptune All Night, that is being broadcast throughout the country here from WHYY in Philadelphia. And we have as a guest here a member of the radio and television and filmmaking community who's had a long and distinguished career. He first made his appearance at the Century of Progress exposition in 1933, portraying the young Thomas Edison in the pageant of electricity. He soon moved on to roles in local radio shows and became a well-known performer by the age of 17. And he's traveled around, been involved in science fiction radio. And I'd like to welcome here to Neptune All Night, George Tirebiter. Thank you very much. I understand you're the only science fiction filmmaker ever to stage a movie on Neptune. Why Neptune, George?
Well, Sedge, it's wonderful to be with you on this historic occasion. It's not much easier to get my voice to you from Washington State than it is to get the signals from Neptune, but I'm pleased to discuss this old film of mine with you. This was during the early 1950s. There was a great cycle of those classic movies like Destination Moon and Invaders from Mars, you know, and so there was a tremendous rush to bring out these alien space travel movies. The plots were, you know, we go there or they come here, pretty much. That was it. And they'd used up the moon pretty well. They had the big sound stage set over at Paranoid Pictures. They did those lunar landings with Mr. Armstrong there, I think, years later. It looked just like it anyway. But, well, I did Mars Is Ours. I did that as a serial for Captain Equinox. He was sort of our Commando Cody, a hero type. He wore a safari suit, a football helmet, dark glasses, you know. And he had a reverse twist on that War of the Worlds idea. We go get them before they come and get us. It was a kind of a Cold War science fiction movie. That was very good. And we had Catwomen of Venus, sort of a sleazy jungle movie. You know, Venus was supposed to be covered with a rainforest. That's what all those pulp writers we hired at a penny a word, they told us that. Republic did, let me think, they did Radar Zombies. The Radar Zombies were from the cold side of Mercury. They wore ski parkas with little flashlights for their eyes. And, well, let's see, there was Atomic Invaders from Planet X. There was Texas Rangers versus the Ring People from Saturn. But we were running very low on planets, Sedge. That was how I came to Neptune.
Well, what about Pluto?
Oh, Pluto. Well, Walt Disney had a copyright on Pluto. Who'd come to see they came from Pluto, anyway? It sounds like a cartoon about singing ticks. Well, that left Neptune and Jupiter. And, of course, that other planet that no one can pronounce the name of. I wouldn't even want to say it, not
No,
now.
you don't even want to try to
TV.
mispronounce it, no.
No, frankly, said, I think we'd have been a lot better off if they'd called that planet Herschel. Doesn't that have a nice ring to it? Mars, Venus, Jupiter, Saturn, Herschel, Neptune, and Pluto. Astrologers would have a good time with that, too, I think.
Well,
your Herschel is a retrograde in the 4th house, which means to expect a surprise visit from your brother-in-law, I suppose, or something like that. Anyway...
well, come on, George.
Oh, yes, gas music from Jupiter. That was a musical from Metro. They made it in true color. It wasn't, of course. It was seafoam green. And red, the color of the stuffing in jelly donuts, They showed it all the worst movie marathons. Well, so it was up to me, Sedge. I was blacklisted. I was writing under an assumed name, George Tirebiter, at the smallest and most pathetic studio in Culver City. What choice did I have? None. So I wrote 13 episodes of Nomads from Neptune, one of the last serials ever made.
Well, what did Neptune look like in your movie, George? We're seeing... pictures now. What did it look like in your film?
Well, oddly enough, I'm seeing these same pictures, and it looked quite similar to what we're seeing now. A big, fuzzy, blue ball. Wait a minute. Maybe that's Pete Rose I'm looking at. No, that's Triton. I've been watching a lot of television today. Well, we had one of those arousing science fiction magazine cover artists did paintings for us, and he just came up with this blue ball. It was quite nice. Also, the female costumes. They were very nice, too. But the trick was, now, let me tell you this. We knew that Triton, this moon, it went backward in its orbit. So I landed Commander Mark Time, official representative of the Circumsolar Federation, on Triton, which had been going backward for so long that it worked just like a time machine. Triton flung Mark forward into the past.
Very clever plotting. Was there an alien monster in your film?
Oh,
George?
Alien monsters all over the place. But we had very small budget for those kinds of things. This was from this movie that expression that you may have heard, worser than a Neptunian Nessie, came from. The Nessie was a sort of a methane sea monster that leaped in and out of those gas bergs up there on Triton. Made entirely out of cheesecloth dipped in cream of wheat. Not much money for special effects.
Well, I haven't seen Nomads from Neptune, George. I assume it's in an archive somewhere nowadays?
Oh, well, here's the end of the story, Sedge. It's lost forever. The entire archive of master prints from Monarch Studios destroyed, completely destroyed by fire. A raging brush fire on Mulholland Drive burned to the ground the great structure which housed these priceless prints. It was a two-car garage belonging to an old-time director of those B-movies, a fellow named Spencer Bennett. No, I'm afraid that Nomads from Neptune was released only once in 1955 on a double bill with Arizona Serenade. It starred Tim McCoy and, I don't know, either Abbott and Costello or Ronnie Reagan. It may be both of them, I don't know.
Well, George, we look forward also to hearing more of this in your biography when it comes out. I want to thank you for joining us, Hollywood legend George Tirebiter.
Well, thank you, Sedge, and a fond farewell to that little Voyager wherever it goes now.
George Tirebiter and his longtime associate David Osmond are frequent hosts for public radio programs, including radio movies. From The Bride and the Sunday Show, Osmond's most recent interplanetary adventure is The War of the Worlds' 50th anniversary production starring Jason Robards, which he directed. It'll be once again heard over many public radio stations this coming Halloween. We have time to take a telephone call. Somebody has called in from across the country watching tonight, and then we'll be going back to the Jet Propulsion Laboratory about 5 minutes early, so we'll advise the affiliates. This is Charles. Welcome. Where are you calling from?
Cambridge, Massachusetts.
Great. Thanks for calling in tonight.
Yes, hi. You've been talking a little bit about Pluto and the Grand Tour, and I have a history question. I was wondering whether or not Voyager 1 was originally planning to go to Pluto before it was diverted to Titan, and I remember hearing a rumor about that a long time ago, and I thought maybe your NASA specialist could field that question.
And our NASA specialist is Jesko van Puttkamer. No, not to my knowledge. I think that Titan was considered from the beginning to be the more interesting target, and it was either Titan or Pluto. You're right in that. But originally, speaking from history, in 1965, we were talking about a grand tour
with only one spacecraft, but going through all the planets. And that was turned down by Congress because of the cost. And instead of having one big grand tour, we cut it into two, what we called mini tours. And that is what Voyager 1 and Voyager 2 then turned out to be.
Mike Weilbacher, you've been watching some of the pictures that have been going by on the screen here. Is it giving you any sort of a feeling of reminiscence of what Voyager has seen over the past dozen years?
It's wondrous what it has shown us from the ring structure of Saturn that just passed by to Jupiter, to all the moons that it's found, to the new moons that it's still finding. Two new moons were just found today, in fact. N4, N5. So,
and we'll be back here with our panel of experts following the next Voyager update from the Jet Propulsion Laboratory. And we hope that you'll stay with us as we go till dawn here with pictures from space and voices from Earth. You're watching live across the country tonight, Neptune All Night.
This special presentation of Neptune All Night, the Voyager 2 flyby of Neptune, is made possible with the financial support of the Office of the President and the Division of Public Affairs of the Florida State University.
Good evening, and welcome to the 12 o'clock edition of Voyager Update. I'm your host, Rich Terrell, and we're starting a little bit early today because we have a special event about to occur. With us is Ed Stone, Voyager project scientist, and Don Gurnett, principal investigator of the plasma wave investigation, to comment on the ring plane crossing. Gentlemen, thanks for being here, and let's go right into the data because we're about to have the ring plane crossing.
Right, we're just about to cross the ring plane, and what I'll show you here is the spectrogram from the plasma wave investigation. And this shows a frequency along this axis over here, and this is time along this axis. And the data that we're receiving right now is being plotted here, and as time advances, the plot shifts over this direction. So the very most recent data is right there. Now, what we're interested here are dust impacts. The plasma wave investigation, although it's designed to detect plasma waves, can also detect dust impacts as we go across the ring plane. In fact, we started seeing evidence of dust impacts almost 40 minutes ago. These little pulses here are probably dust impacts, and you can see as we're approaching the ring plane crossing, this red region is showing very intense dust impacts.
And we're about 2 minutes from ring plane crossing, and does this very clearly we're going through a region of unexplored territory, and we understand that there are rings, and they're irregular, and they're very poorly understood. So does this pose a danger to the spacecraft going through the ring plane? Ed? Well,
we don't think so. If it's just dust, that is micron-sized, micrometer-sized particles, it will cause a lot of signal for Don's instrument, but it won't hurt the spacecraft at all. If there are BBs, on the other hand, that could be a very serious problem. But there's no real reason to believe that there are any BBs orbiting out where we're flying through the ring plane.
It doesn't take a large particle. A grain of sand can cause a lot of damage going in 15 miles a second.
From our previous experience, these kind of dust impacts are produced by micron-sized particles, but notice the intensity and rate is increasing very rapidly. Red is the very high intensity. We should hold our breath here.
Getting kind of exciting.
How close are we to ring plane crossing?
We're about less than a minute from the official time of ring plane crossing, and there could be some fluctuation within half a minute or so of that because of uncertainty in the pole.
Just about 30 seconds, although there is a slight data transmission time here.
Now, well, I guess we shouldn't get alarmed because the data is going to stop about 2 minutes after ring plane crossing, and that's intentional.
At 2 minutes after midnight Pacific time, the modulation is turned off in the transmitter. And that's to start the radio science occultation.
The occultation, which has actually already occurred, but the data from that is now on its way to Earth. And,
right. Whatever has happened 4 hours and 6 minutes.
That's right. So either we've got to a viable spacecraft taking pictures, or
we're seeing a lot of dust impacts here. The spectrum is going all the way up to almost 10 kilohertz now.
Well, Don, what was the, you saw dust at both, as I recall, both at Saturn and at Uranus during ring plane crossing.
This is looking, to me, very comparable to what we saw at Saturn. Because at Saturn, we were seeing noise going all the way up to about 30 kilohertz in our...
Saturn, we flew very close to the G ring.
Yes,
right. Very tenuous ring around Saturn. Somewhat unintentionally.
Maybe we should have changed the color scale on our spectrogram to allow higher intensities.
Looks like you need more colors.
More dynamic range.
Just before we started, this whole area was completely devoid of any features. There was all solid blue.
Right. An hour ago, there were no evidence of any impacts at all.
Okay, we should be at ring plane crossing or just after ring plane crossing, so hopefully that data will start to decrease on the other side, indicating we've gone through successfully.
In another about 2 minutes, the modulation will be turned off the transmitter, and we'll lose the low rate data here.
Now, you do have some wider band data being recorded on the spacecraft at this time, isn't that right?
Yes.
So after, when that data is played back, you'll be able to do a better analysis of exactly what the rate of impacts was at this time.
That's right. We transmit the waveform that's being detected by the antenna. It's transmitted back to the ground. Right now it's being recorded in the tape recorder, and that won't be played out till played back till somewhat later this morning.
Now, what kind of impact rate do you think that probably corresponds to, given your experience?
I would think it'd be something well over 100 impacts per second. At Saturn, we had 500 impacts per second, and at Uranus, it was about 50.
Okay, so substantially more material than Uranus, and maybe not as much as Saturn.
You're asking me to make guesses with rather little information. We really need the wideband waveform data to analyze this. But it's certainly a dramatic effect on our low rate data.
Right. It looks like perhaps the data has begun to turn down, and
yes,
we may not be receiving any more now. I think we're approaching the time when we turn off the transmitter.
In fact, you can see that peak right there. That is probably exactly the ring plane crossing, where it goes up and reaches a peak. It looks like it went down.
Yeah.
So, and we're still receiving data, right?
A sigh of relief.
Right.
Oh, there we go. That's the data, end of the data.
Okay, we lost the signal from the space.
Intentionally.
Intentionally.
Right. Okay, right. So a big cheer.
Big cheer.
Champagne corks are
Looks
probably
like
popping
we're through the ring
all lab, and we've made the first hurdle. Ed, you've always been the voice of serenity and calmness and optimism. Clear your soul. Was there any doubt at all, any apprehension?
Not really, no. I really felt that we had a very low risk trajectory chosen because we had really picked it well outside the known ring arcs, and we haven't discovered anything on our way in that would suggest that there are any ring arcs out there. And of course, this is also the time when the radiation environment is at its maximum, passing through the ring plane. And but again, I really didn't think that the radiation environment at Neptune could be as severe as the one we already experienced at Jupiter. And I suspect that, although I don't know what the results are yet, that we'll find that indeed there was a radiation environment, but not overly intense.
I know you have to go back to other duties around the lab, but before you do leave, what do you anticipate about tomorrow? We had Larry Soderblom here earlier, just about jumping out of his chair over images of Triton.
Well,
you've seen them.
Yes, I can't wait until 3:30. I think the Triton looks unlike anything we have seen before. It's just an incredible place, and the images, the high-resolution images with kilometer resolution that we'll see in several hours, I think will just be amazing.
You've got me jumping out of my seat to look at those Triton images. In the meantime, we've got an animation. Well, I'd like to thank you for being here. And in the meantime, we have an animation to show us a little bit about what ring plane crossing is like. So if we can roll the tape, and here we have the spacecraft coming up on ring plane crossing. You can see the ring arcs defining the ring plane. And you'll see the entire system flatten out. That's when we got the maximum of dust impacts in the plasma wave experiment. Ring plane crossing is right now. That's where the data we're receiving is from the spacecraft. However, the spacecraft is, in a sense, 4 hours in the future. And the spacecraft has already gone behind the planet, cutting off the signal from the Earth and the Sun, going into occultation, measuring the temperatures and pressures of the atmosphere. It has come out of occultation about 15 minutes ago, and will be turning its cameras to look at the moon Triton, and we'll be receiving those data in about another 3.5 hours. So,
yes, right.
We've gotten successful data from Voyager on ring plane crossing. What does it all mean? What are we going to learn from this, and what have we learned from other encounters?
Okay, maybe we could take a little time to just talk about the how we detect the dust impacts. If you could hand me the model over there, I would
Sure.
Talk about how our instrument operates. The plasma wave investigation uses these antennas, 2 antennas, to detect waves in the plasma. That's its primary purpose. These antennas are about 30 feet long. And the way we detect dust impacts, actually, when Voyager was launched, we didn't anticipate that this would be possible. But when we flew through the ring plane at Saturn, we detected an effect very similar to what we've just seen at Neptune. And because of the very high velocity of the spacecraft, at Neptune it's about 15 miles a second. If there's a small particle in the way and the spacecraft runs into it, we find that it makes essentially a small explosion when it hits the surface of the spacecraft. Now, by small particle, I'm talking about particles that are micrometer diameter.
So the particles that make up smoke.
These are like particles in smoke, so they're really extremely small. And if we could switch to this illustration over here, I'll try to sort of indicate what happens. When the particle hits the surface of the spacecraft...
let me put that up on the...
Okay, when the particle hits the surface of the spacecraft here, it essentially explodes, and the temperature is so high that it vaporizes and ionizes the material that's in the particle and produces a little pulse of plasma, consisting of charged particles. And these charged particles then fly out and get detected by our antenna. And so our instrument detects an electrical pulse on the antenna. And that pulse produces a pulse shape that typically lasts about a millisecond. And as we discussed earlier, that waveform is transmitted back to the ground. So we can actually, you could take the waveform and record it on a tape recorder, and then play it back and listen to it. And at the Uranus ring plane crossing, we did that, and I have, in fact, a tape recording of the ring plane crossing at Uranus. And you can hear the impacts. This is not exactly a pleasant sound, because you can hear the kind of a hailstorm effect. Let me start the recording, and this is the ring plane crossing at Uranus.
Like being in a hailstorm.
Like being in a house with a tin roof with all kinds of hailstones falling on the house. Now, the reason the spacecraft is not damaged is that these particles are very, very small. If they were even a factor of 10 or 100 bigger, they could be potentially damaging. So, fortunately, they were not. It appears that it was very similar to Saturn and Uranus.
Was Saturn the first time you detected these kinds of
Yes.
things?
And
by surprise?
By surprise. We hadn't realized a plasma wave receiver like this could be a particle detector. But, in fact, it's a very sensitive particle detector because it's the entire spacecraft that is the sounding board.
Right.
And we and many of our colleagues spent several months trying to understand the details of this physical process of how a dust particle hitting a spacecraft could cause an electrical effect like that. But we think we have this pretty well understood, and we can make now estimates of the size of the particle, and especially the rate and density.
So not only can you tell a little bit about those particle properties, but also a little bit about the geometry of the ring itself.
Yes, right. We can tell.
The width of the peak tells a little bit about the thickness of the ring material.
Right, just like at Neptune. Why don't we get the plot that we just received from Neptune? From the width of the, so this width right here, we can get a measure of the thickness of the ring plane for these small particles. Understand it doesn't mean we're measuring larger particles, which might be detected optically, for example.
Typically, those particles are distributed over a fairly large spatial extent, much larger than, for instance, the ring plane of Saturn.
That's right. These are typically
or
several thousand kilometer thickness for these very small particles.
So a very broad sheet of material.
Very broad sheet of material. It is presumed that these very small particles are produced by bombardment of larger particles, micrometeorite impacts that spew off debris, very small particles, and that's what we're detecting here.
So we may be seeing evidence of Voyager running into debris off some of the newly discovered moons.
That seems very,
inside and outside the
very
point
likely.
ring.
Yes.
Okay.
So it looks like that part of our investigation was a big success, and we'll have plenty of data to work with here and try to analyze.
Okay. Are there other things that that we might learn from the plasma wave instrument?
We're all very excited. If we switch back to the screen over here, there are many other types of, like these, this green area up here are radio emissions that we've been detecting for some time, and we've seen a number of exciting things. Earlier today we detected the bow shock crossing.
Right.
When we went across the shock, there was a big burst of plasma wave noise, which we were expecting, and occurred just about like we expected, although we couldn't predict the exact time.
Right. Are these the same frequencies that that one has in their car radio, for instance?
The frequencies that we detect are much lower frequencies than are detected by a car radio. Our lowest frequency is 10 hertz, and the highest frequency is 56 kilohertz. So a good part of the range of frequencies that we detect are the same kinds of frequencies we're talking with, the audio frequency range.
That's why you can directly put these things into an audio tape and actually listen to what's going on.
Right. There's no frequency translation involved, as in a car radio. When you tune into a radio station, you're tuning the receiver to a high frequency, maybe 600 kilohertz, and then you hear the sound. This has no frequency conversion.
Great.
These are the exact. It's just like you were riding on the spacecraft, and you had earphones on, and you were listening to the exact signals detected by the antenna.
So quite literally, we're hearing the sounds of the ring plane crossing and the encounter with Neptune.
Yes, and tomorrow, after the tape recordings are transmitted back, the wideband data where we can actually listen to them, later tomorrow we should be able to listen to these impacts.
Fantastic. Well, thank you very much for joining us, and
thank you.
We're all cheering the success of the encounter. At 12 o'clock p.m. Pacific Daylight Time, the Voyager was 196,000 kilometers or 121,000 miles above the swirling cloud tops of Neptune. It's speeding away from the planet at a velocity of 41,848 miles per hour. We'll have another update at 1 a.m. Pacific Daylight Time. I want to thank you very much. This is Rich Terrell for Voyager Updates.
Oitenis poteste Tirebiter.
Des voix, des nuages, des mers, par-delà le soleil, par-delà les éthers.
Paz e felicidade a todos.
各位好嘛，祝各位
Tu te vois avec
健康
agilité.
快樂。
Et comme un bon nageur qui se pâme dans l'ombre, tu sillonnes gaiement l'immensité profonde.
สวัสดีค่ะสหายในธรณีโพ้นพวกเราในธรณีนี้
हमारे
ขอส่ง
दोस्त जो कला में बसते हैं उनके लिए दोस्ती और खैर सगाली
النجوم يا ليت يجمعنا الزمان.
हमारी दिली ख्वाहिश है कि सारी दुनिया में अमन रहे
Mae Lagnia.
जिंदगी के हर
Liebe Freunde, Eis. Als Vorsitzender des Denkmalraumes
sampai bertemu lagi di lain waktu.
Österreich, das freut mich, Ihnen auf diesem Wege
Hello from the children of planet Earth.
With pictures from space and voices from Earth, this is Neptune All Night.
And we're continuing live here from WHYY in Philadelphia with the images coming to you from the Jet Propulsion Laboratory. And this is Neptune All Night. My name is Sedge Thompson, and sitting around a table here, a round table very much like a late-night poker game here tonight. We have Jesko von Puttkamer from NASA, strategic planner from the Office of Spaceflight, the science fiction writer and author of Pantera, Judy Moffett, Jack Horkheimer, star hustler and director of the Miami Space Transit Planetarium, who once went through a vigil couple of vigils when Voyager 1 and Pioneer passed Saturn.
Right.
Also here from the Franklin Institute Science Museum here in Philadelphia are Joyce Town, Mike Weilbacher, and Derek Pitts. And we'll also be taking calls from you who are watching throughout the country this evening at 1-800-FLYOVER. So figure those letters out on your dial and you'll be able to reach us here and ask our panel of experts questions. Also in this hour, we'll have some interviews from some people at the Jet Propulsion Laboratory. And first of all, Jessica, could you explain why it is that the Voyager 2 is
Yes, I
not
think
sending anything
first
at the
we should
moment?
say that the picture you see on your screen right now is not real time. It is you know, several hours past. It's a playback picture here from the studio, because right now Voyager's transmitter, Voyager's telemetry has been turned off, starting at 3 a.m. For the next 3 hours. It's not just because Voyager is behind Neptune, but because all the power on board needed to be channeled into a pure radio signal without modulation. That pure radio signal in X-band and S-band is used as a probe to probe the atmosphere of Neptune. The high-gain antenna is continues to be pointed toward Earth, and that pure radio tone penetrates the fringes of the Neptune atmosphere and reaches Earth and is changed by the atmospheric parameters. And scientists can read a lot about the Neptune atmosphere from those changes in the radio tone. And so for the duration of the passage, that tone is being transmitted, and that takes about 3 hours. So during that time, we cannot use the radio for telemetry, which means that all the onboard measurements, which will continue, of course, are being stored on that tape recorder. There's only one tape recorder on board, and of course everyone is praying that nothing happens to it.
As it moves through the ring plane.
But then in 3 hours from now, we'll pick it up again, and then we'll get to see the most fantastic pictures of Triton, which everyone is, of course, waiting for with bated breath.
Now, I'd like to ask Judy Moffat, a science fiction writer here with us. We've been seeing a lot of images of the planet Neptune and all the other planets in the past years of the Voyager expeditions. It's a swirling planet of gases. It's a lovely blue. There's a great sort of magic that comes from seeing these images. Is this sort of force of vision, in fact, taking anything away from science fiction writers?
Taking anything away? No.
Does it make you even wonder more?
Science fiction writers feel the same sort of emotional response to these images that everyone feels. And in fact, it's wonderful, tremendously exciting to see what the planets and the satellites actually are, to see the turbulence of the atmosphere, to see volcanoes erupting. Makes it much better and easier for us to create worlds and systems which have a feel of being real. But the effect it's had on science fiction writers to see what the planets in our own system are really like is that it's become immensely more difficult, maybe even impossible, to locate a certain kind of story on, for instance, Mars or Venus, which were the old standby favorites of the Golden Age writers when they told a story about our own system, because they thought that Mars and Venus were very different from the way it's turned out that they actually are. They thought that Venus was a wet, warm, swampy world with maybe dinosaurs, and that it would be relatively easy to establish a human presence there because it had breathable atmosphere. They thought that Mars, well, Robert Heinlein wrote a novel called The Red Planet, which was published in 1949, in which people lived in a habitat which was pressurized and sealed, but it was very easy to go in and out, and wander around the surface at will, go on long ice skating trips on the canals. And now, of course, we know that there are no canals, that establishing a human presence on Mars would be very much more difficult, enormously more expensive than anybody ever dreamed. So if you want to tell that kind of story with aliens and people relating comfortably on a world that's a good deal like Earth, you've got to make up your own.
You feel that in the golden days of science fiction drew its power from sheer distance. You know, there was magic and sense of wonder just in distance. Before science fiction, there was a sense of wonder in tales about the dark continent, about Africa, about exploring, and so science fiction then started telling about long distances in space. Do you feel that today, with Voyagers traveling billions of miles and people getting used to that, it's going to be impossible for science fiction writers to draw on that power, that they have to invoke something else?
Oh no. Even as the Voyager space probe, for instance, takes away some of the mystery about the rest of our system, it creates these magnificent images, which are so much greater and better than anyone has really imagined, that I don't think anything is lost any more than, that there's a balance between.
Do you think that Voyager, that trip, can stimulate you to write a science fiction story about it?
Me?
Yeah. Yeah.
Well, conceivably, I think if I were going to write a science fiction story about Voyager, it would be about some alien race intercepting the probe.
Which has already happened. In fact, that was Star Trek, the motion picture. Machine aliens took over Voyager 6, which of course it doesn't exist yet, and embellished it a whole lot and sent it back to Earth to find its creator. It was coming back to report. That was...
I was a science advisor for that movie.
Were you really?
Yes.
Were you? And what did you, Jessica, suggest about Voyager 6?
Well, first of all, I insisted that the originator, namely the National Aeronautics and Space Administration, be given a proper plug in the movie. that was my payment for being a science advisor. And we insisted on, in that first Star Trek motion picture, that we depicted a future which was as realistic as we tried to make it from our perspective. The later Star Trek motion pictures just tried to be fun and shoot 'em ups. But with that first one, directed by Bob Weiss, we were very serious about making an adult, a grown-up type science fiction picture, like Kubrick's 2001. But that Voyager story can inspire many other stories. Not just being found by machine beings. There must be more poetic ways of spinning that tale.
There was actually some discussion among scientists for a while about putting plaques on these vehicles. The fear that perhaps an alien culture would find, therefore, directions to get back to planet Earth.
We have a plaque each on Pioneer 10 and 11 showing exactly where these probes came from. And there were a lot of people in the country who told us we shouldn't have done that.
Except we've been setting out radio and television signals for years, which would be any clear indication exactly where planet Earth is. And the disc that's on there with the Earth sounds was also put on as an afterthought almost. It was not part of the original
It was whipped up in pretty short time. And you may have noticed on an earlier picture here on the screen that the Voyagers don't just include a disc, but also a description of how to build a record player.
A record player, right. And there's a stylus
with an old-fashioned pickup. We didn't have any compact discs then, 12 years ago, so we are sending an old-fashioned long-play record.
I talked with Timothy Ferris about why they chose a record and asked him about the compact disc, and actually the material, the copper, is far more durable. He says, we have no idea how long a compact disc will last. The copper, they believe, will be last for.
Well, there's something very interesting about,
yeah.
There's something very interesting, Serge, about a machine, a disc that is played with a stylus, and they include the stylus, because that is the records, the long-playing records, represents a complete change in technology. Once you go to a CD, the entire technology takes a quantum step into the future. A primitive person, let us just suppose for a scenario that the Voyager spacecraft floated gently down on the shores of a distant planet millions of years from now. A relatively primitive but intelligent creature could find that stylus, or even take a fingernail and put it in the groove, and if you run your finger across it, you'd hear a sound. Using that stylus, a relatively intelligent person could figure out to take the stylus and trace the grooves with it. If you do that, you would get sounds. A compact disc is impossible to play without the kind of playback equipment. And as soon as we hit compact discs, our whole technology changed. As a matter of fact, I kind of date personally the change in technology of this whole planet right from compact discs, because if anybody found a compact disc that had no idea what it was, they'd never be able to figure it out. They just couldn't figure it out. A stylus and a record, that is a wonderful, it's a real earmark of where our civilization has gone in the past 15 years.
Well, we could have included directions how to use a compact disc.
But unless you have a player and you have so you'd have to have electricity.
And then the battery.
With it, just take a stylus and run the stylus around a little record.
Yeah.
Bang, that's it.
You know, it's an amazing gesture of hope and of speculation that somebody out of the million years before it gets far out, that somebody might actually hear from it. There was a quick observation that Lauren Isley made about the idea of that perhaps a probe was sent to this planet, and it landed in the swamps before before coal had begun to form, and that perhaps there was some metal probe sending out its own messages from another civilization, and there was a reptile slithering over it as its batteries ran down. You're watching and listening to Neptune All Night here on PBS, coming to you from WHYY in Philadelphia, with scenes recorded earlier from the Jet Propulsion Laboratory, and that was earlier this afternoon of Triton, right?
That's Triton earlier this afternoon, right? Because right now there aren't any pictures coming in from Voyager.
Those are about 9 hours old, it looks like.
Yeah.
9 hours old. Joycetown, could you describe the size of the Voyager spacecraft?
Sure, this is a pretty amazing machine. The middle of it has kind of a round frame with lots of louvers on it, and attached to that is a very big parabolic antenna. You call it maybe a dish antenna that always points towards Earth, and that's kind of how we get information and data and pictures when pictures are being sent. Right now, no pictures are being sent live. It'll be just a few more hours before we get some more pictures in. But there's also some appendages sticking off of this craft, some very long things. One of them is very important to us today. It's called the science boom, and it has about 9 science instruments on it. And it has the TV cameras and cosmic ray experiments, photopolarimeter, infrared interferometer that we were looking at some experiments from earlier. And over on the other side of the craft is a very long magnetometer that we'll be using later on. And another area is where the generators for electricity are located that have the plutonium pellets in them.
Thank you, Joyce. Describing the Voyager 2, a spacecraft that's lasted far longer than its manufacturers thought possible, and who knows, may last for 1 million years.
Like my Chevy.
Like your old Chevy, huh?
Also been lasting 27 years.
And we'll be back with more commentary from our panel of experts. We'll take some calls from you, have some interviews, and continue taking a look at what is far away from us tonight. With pictures from space and voices from Earth, this is Neptune All Night. Welcome back to Neptune All Night, live from WHYY in Philadelphia, and with images coming to you from just outside the planet Neptune, that gaseous planet that has been astonishing scientists and amateurs with the great knowledge and information we're gleaning from it, things that were not known until tonight, as we're watching this evening. Mike Weilbacher is known as Mr. Science at the Franklin Institute and runs a radio show for kids, often has quiz questions. We're going to take some calls from around the country, and who knows, maybe one of them will actually answer one of your trivia questions tonight.
In fact, we had asked earlier how many Neptune years had passed since James Monroe was president in 1824. The answer was only 1. 1824 was 165 years ago, or roughly the orbit, one revolution of Neptune around the sun. Another quick question. let's see, compared to, okay, here we are. If one weighs 200 pounds here on Earth.
Are you speaking of yourself or somebody else?
I roughly weigh 200 pounds here on Earth. So what would I weigh if I stood on the surface of Neptune, if there was a surface on Neptune? But anyway, if one weighs 200 pounds on Earth, what would one weigh then on Neptune?
All right.
There's a challenge.
What would you weigh on Neptune if you could stand on Neptune?
If you could stand there.
And not get in the way of those storms. All right. And the telephone number is an 800 number, 1-800-FLY-OVER. And do we have a phone call? This is Kevin from Cincinnati, I believe. Welcome.
Hello.
Hello. Thanks for holding. You have a question here for our guest.
Yes, I do. I've always been a tremendous fan of, you know, things that involve space ever since I was a young boy, you know. And we didn't have the wherewithal at that time to get out where we are now. After Voyager's latest triumph, I've got a question. We haven't launched a probe, an interplanetary probe, since the 70s. And there seems to be no governmental priority placed on that, or any scientific information finding missions. We've got this tremendous lag there. You know, if we launched one tomorrow, and obviously we don't have any built at this point, we wouldn't be where we are with the Neptune probe for, 15 years. I was wondering, with the shuttle being used for primarily military purposes at this point, Galileo's been pushed back repeatedly, even before the Challenger disaster. Is there any perception among your panel of any change in the attitudes the present administration's taking towards genuine information-finding probes into space?
We'll go to Mike Weilbacher from the Franklin Institute.
One of the things that's worth pointing out is the cost of manned versus unmanned exploration. Sending humans into space is often seen as sexier, or at least it's great PR for NASA, and it's a great thing to do. The Neptune project has cost roughly $865 million or thereabouts in the last 12 years, which is about the cost of the space shuttle in 1 year of operation. Not that we shouldn't be sending humans into space, but there are efficiencies to sending unmanned probes and safety factors as well. But I think one thing to correct is that the Magellan space probe was sent by the shuttle. The shuttle has done this for us, so Magellan is on its way to Venus, I believe, as we speak. So we are back in the business of launching space probes. We're also going to be setting up the Hubble Space Telescope later on this year.
Let me also say something. I'm from the shuttle office. It is not a fact that the shuttle launches primarily military payloads. That is just totally wrong. We have been launching about 30% of our payloads military, and that number has gone down recently. And next year we won't be flying any military payloads anymore. The military has turned away from the shuttle since the Challenger. So let's stop, kind of believing that myth that the military are predominantly using the shuttle.
So the recent flight that launched a top secret
that was one of the last ones, and it's just one of those 30% of military flights. So it's a minority, the military flights. Also, we are going to launch Galileo in October 12th. We're launching Hubble Space Telescope next March, 1990. We're launching the Ulysses solar probe in October next year. The Mars Observer in 1992. The Comet Rendezvous asteroid flyby in 1995. The Cassini Saturn Titan mission in 1996. So you see, there are going to be very, very exciting years for space science ahead of us, and even this year and next year we'll already have some highlights in that area.
Thank you, Jessica. We're going to Rick from Dallas.
Hello there.
Good evening.
Yeah, I have some suggestions for the moons and then a question.
Oh, all right.
I think they ought to be named after people who've died in exploration, or failing that, a more scientific name such as Moon Number 1, Moon Number 2, and Moon C. My question is, if the probe still is transmitting in 2025, how long will it take for the signal to get back to Earth? And a stab at the trivia question. Probably with Neptune being larger mass than Earth, you probably weigh maybe 200 tons versus 200 pounds here on Earth. Thank you very much.
All right, thank you, Rick in Dallas. Okay, Mike, how much would you weigh?
I've seen various estimates for the gravity of Neptune. The ratio, let's assume it's 1 to 1.23. So it's a little more than the gravity here on Earth. So you'd weigh about 246 pounds.
246, and not 2 tons.
Not
okay.
2 tons.
All right, and the other question was how long would it take a signal to reach Earth from the year 2025? And Jessica von Puttkammer is actually...
well, I figure that in 2025 we'll be about 120 to 130 AUs away from Earth times 8 minutes. So that would then, am I right? Is that about it? 8 minutes times 120 makes it 960 minutes, which would make it about...
16 hours?
960 divided by 60, yeah, it would make it 16 hours.
16 hours.
Right.
So 16 hours to get back. Here's Tom from Colorado.
Hello. My question is, what do you hope to do with the Voyager spacecraft after it passes Neptune? What kind of experiments would you, do you definitely hope to accomplish? And what other type of things would you like to at least be ready for if they were out there? I know about the bow shockwave detection, being ready for that, but whatever else you might hope to find out there. Thank you.
We'll go to Jessica von Puttkammer.
Both Voyagers, as we said before, will continue to research interstellar space, its fields and particles and radiation, and the ultraviolet spectrum. The program will henceforth be called the Voyager Interstellar Mission, the VIM, and they'll communicate with us for another quarter century. We will be receiving telemetry from both Voyagers until about 2037. In 2034, however, Voyager 2 runs out of hydrazine propellant, so its high-gain antenna can no longer be controlled to point to Earth. Voyager 1 will have enough hydrazine until 2040. The first instrument to shut down will be the ultraviolet spectrometer in 2000 for both Voyagers due to depletion of the plutonium power supply. The heaters of the UV instrument can't be kept warm enough to function anymore. And the fields and particles experiment closes down in 2016 for Voyager 1 and 2018 for Voyager 2 due to lack of power. Telemetry will then be limited to engineering data until the Voyagers go to sleep for their endless voyages through the universe.
Thank you. That was a very comprehensive answer of what will happen step by step. Quickly, what is on the screen? What was on the screen that we were looking at, Joyce, just before?
I don't know, Mike wanted to comment.
Oh, Mike, you wanted to comment on it. Yeah.
As a group, we haven't yet commented on a full-screen picture of the planet Neptune. This is the best one that we've seen as a group. I didn't want to let this opportunity pass to point out the great dark spot in the center and the white clouds swirling by that and the poles. So I was hoping to have a chance as a group to sort of point out some of those features on the surface of Neptune.
All right, and we'll return to do that. This is a photograph, an image from yesterday. We're now going to the Jet Propulsion Laboratory on the other side of the continent and back to Ira Flato and his guest this hour here on Neptune All Night. Ira?
Thank you, Sedge. My guest is David Morrison, a planetary astronomer and chief of the Space Science Division at NASA Ames Research Center. Dr. Morrison is author of a popular book called Cosmic Catastrophes. It's a little late for me to say that quickly, but more exciting to me is that you also have an asteroid named after you, 2410 Morrison. How did that happen?
Asteroids are discovered at a pretty incredible rate, really. Dozens of them every year, and so there's enough to go around to quite a few of us astronomers.
Well, how do you find an asteroid?
Well, I didn't find it. One of my friends found it with a telescope. Finding
You mean
an
amateur astronomer?
No, professional astronomers who search for asteroids and did me the courtesy of naming it for me.
Now, amateur astronomers find comets, don't they? There are a lot of amateur astronomers who've had comets named after them.
That's right. And in the case of comets, the person who finds it actually gets to have the name affixed to it.
Now, I want to ask you about infrared astronomy, and this is where you use infrared radiation, actually, to find other solar systems. What is the chance? I know there are some indications that we might be looking at some other solar system out there. Tell us about the state of how that is developing.
That is a very exciting topic in astronomy today. There are really two ways of going at it. One is just statistics. There are so many millions of other stars, indistinguishable from our own sun, that we would expect, surely, many of them have planetary systems. Actually, observing those planets is harder. What we can do, especially with infrared observations, is measure the early stages of planet formation, when there's still a thick disk of material, of dust. But unfortunately, we still don't have the capability to measure a planet itself once it's formed around another star.
Now, let me explain that a little bit. In other words, if you see more infrared radiation coming from one spot than another, you infer that that may be a planet system developing.
That's right, especially with very young stars that are still shrouded in the cocoon of dust in which they're formed before that dust dissipates.
And are there any real candidates that you have for new?
There are many young stars that show disks of material rotating around the star. And there are a few more mature stars that also have these disks of material, not planets themselves,
So you don't want
the raw material.
You don't want
planets.
people to get the impression that you're seeing another planet that might.
That's right. I wish we could, and it's just on the limits of what astronomy might be able to accomplish in the next few years.
What will it take to find a planet? What kind of technology do you need? Will the Hubble Space Telescope?
Unfortunately, that won't be able to do the job either. The best way we know to search for a planet is not by observing the planet itself, but by observing the motion of the star induced by the gravity of the planet going around it. So you don't look for the planet, you look for very subtle wiggles in the motion of the parent star.
And do you do that from Earth, or would it be better to put a telescope into orbit to do that, or?
You can do some of it from Earth, but certainly the best way would be to put a telescope in orbit. And there is a proposal for such a telescope to be put on the space station Freedom.
You also study asteroids. I know that's one of your specialties. What makes asteroids so unique? That's the wrong phraseology. What makes asteroids unique in our solar system? And why would you be interested in studying these giant pieces of rocks out there?
Those giant pieces of rocks are the debris from creation. They're the leftover materials out of which the planets and the more mature members of the solar system were formed. So they give us a window on the past, an opportunity to look at the kinds of raw material that formed when the solar system was very young.
And what about sending then a spaceship to an asteroid? That would seem to be a nice idea if you want to study it that way.
That's exactly right. And we have several spacecraft now that are going to pass by asteroids on their way to other planets.
Really?
The Galileo spacecraft, for instance, on the way to Jupiter, will pass at least one asteroid.
A big one? I mean,
not so big. You have to take pot luck on what's available along the trajectory.
Can you actually chip a piece off of it, or do you just observe it as you go by?
You just fly by in much the same way that Voyager is flying by the Neptune system now. Take a few pictures, make a few measurements, and then rush on to your next destination.
And of course, you know, this opportunity doesn't come by all the time, so you want to make the best use of that.
That's right.
Opportunity.
Now, you want chips of asteroids, and we almost certainly have them in the form of meteorites, the rocks that fall from the sky, occasionally on the Earth and can be studied in the laboratory. We believe that the majority of those are fragments from asteroids.
In fact, I was in Antarctica a few years ago watching them collect some of these meteorites, and there was speculation that some of the meteorites, now I don't know if this has been proven since then, may actually have started in Mars and have been coughed up by volcanoes in Mars and have landed on Earth. Is that viable theory?
Well, in a sense it is. For one thing, we know for sure that 4 of the meteorites collected in the Antarctic are fragments from the moon. And those match very closely the kind of samples that the Apollo astronauts brought back.
Right.
There are another 8 meteorites that seem to match what we understand about Mars. And we think they're fragments of Mars that were chipped off not by volcanoes, but by impact explosions, and found their way to the Earth.
Visitors from other planets right here. And they've been looking for UFOs all these years, and we have them right here already.
Yes, but they're just little pieces of rock the size of your fist.
All right. Thank you very, very much, David Morrison, planetary astronomer and chief of Space Science Division of NASA Ames Research Center. Back to you, Sedge.
Thank you very much, Ira, as we're continuing here with our Neptune All Night. Our next guest here this evening is Dr. James Truffle, who studied at Oxford University and has studied also at Stanford University. He serves as a science commentator for National Public Radio, and he has a book out called Reading the Mind of God, which is an approach to the laws of nature that continue to persist throughout the universe. Dr. Truffle, you with us here on Neptune All Night?
Yes, I am. Happy to be here.
Good, thank you very much. Do the laws of nature and science that have been handed down to us since the time of Newton apply to Neptune and the other planets?
Well, yeah, actually, Neptune played a very important role in our understanding of the laws of nature because it was the first planet that was discovered because of its effects on other planets rather than discovered just by looking through a telescope.
So it was a process of deduction then that found.
That's right. What happened was in the 19th century, after the planet Uranus was discovered, it was found that its orbit didn't quite match with what Newton's laws predicted they ought to be. And at that time, some scientists actually believed that, well, perhaps Newton's laws weren't right or they didn't apply everywhere in the universe. But others felt that the laws were correct, and what was wrong was that we didn't know enough about the solar system. And they said, well, if the orbit of Uranus is wrong, then that means there must be another planet somewhere pulling on it with the force of gravity. And they calculated where the planet ought to be and told astronomers where to point their telescopes, and that's how the planet Neptune was discovered. And this is very important, Sedge, because it was one of the first steps in a very important process that took place over the last 100 years. It was a process by which we came to understand that the laws of nature that we discover on Earth now in our laboratories apply everywhere in the universe, not just in our own solar system, not just to the planet Neptune, but to the farthest galaxy we can see, 15 billion light years away.
Hello, James Truffle.
It's an idea that's so important and it's become so ingrained in science that we hardly ever talk about it anymore. But it's not an idea that people have always had.
So the idea that the laws of nature are constant throughout the universe is really one of the most significant of rules.
Yeah, it's what allows us to talk about the origin of the universe. It's what allows us to talk about what goes on in other stars and in other galaxies, as well as within our own solar system. And it's not an idea that's natural. If you think about it for a minute, here we sit on this little planet on a star that's out kind of in the low rent section of a very ordinary galaxy, one of billions of galaxies in the sky, that we should be able to discover the laws that make the whole system work. It is really amazing.
I have a question for you from Judy Moffat, our science fiction writer here tonight.
Sure.
Yes, you talk about the laws of nature
I'm sorry, I can't hear.
You talk about the laws of nature being universal. You mean the laws of physics?
I'm sorry, I couldn't hear the...
I'll repeat the question,
Okay.
then, Judy, why don't you ask me then?
Okay. The laws of physical nature.
You talk about the laws of physical nature
Not
being
biological
universal.
nature.
Not biological nature, but these are physical.
Well, now that gets into a very...
I have only one example of biological.
Judy says we have only one example of biological.
Of biological natural laws.
Which
this
is
one.
which is the planet Earth, right?
Right.
That's correct. And this gets into a very interesting question about whether the laws of biology are based on the laws of physics or not. And as I'm sure you're aware, there's a debate that goes on between scientists about whether or not that's true. My own feeling is that with the development of molecular biology in the last 30 years, we're coming to understand that the laws of at least the one living system that we know about can be understood in terms of the laws of chemistry and physics. And certainly, if life exists elsewhere, which is another question, but if it does exist elsewhere, it has to exist in a way that's consistent with the laws of physics that we know about.
Well, thank you very much for coming and talking with us tonight. Dr. James Truffle, author of Reading the Mind of God and a science commentator. We're now going back to the Jet Propulsion Laboratory, where Ira Flato has another guest for us. Ira?
Hi, thank you, Sedge. I have with me a unique guest, James Head, who teaches planetary geology at Brown University, and he's a geologist. And astronomers don't study planets anymore. You have geologists and weather people studying it because they're already at the planet. And he has some new information about some latest details of Triton. And if we could get that picture of Triton up, I'll be so bold to suggest. Dr. Head, tell us what some new stuff that you've just discovered.
Well, I think the images that have just recently come in and the ones we're going to see in just a few hours here are incredibly exciting. what we see now is a real harbinger of what's to come, and the complexity. It's almost as if Triton is sort of the grand finale of our tour through the solar system, because it appears to have almost one of everything that we've seen in the inner solar system. It's shaping up now to contain things like incredible fault structures. There are T-shaped cross faults on them. We see a surface that's very pitted in a lot of places that's beginning to appear now, and in fact, it almost looks like a golf ball. These pits.
It looks like a golf ball? That suggests that there have been meteorites?
Well, the thing of it is, from what we can see at the present time, the pits almost look like they're pretty much the same size. If there was impact cratering, you would anticipate that there were a variety of sizes, and you know, some big craters, some small craters, but from the preliminary images we've seen, it looks as if the pits are approximately the same size, which would suggest that maybe there's some other type of process going on, maybe ablation by winds, or maybe collapse and melting of some of the ices. It's, as you know, it's really complex, and one of the reasons we're really looking to see the details and the structure is because the deformation patterns will give us some idea of whether it's water ice, or nitrogen ice, or methane ice, and we really don't know at the present time in detail.
What about the pink color? Now, it's the first moon I've ever seen, and that has a pink color to it, and that was one of the surprising things, wasn't it?
Well, I think
is it truly staying pink, the color, as we get it closer?
I haven't
and closer?
seen the more recent color images that were just obtained, but I think that from what I have seen over the last day, it's still definitely that way. And the thing is that one of the problems is to try to distinguish what might be occurring in the atmosphere, what might be occurring in the icy, rocky surface, and then what might be like polar deposits, sublimates, ices that are condensing out of the atmosphere as a function of position on the planet and temperature on the planet. So a real difficult problem will be to try to distinguish between these three things, anything that might be in the atmosphere and the sublimates like frosts and so on, and the rocky materials. But it's very clear from what we see now that we're definitely seeing geological structure on the surface, and very complex structure.
So you're here to tell us that Triton looks like a golf ball.
In parts of it look like a golf ball. Other places, there's bright and dark, very smooth plains that, in fact, have been faulted. In some places, the bright and dark material appears to be flooding the fault. So it's really complex. It's almost like you see, like it's like lava flows, except probably liquid water or liquid
methane,
possibly, and at the same time, it's clearly been deformed. So we see, in fact,
so could there be seismic activity on it?
If looking at the linear features and the size of them, it's very clear there's been deformation, which would result in quakes,
earthquakes, Triton quakes.
Absolutely, yeah. I mean,
and this is something that no one had expected.
It's really hard to know what to expect in a situation like this, but it's, I mean, the incredible thing to me is like it's a potpourri. It's like sort of a grand finale in a way, because it's got almost one of everything we've seen on the icy satellites, at least at the present time. And of course, in a few hours, we'll really be able to see in very great detail you know, what parts of the surface are characterized by these different things and all the relationships. But I can guarantee you it's going to be a spectacular show from what we see now.
It seems to be that has been the story of Neptune. It has been absolutely surprising, no matter what angle or what aspect you look at it. You know, from the clouds, the wispy clouds, and riding above the surface, to the fact that there are storms, and no one can really explain where the heat is coming from to produce these storms.
Well, I think this is one of the really exciting things about exploration, because if you just sit on your own planet and think you know everything and sort of have models for this, you don't test them and you don't question them. I mean, you might question them, but you don't know the right questions. And this is really Voyager is a demonstration of the power of exploration in scientific endeavors, because you go out and you see things for the first time, and it really makes you think about your own frame of reference. I mean, the examples you cite are perfect examples of why we really need to explore space.
And so you're going to go back now and look at some more photos of Triton as they come through? Now, I want you to promise, if you see something great, you'll come back later in the evening and you'll tell us about it.
Definitely.
You've heard it first, folks. We've been talking with James Head, who's come and given us for your ears and eyes only, look at what we'll expect to see later on in Triton. Thank you very, very much. Back to you, Sedge.
I'd like to ask Judy Muff to follow up a bit on what was being said there. One thing about sitting on our planet is using our imagination about what might go on there. The probes are showing us the outside of the planet. What about the imaginings of life that would exist on this kind of planet? What would a science fiction writer say, Judy?
The kind of life that might exist on a gas giant, a planet which has no solid surface on which life could move, has been speculated by Carl Sagan, though I don't know whether this is original with him, to possibly consist of large gas-filled bags of hydrogen, for instance, that could propel themselves by jets of gas. The only novel I know of that has actually tried to use this idea, well, there are two of them. One is by Frederick Pohl. It's a book called GEM, J-E-M, and in it there are characters who are intelligent and intelligent gas bags, essentially, little creatures attached to the bottoms of enormous bags, and they do move in this way, using temperature differentials and thermals and so on to propel themselves through the thick atmosphere of the planet, GEM. The other book is by the late James Tiptree Jr., the pen name of Alice Sheldon, and it's called Up the Walls of the World. And in that one, large, intelligent aliens, or they weren't aliens, to the planet they lived on, of course, large, intelligent creatures with great flukes glided through the atmosphere and rode the thermals.
Thank you, Judy Moffat, and our science fiction writer and guest here tonight. With pictures from space and voices from Earth, this is Neptune All Night. Neptune All Night is made possible by the financial support of viewers like you. With pictures from space and voices from Earth, this is Neptune All Night, continuing with our coverage from the Jet Propulsion Laboratory and our updates, and also with our commentary here in Philadelphia from our experts. I understand we have a phone call. Well, we've not yet heard from the Jet Propulsion Laboratory. They were expected to be here at 1 o'clock Pacific time, 4 o'clock here in the East. Our 800 number is 1-800-FLYOVER. Meanwhile, Derek Pitts, what is the image we're looking at on the screen at the moment?
We're again looking at Neptune. This is a picture that was taken about 6 o'clock, I'm sorry, last night. And we're looking again at the cloud tops of Jupiter. You can see very clearly in the upper left-hand corner of the screen what's called the Great Dark Spot, which is considered to be quite large. Mike, you had a number for that you were mentioning before for the Great Dark Spot, wasn't it?
It's something like the size of the Earth, which would make its diameter to be roughly...
Diameter would be 8,000 miles.
Across.
Across. And we can also see some light streaks of clouds zipping across the surface, again, that demonstrate the dynamic nature of the atmosphere of Neptune, something that's turning out to be incredibly interesting.
I think we're going to probably go back to JPL in just a moment. The signal from the Voyager 2, from the point at which it was nearest to the planet, is just now reaching planet Earth.
It's 4 hours and 6 minutes ago that that Voyager flew by Neptune, and now is the time when the signal arrives here on Earth, which is just a radio signal, not telemetry.
But that's just how long it's taken the signal from 4 hours ago to reach here. Derek?
And Jessica, will that signal be of, you mentioned before what that signal is doing, but will that signal also tell the scientists at JPL something else about the spacecraft besides just the atmospheric information?
This was the radio signal that was designed to pierce the atmosphere, thus being able to help measure.
And will there be any other information?
Well, first of all, it'll tell them whether the spacecraft was alive at that time, which is much more important even. So we'll find out at any moment now.
All right. We are now going to the Jet Propulsion Laboratory for the Voyager update, and then we'll be back here as we continue with Neptune All Night, live from WHYY in Philadelphia.
Come back from 2 billion miles away.
The spacecraft is now speeding away from that planet at 33,609 miles per hour.
Morning. Welcome to the 1 o'clock a.m. edition of Voyager Update for this, the 25th day of August, 1989. I'm Steve Wall. At 1 a.m. Pacific Daylight Time, Voyager is 256,000 kilometers, or 159,000 miles above the cloud tops of Neptune, and speeding away at 40,579 miles per hour. We've just passed through the Earth-Neptune occultation, which of course means that Voyager is now behind Neptune as seen from the Earth, and we've begun to receive data from the spacecraft once again. We have some tape which shows what this period on the spacecraft looks like to an observer out in that area, so let's roll that tape now. Okay, so you can see that Voyager is now headed through this radiation zone and has come into this shadow that's marked there on your screen. We'll be going now back through the radiation zone on the other side and out toward an encounter with the satellite Triton. Of course, as we go by there, one of the things that we study is how the radio signal comes in and out of this occultation period to tell us something about what the atmosphere is like. Coming closer, we come within tens of thousands of kilometers of Triton through its occultation. And then on speeding away from the system. Many questions have been asked as to when we're going to receive these best pictures from closest approach to Neptune. Now, of course, you have to realize that the spacecraft is limited in the number of things it can do at one time, and so both because of this occultation period and because of the high activities that are going on at this time, a lot of those images and other scientific data get put on tape so that they can be telemetered back to the Earth later on. With me to answer that question, and I hope a lot of others, is Larry Soderblom of the Voyager imaging team. So Larry, I guess first of all we want to talk a little bit about Triton and some of the...
I think a little bit about what we're seeing now. This color image of Triton we were looking at earlier this evening, and I'd like to point out a couple of things that we're looking at and looking for. This northern region is a fairly featureless, dark terrain unit. You see a number of spots and markings. Here's a bright looking patch that could be frost in the floor of an impact crater. We don't yet know whether or not we're seeing, as I mentioned earlier, we still don't know whether we're seeing a heavily cratered surface or a very young surface.
A lot of pockmarks on there.
That's right. So one of the things that we are seeing, we've noticed this for a couple of days, is these long streaks. And they're becoming prevalent. You'll see them in the high-resolution pictures in a minute. Those are suggesting tectonic forces, that is faulting, breaking of the crust, internal geologic activity. Now, it may have been very ancient. If we go to the image that came down about an hour ago, we're now looking at about twice that resolution, and we are looking in the hemisphere of the Voyager close up imaging of Triton that I'll talk about in a minute. The closest images will be of this region right here along the terminator. We call that V-term. Okay. And that'll be acquired and put on tape. That's the highest quality data. And so in order to ensure that it's not lost, it is taped. In this case, not because of the occultation, but in case there's rain in Spain or something, then we have the option of playing it back off from the tape recorder several times if necessary. Okay. This region tonight, as we approach, will be imaged first in color, and that will go on the tape recorder, and we won't play that back until late tomorrow night this time. And then following that VT color sequence, we at somewhat higher resolution map this entire region in black and white. And that will come down tonight, and that's the stuff that's most exciting, and I'll show you what that coverage looks like.
Now that'll come down this morning?
Well, I'll tell you exactly when it'll come down.
Okay.
I'm going to center that in there. Okay, there we go. So that's what VT map looks like. Okay. And that data will start hitting the ground around 3 o'clock a.m. and finish up around 5 a.m. And there are some wide-angle frames as well associated with that map. But those are the 18 narrow angles. And you can see, in fact, depends on how whether you're numbers. Yeah, well, that's fine. This This depends on whether you're an astronomer or a geologist. If you're a geologist, it goes like this.
Oh, okay.
Okay? The North Pole's at the top. That has to do with the way things are plotted in terms of the coordinate system of the spacecraft.
Okay.
But the Terminator, recall the dark side of the Terminator is up here, so we are in fact photographing the bright side.
That's good.
That's good. And the sequence basically builds to higher and higher resolution, so you see the frame size shrinking.
Mm-hmm.
So this highest resolution frame, I believe, comes in about 513 this morning.
Okay.
So, and again, notice this is 0 longitude.
Mm-hmm.
So if you go back now to image A, in the 0 degree longitude is approximately right there.
Mm-hmm.
All right?
Yeah.
Sort of goes down near this long sort of gash.
Okay, now the South Pole is still down in the bottom.
I shouldn't say
area
gash,
here,
I
right?
should say this long, dark linear marking here.
You're talking about this marking.
We don't know that we don't have evidence yet for any relief. I haven't seen anything in the Terminator or on the limb that, you know, you'd expect, as I was saying, in these higher resolution views, if there is mountainous topography on Triton, you ought to see it starting to emerge now. Now we're at a resolution where those hills on Io would really be obvious, and the mountains associated with craters on the moon.
Okay, does that mean that...
And again, in this region, which is the Terminator, we haven't seen evidence yet, except very subtle topography suggesting ridges, and it's looking more and more like Europa.
So these are different color markings on the surface. You're saying this probably is not due to mountains.
Well, we
and
don't know
valleys,
yet.
Or you don't know.
We don't know yet, but we haven't seen yet. The resolution hasn't gotten good enough. But let's look again. This is the 0 degree meridian.
Mm-hmm.
Okay, back to the overhead. And again, all right, here's 0 degrees.
Mm-hmm. So
that's basically the hemisphere. Now that light dark boundary is close to the equator, and so it'll be sort of modulating through this in position through this region here. Okay, now going on, tomorrow night then, in addition to VT color, we will get VT term. Now notice again, this is 0 degrees in longitude at this point.
Mm-hmm.
This sequence was redesigned. It turns out that this plot I have here is from an earlier estimate of the diameter of Triton, which is now shrunk. This was either 3,000 or 3,600 kilometers. I can't remember which, but the correct diameter now is about 2,700.
Okay. Now, when will these pictures be played back?
Okay, these pictures are going on the tape recorder, and they will be played back tomorrow night. And I can show you the time here. Blow this down. So here we are tonight. This is, where are we here? Here's midnight.
Okay, here's midnight.
Here's midnight. So we've just come out of the occultation zone.
Right.
So we're now on this approach you just showed in the simulation, as we're flying down toward Triton, we start taking VT map, and this is coming down in real time between 3 a.m. and 5 a.m.
Okay, so this is 6 the sequence of pictures you were just showing us.
That's right.
Right, okay.
And then tomorrow night, here's midnight again. Here's the color approach being played back off the tape recorder from about 2 a.m. to 6 a.m. And then V-term is actually, it's part of that same playback. So these images, and you can see what I mean, it's been redesigned.
Yeah.
Will be played back between about 6 a.m. and 8 a.m.
Okay.
So that'll give you the orientation. And remarkably, as I was mentioning earlier, just by plain luck, this set, when we shifted it down, so it now crosses right over the bright dark transition zone, which is extremely important if we're going to understand this object. From what I've seen so far, it's the most mysterious thing we've ever come across.
Yeah. What are your
what are the range of models?
What do you think? Yeah.
Wow. we haven't even focused down from such things that, let's go back to this color image again. One, it's conceivable that this southern hemisphere, this modeling you see, is because it really is rough. Suppose there is really cratered terrain there.
Yeah.
And suppose this is northern plains are resurfaced by some icy volcanism.
Yeah.
This could be sort of organized like the planet Mars. In the southern hemisphere is a rough terrain, and also the this boundary between the light-dark boundaries is slightly tilted on Triton. We don't understand that, but if it were due to real topographic differences of a highlands and a plains, all right, well, that's one extreme model. And then you'd have to say, well, the highlands have a different composition than the lowlands, and it makes it a little difficult to explain why we should arrive just at a time. If it's a frost cap, why is the frost cap just coincidentally on the margin?
Yeah.
It would have to be related to the intrinsic properties of this material. Another model is that this is a polar cap, mixed methane and nitrogen ices, one or the other or both, which is subliming as the sun is shining down in this latitude region and actually condensing along this margin, and then re-subliming and going northward. Now these wisps of material appear to be not going straight north, but they're going to the northeast. In other words, this angle. As a matter of fact, all the way around the disk, we've noticed that these patterns are systematically at that angle. Well, what's interesting about that? The North Pole is cold, and the nighttime is cold. Well, the nighttime's over here, and the North Pole is over here. So if these materials are headed for the coldest place, they would be deflected in that sort of way. So there's even another extreme model. Suppose this is, in fact, the material that's moving around.
Yeah.
This is...
you're saying, suppose now that the dark stuff is that this is stuff that moves.
Yeah, Torrance and I were talking about this, and I don't think either of us believes any of these models, but that's the other extreme, that this dark material is actually mobile, and it's actually being, so this is sort of the condensation. So you can see that until we get higher resolution, the whole question is pretty well unconstrained.
What's the highest resolution we'll get?
Well, the highest, this is a resolution of about 40 kilometers per line pair. 40 kilometers. And the highest resolution we'll get is about 0.8 kilometers per line pair. So about nearly 50 times higher resolution than this.
So we'll be able to see objects that are a few miles across. We'll be able to identify objects that are a few miles across.
We'll be able to resolve features the size of a city block.
Wow. And how big are these things that you've been talking about, these smaller features?
Oh, typically these are in the 50, sort of 20 to 100 kilometer scale, these dark spots. And there's quite a range. There's people who are certain they're seeing impact craters to people that are convinced that nothing there yet requires an impact crater. And so whether or not there's topography there or not is very important. One of the things we're interested in is what is the rigidity of Triton's crustal materials. If they're really if they contain a lot of methane, nitrogen, or ammonia, then they could be quite mobile and quite soft, geologically speaking, and flow could occur. And so the topography could have simply collapsed. As you may recall, that's what happened on Ganymede and Callisto, in which craters, and some of the Saturnian satellites, in which the crater forms, the only thing recognizable is sort of a painted scar on the surface, but the topography is totally gone because the plastic material has relaxed.
So the surface is just not strong enough.
Yeah. So far we haven't seen the topography. So far it could be a very soft body.
When you think about an ice ball in terms of water ice, I think of images of of glaciers and the things that, the earthly things that we think of as ice. Any idea whether there's going to be that kind of motion? Could this stuff have piled up into glaciers that made topography, like from the Ice Age on Earth?
There can certainly be flow of material.
Yeah.
In other words, even though, see, water ice is literally a rock at these temperatures.
Right.
I mean, the stuff is really rigid.
And is methane ice
But
as
if
solid?
it contains other ingredients, namely things like ammonia, we know methane's here, and methane and nitrogen mixed together in an ice would be a candidate for a mobile material on this object. So to make a glacier, you got to get the material to the top to a higher potential so it can flow downhill. So you got to worry about that too. As a matter of fact, the biggest problem is figuring out what energy source is going to drive this. There was an energy source in Triton's tidal evolution, but right now it's in a very circular orbit, the eccentricity of 0.001 or something. So there's very little going on in the way of tidal heating. So, but we've been introduced to new phenomena before. It wouldn't be the first time if something else is going on here.
We've said that Neptune is expected to be less, show less motion of features because it's lower energy, it's further away from the sun. Should we expect the same thing of Triton compared to the moons of Saturn and the moons of Jupiter in general?
Well, in general, you expect smaller bodies to have lesser activity, largely because they lose heat faster.
Okay.
And whether radiogenic or otherwise, tidally induced. But the other thing counter to that is that as we move out in the solar system, there are materials that are even more fluid that are available at those temperatures, like methane, ammonia. Carbon monoxide is another candidate as a gas in here, and that's even more volatile than nitrogen. So there's a lot of things that could be there that would really mobilize and lubricate the geologic activity in these bodies.
Speaking of geologic activity, is that what's going on in the imaging team over the night tonight? Is trying to piece together what's going on Triton while we wait for
That's right. So trying to we'll be sitting on the edge of our seats as this stuff comes in, and some of the questions will be quite clearly answered. I suspect more of them will still remain a mystery for some time. I predict this is going to be an extremely complicated object, more complicated than even Miranda or Io. And it'll take some thought.
Boy, if this is more complicated than Io, this is going to be an exciting time for the next few days.
You got it.
Wow.
It's one way to go out of the solar system, isn't it?
I guess so. Well, while we've been talking here, of course, we think, or we believe, and have every reason to believe, that Voyager has done its closest approach with Titan out at Neptune. We won't know, of course, until the radio signals have had their 4 hours and 6 minutes to get from there to here. But we'll know more at the 2 o'clock update. In the meantime, this is Voyager Update, and I'm Steve Wall. Thank you.
Eucnis poteste caerete.
Des voix, des nuages, des mers, par-delà le soleil, par-delà les éthers.
Paz e felicidade a todos. 各位好嘛，祝各位
Tu te moques avec
健康
agilité.
快樂。
Et comme un bon nageur qui se pâme dans l'ombre, tu sillonnes gaiement l'immensité.
สวัสดีค่ะสหายในธรณีโทนพวกเราในธรณีนี้
हमारे
ขอส่ง
दोस्त जो खला में बसते हैं उनके लिए दोस्ती और खैर सगाली
النجوم يا ليت يجمعنا الزمان
हमारी दिली ख्वाहिश है कि सारी दुनिया में अमन रहे
माए लागनिया
जिंदगी के हर
Freunde, als Vorsitzender des Denkmalschutzes
sampai bertemu lagi di lain waktu.
Österreich, freue ich mich, Ihnen auf diesem Wege
Hello from the children of planet Earth.
With pictures from space and voices from Earth, this is Neptune All Night.
And we're seeing a picture of Neptune that was taken earlier today, and this is all part of Neptune All Night, as we're waiting also to see the images that are coming from Triton. Good evening, good morning, wherever you are in this country. You're listening and watching to this program that includes the images from the Jet Propulsion Laboratory and a panel of experts here around our table. The 8 of us here gathered at this hour of the night. I think somebody's out taking a little walk here at this moment, but they include here Jesko von Puttkamer from NASA, Strategic Planner in the Office of Flight, Judy Moffett, science fiction writer, Jack Horkheimer, and then from the Franklin Institute of Science, the Franklin Institute Science Museum here in Philadelphia, Derek Pitts, Mike Weilbacher, and Joyce Town. We're going to take a phone call here to begin this hour. Wayne from Urbana, you have a question for our guests?
Yes. A couple of the questions and comments that I heard earlier kind of sparked this question that has occurred to me before. Postulating an intelligent alien race who had a technology similar to ours with things like Voyager, our deep space tracking network, and so on, how far away could they be from us and still be able to detect things like the television and microwave transmissions that we've been making on this planet for the last 40 or more years?
Derek Pitts?
Well, one of the ways we can think about how we are making a reach out into space from Earth, besides just these unmanned spacecraft, are those signals that we have been broadcasting by radio and television. For the length of time that we have been creating signals like that, they have been traveling out into space at the speed of light. So we can say that if we have been broadcasting these signals for 50 years, 60 years, then they have reached 60 light years out into space. So at that distance, there is a front of information coming from the Earth that is increasing as time goes on in that direction. So there's one way to measure that kind of information going out there.
Which means that Uncle Milty Burrow will be essentially the first contact that...
Okay, let's say it's 50 to 60 light years. Now we know that within that sphere, within that regime, there are many stars which may have planets. But we have done some calculations assuming, optimum conditions for life to come about in the universe. So even if there are millions of civilizations in the galaxy, space is so big that they are spaced so far apart that the average distance between civilizations is still about 300 light years. So if that applies to this particular case, 50 light years for this front of radio and television hasn't even covered half of the distance to that potential or putative 300 light years distant civilization. So we still have many, many years to wait for them to receive it.
All right, thank you. Do we have another call? Not at the moment. All right. Mike, you were talking about the idea of the similarities between the myths of Neptune and of Triton and what we're actually seeing on the planets. Neptune, the god of the sea, Triton, the sun, and Nereid, one of the planets, a nymph.
A nymph. Neptune is in Roman mythology the equivalent of Poseidon. In Greek mythology, the brother of Zeus. So essentially, he's the brother of the king of the gods, the head of the gods. He was never quite pleased with his place in that hierarchy, since he was Zeus's brother. He thought he should have equivalent power. So he was a jealous, kind of angry, kind of vengeful, and extremely unpredictable god. And they often gave sacrifices to him as god of the ocean. He never quite knew when a tidal wave was going to come. So what we're seeing is the unpredictability in the surface and the violence in the surface. He was also the earth shaker, was another name for Neptune. So what you're seeing on the surface of, the lively surface of Neptune is rather striking for a planet named after Neptune.
Mike Weilbacher from the Franklin Institute, and comparing myth and reality and showing how sometimes they mix. Neptune.
Food for thought.
Are you getting hungry at this hour here, Jessica? Is that why you're
I'm looking forward to my breakfast.
With pictures from space and voices from Earth, this is Neptune All Night.
Oiktinis poteste chairete. Eirenikos prosphilus eleluthamen philoi.
Paz e felicidade a todos. 各位好嘛，祝各位平安健康快乐。
Adanish Lushulmu.
Здравствуйте, приветствую вас.
สวัสดีค่ะสหายในธรณีโพ้นพวกเราในธรณีนี้ขอส่งมิตรจิตมาถึงท่านทุกคน
Some of the voices of the planet Earth sending their greetings that may or may not be heard one day, and these are aboard the disk that's affixed to the Voyager 2 spacecraft, now just passing beyond Neptune, and which will be bringing us photographs, images of Triton in a couple of hours. Neptune All Night continues here from WHYY Philadelphia and the Jet Propulsion Laboratory. Stay with us.
Visce Shantihok. Salvete quicumque estis. Bonam erga vos voluntatem habemus, et pacem per astra ferimus.
Shalom.
Hartelijke groeten aan iedereen. Herzliche Grüße an alle.
अस्सलाम वालेकुम हम ज़मीन के रहने वालों की तरफ से आपको खुश आमदीद कहते हैं.
Chân thành gửi tới các bạn lời chào thân hữu.
Sayın Türkçe bilen arkadaşlarımız, sabah şeriflerinize hayırlı olsun.
Konnichiwa, o genki desu ka?
धरती के वासियों की ओर से नमस्कार.
Yache dai hui an aur akanoizoid.
Tanti auguri e saluti.
Aibuan. Sian ibingalela makawe, snipisela inkonzo ende. Pria dumelisa marena.
Sonada kaho.
Բոլոր անոնց, որ գտնվին եզերքի մի կամազություններեն անցին.
Welcome back to Neptune All Night here from WHYY in Philadelphia with images coming from the Jet Propulsion Laboratory in Pasadena, California. I'm Sedge Thompson along with Judy Moffat, Jessica von Puttkamer, Joyce Town, Mike Weilbacher, Derek Pitts, Jack Horkheimer, and yourself. Those are the sounds of greetings that we were hearing. They're on the Voyager spacecraft. Several of us were chuckling as we recognized different languages going by.
Even
Just
Latin.
Noticing
Even
the Latin. Some of us noticed the Hittite and the Sumerian and the Greek.
There's actually the voices of whales on it.
There are the voices of whales also in that recording. And one historical footnote, he may not make it on future discs, but the greeting from the UN Secretary General on there is on there at the time, Kurt Waldheim. And he may not have qualified this time
Change
around.
the subject.
Yes, we'll move on. From College Park, Maryland, Steve has a comment or a question for us.
Oh, hi. I was just wondering, I recall it was about radar telescopes. Back when they were looking at the supernova, they computer-linked two widely dispersed radar telescopes to form a very large one. I was wondering if it was practical or desirable to launch radar telescopes on a Voyager-like platform and computer-link them over a vast distance to get a large radar telescope in effect.
Who would like to take that? Joyce?
I think I can address that. Pretty much as a system of arraying that's already going on Earth, where we have dish antennas hundreds and thousands of miles away from each other, and that's pretty much all the distance that is necessary for hearing most of these things from space. So we don't really need to have anything launched, I don't think, at this time. We could also put parabolic antennas on the moon. Yeah, that might be a nice location for things like that, too, in the future.
Derek?
One of the other interesting things that's been done by radio astronomers involves using one radio telescope, but observing from different positions in the Earth's orbit. For example, one could use a radio telescope to observe an object in January, and then wait 6 months later when we're on the other side of our orbit around the sun and observe from that position and use the data from both of those positions to create a baseline from which we can then make our observation. That very long baseline, a line that goes from one side of the Earth's orbit to the other through the sun, can set up this system that gives us a very refined image.
NASA is developing what we call a large deployable reflector for the years after 2000. And if you have several of those in orbit, you could do what the caller just proposed, ganging them up or arraying them in a very large radio astronomy antenna, which could find maybe planets.
Have there been any, have you heard anything about size on those, Jesco? How big they might be?
Well, they start out with maybe 100 meter in diameter, and then you can go up maybe to a kilometer or so.
What is the size of the dishes that are in New Mexico?
Well, 3 of them have just been enlarged from 210 to 230 feet in diameter.
And these are on like railroad tracks that are able to move back and forth across the...
These particular ones are not, I don't believe. There is another system like that, but I think that...
Well, there is a VLA, the Very Large Array in New Mexico, which is, I think, 23 or 27 radio astronomy antennas on rails. And if you add up all their receiving surface right now, it amounts to about 4 times a football field. And that's what we need to receive those signals from Voyager right now.
And I remember driving across a rise and coming down into the plateau and seeing it was a very eerie landscape sculpture, seeing all of these antennas.
You know, we hope one day to have those types of things on the moon, on the backside of the moon. You know, imagine that the power of the radio signal of Voyager when it arrives here is 20 quadrillions of a watt, which means it's, you know, it's just a tiny little fraction of the power of your digital wristwatch. You know, it's just so unbelievably small, and still those antennas actually are able to receive it and amplify it.
This very large net that is actually connected all around
and,
the world.
And, there are antennas, you know, like Joyce said, there is an antenna in Japan, in Usuda, helping us, and 3 antennas, one in Madrid, one in Australia, and one in Goldstone in California. So they are arranged to stay in connection with Voyager all the time.
You know, when we've seen the new images come up here, screen by screen, the scientists here around the table get very excited and eager and look and try to puzzle out what's going on. Ira Flato is at the Jet Propulsion Laboratory, where I know that the scientists there are eager and in anticipation of what they're seeing. Ira, can you describe the behind-the-scenes activities at the Jet Propulsion Laboratory?
Well, I can only imagine what's going on because they don't let any journalists in there to see it, but I've been to enough Voyager encounters to get a good picture of the scurrying that's going on. I can tell you here in the press room that there's an unprecedented, no pun intended, number of press people waiting around. There are at least 100 or 200 press people here now at 1:37 in the morning, whereas in past encounters they would have gone home and been in bed by now. And I think that what they're all waiting for, and what we're all here holding our breath for, is to find out whether Voyager 2 made it unscathed through the ring planes. Don't forget that they have found rings where they had not expected to really see any before. There's at least one ring there. And they've also sent Voyager into a planet that has a larger atmosphere than they thought it would have. So they're wondering whether, you know, Voyager will come through the dust and the debris that they might encounter, not only going up initially into the ring plane, diving over the top of the North Pole and coming back down through the ring plane again. They're waiting to see if there will be any damage to Voyager 2. Interestingly enough, Voyager 2 should have sent us, we should have received the signals from Voyager 2 about a half hour ago, telling us that it had reached the closest point of Neptune, but there has been no word that those signals have actually come through. So we're still waiting for confirmation of that. We may hear that at the 2 p.m. press briefing, as you will all hear it at the same time. They're also wondering, you know, what the state of the cameras on board will be. You remember that when Voyager 2 went through the ring plane of Saturn, it came out of it a little bit damaged. Its camera platform was not working so well when it came out. And there was speculation, I remember being here at that time, that it might have picked up a piece of dirt or something and chewed it through its gears and slowed down the arm, but the arm never worked the same again after it came out of there. They now attribute that to some oil not being distributed correctly or slowly leaking around on the camera platform. But that's basically what they're here for. Everybody's waiting to see what the state of Voyager will be. And in the meantime, they're all discussing some of the incredible surprises that have occurred. For example, something that has sort of been lost in the noise is that the 6 moons that were discovered by Voyager, they've all been labeled 1989 until they give them other names, 1989 N1 through N6. N1 now takes over the place as the second largest moon of Neptune, taking the place of Nereid. And somebody asked today, how come no one has not seen this by telescope if it's such a large moon? And the answer was, it hugs very close to the planet, and therefore it is really lost in the glare of the planet when they look through a telescope. They also had the first successful weather forecast of Neptune, in which they had to predict where to point the cameras, because it takes 4 hours to send a command, and then the camera has to react. So they were looking to take a picture of the giant dark spot, and they had to figure out where the giant dark spot would be 4 hours later after the command arrived. So they actually were able to predict what the where the giant dark spot would arrive, and they pointed the camera in that direction. That was the first successful weather forecast, I think, they said, on a foreign planet. They tried to do it a little later, and it didn't work. They tried it on the small dark spot in the southern, sort of the southern part. If you look at the picture now, down where that wispy cloud on the bottom is, that's sort of the vicinity where the smaller dark spot was. They tried to predict the movement of that, and they were not successful. And it was interesting that someone asked why were they not successful in this prediction, and it was because unlike on Earth, where we have a giant heat engine at the equator that sends storms north and south, there is no giant heat engine in this equator, and these storms just move wherever they want to go, or they just stay stationary for a while. They go in unpredictable directions sometimes.
Ira?
Yes.
I want to thank you for the report from the JPL. So it sounds like the press is there, one, for new discoveries, and two, in case there's disaster.
They're always here for those. They're also waiting to see pictures the other side, you know. Because the most interesting pictures of Neptune will be from when the sun is behind the planet. If you look at a photographer who takes a picture of, for example, a model's hair, they'll backlight the hair, and you can see every single strand of hair sticking out. Now they're going to look for the ring of Neptune by that backlighting technique, so they might be able to see fine dust particles that they could not see coming from the other side.
All right. Thank you for the insight. And that's Ira Flato reporting from the Jet Propulsion Laboratory in Pasadena.
Okay, this is more of the housework. I did a lot of the cooking and bottle washing, and if you look out the window there, you can see the snow going by. We're doing a water dump at the same time. Cooking a meal is about like doing it on the ground there.
This is a bank shot by Crippen. Trying to get my eggs in my mouth.
We do. You do tend to eat in space like you do underground.
Almost.
Almost.
Some of us do.
At least I eat in space. I eat like I do underground.
Right. So did Doc.
So did Doc.
That was the real rotating Grappolo boy.
He gave us time to play up there, too.
Well, in this particular sequence, we're showing how we prepare a meal. And we divided these tasks up among all the crew members. Dale usually wound up doing breakfast because nobody was quick enough for him. Making meals is a fairly easy task on orbit. All you had to do is essentially like, it's very good, essentially like backpacking. You essentially add water to the food, and it was very good. I'll let Rick describe what we're doing here.
Well, at the risk of endorsing a product, that's an interesting physical demonstration on orbit of the fact that things really are weightless.
That's how the crew was rewarded when we did something properly. Rick would release another handful.
Since Anna did more things right than anybody, she got most of them.
Dave, on orbit, described Dr. Allen as large in personality, but diminutive in stature. Whenever his personality got a little bit too large, we would stuff him away in a locker for a few hours, And then when a task needed to be done, it was my job to go down and get him out. This was a somewhat unpleasant task for me, but Joe seemed to like the freedom at times. And
the hard part was putting him back in there again later once we got him.
And here's Gordon getting ready for one of the many burns with our smaller orbital maneuvering system rocket engines. Here you see us maneuvering Attitude and the small Attitude jets firing. We did an experiment so you could appreciate the acceleration we get out of these rocket engine firings. We put 8 ounces of water on the middeck, and here you see it traveling across, and Dr. Bartow is catching it. We also tried to sleep through some of these burns, and we staged this next scene to show you what it felt like in the bunk.
That hurt.
That was a great train wreck.
Believe it or not, some of them slept through those once they got used to it.
Here we're setting up for an on-orbit OMS burn. We're getting some things ready in the middeck. There's the OMS engines firing out the back, and now watch what happens in the middeck. That's 1/16 of a G. Each of the OMS engines is 1 foot per second squared for a total of 2 feet per second squared, and that 1/16 of a G felt like a lot to us after being up there for 3 or 4 days. And you can see the acceleration on the tape. It keeps wanting to go back towards the aft bulkhead because we're accelerating forward towards the left of the screen.
Here we can see the left OMS engine burn, and that's just the start up. The burn lasts for a little while, and this is what it looks like in the middeck. And Jerry made it right into the airlock, and we collected all those pieces.
Here's a picture of Gordo establishing himself in that area. And why don't you move the coat there, Gordo, and get it out of the way? Thank you. And, of course, one of the things Gordo had to do is brush his hair every morning.
Some more sounds from the Voyager record. This is Ira Flato at the Jet Propulsion Laboratory, and I'm joined by Carolyn Collin Peterson, who is a member of the Comet Halley Atlas team at the Laboratory for Atmospheric and Space Physics at the University of Colorado at Boulder. Welcome. What is the Comet Halley Atlas team?
Well, good morning, Ira, and can I say hi to my friend Jesco and my colleague Jack Horkheimer?
Okay.
I can't hear you, but anyway, the Comet Halley team, the Comet Halley Atlas is will be a collection of about 700 to 800 of the best observatory and amateur comet photos taken of Comet Halley during the 1985-86 apparition.
People still learning things from the Comet Halley?
We will be, a lot of the scientists that will be looking at this will be doing the kind of work determining the position of the tail in the solar wind. And so my work is to help determine the exact position of the comet in the picture, how it's oriented north, south, east, west, and what the scale is of the picture, how long a feature is in tens of kilometers or millions of kilometers.
So this is not a coffee table book that consumers will go out and
Well, we
buy.
refer to it as a coffee table book, but it really isn't unless your coffee table happens to be in a science office.
You also have a lot of experience producing planetarium shows. And
Yes, that's right.
Yes, and you were saying, and I thought it was very interesting, that planetarium shows now are a lot different and have to be a lot different than they used to be. Why is that?
Well, a long time ago, planetariums were solely conceived of to teach astronomy, and there was that perception that it needed to be a very strict educational medium. And now with the advent of television, a lot of movie things from Star Wars, things like that kids are seeing, that our audiences are seeing, they're influenced by that, and the level of sophistication has gone up in that kind of programming, and so therefore I think that planetarium shows have had to go up as well.
You just can't show stars on a starry night up in the sky with an arrow pointing
Oh, sure
to
you
things.
can. But if you can do that, and those are some of my favorite kinds of shows to give. I'll get 5-year-old kids in the planetarium, do star talks. We play Cosmic Connect the Dots with the constellations. But for teaching something, say, about the Voyager Neptune project, we will produce a program. Well, we're producing 2 programs, but the first one we'll produce, our company, which is called Loch Ness Productions, the first one we'll produce will be very much produced with a television kind of ambiance in mind. A slight tease at the beginning, some very well done electronic music, hopefully a celebrity narrator, although I'm not quite sure who we're going to have yet. And it will be something that people who are used to watching television or films can come and listen and watch and learn something and be entertained at the same time.
A lot of planetariums have laser shows now. Do you incorporate laser?
No, we don't.
themes
There
and
isn't
things?
really any way to do that. We're solely producing the software, the soundtrack, the tapes, sometimes film, although we're getting away from
Are
that.
people
as
still
video.
coming to the I love the planetarium. It was such a great place to, you know.
I hope they are. At the planetarium I lecture to, a number of people come to the shows. We did a show about Mars last year that drew in sellout crowds for 6 weeks in a 213-seat planetarium. I think Dr. Horkheimer in Miami also draws very good crowds. A number of planetariums in the larger cities do.
Well, that's good to hear, because I don't want to think that TV has taken over everything.
I don't think
People
it's TV taking over so much as it's some of the influences of television, some of the really slick professional production techniques that television uses that you can't incorporate into the planetarium.
Well, thank you very much. We'll look for your show
Oh, thank you.
On,
Thank you.
on the Voyager. Carolyn Collins-Peterson. Don't forget her Comet Halley Atlas.
It's due out sometime next year.
If you have a giant coffee table in your science office. Back to you, Sledge.
Thanks very much, Ira. And planetariums, of course, are wonderful places to visit in the dark, and then the night stars come up, and you have programs that take you to all these realms. And of course, members here tonight on our panel, Mike Weilbacher, Joycetown, and Derek Pitts are with the Franklin Institute Science Museum, which has a planetarium, and Jack Horkheimer, of course, the planetarium in Miami.
Thank you, Jack. The Miami Space Transit Planetarium.
That's right. Planetariums are a wonderful place to sleep. It's the only place I can get away from phones.
No, I sometimes
space out.
I sometimes spend time at the planetarium, the Morrison Planetarium, at the Academy of Sciences in San Francisco.
Wonderful place.
Which does a lot of fine shows. And we have our own kind of vertical planetarium here tonight, taking a look at Neptune. And we have now a call from the coast, from Los Angeles, to Jim. Good evening. Good morning.
Hello.
Hello.
Hello. I had a couple of questions. Number one, I was told this was answered earlier, but I guess I didn't catch it. How come the Voyager is not heading towards Pluto instead of flying out of the solar system after it passes Neptune?
Can we have a quick recap of the answer, Jessica?
In order to be redirected by Neptune in the direction where Pluto is right now, the aiming point would have to be inside Neptune.
In other words, the Voyager 2 would have to go through
Neptune in order to be turned around enough to get to Pluto.
And although it's a gaseous planet, it's not that gaseous.
That's right. And with other words, Pluto is not in the right place right now.
Okay. Thank you.
Second part.
Oh, second part?
Did you have a second question?
The caller may be gone.
Oh.
We're going to Maine, to the other side of the country, to David.
Yeah, I've got a two-part question. First of all, is it known yet whether the satellites of Neptune are spin-orbit coupled to the planet? And the second part is it known whether there are any natural, non-asteroidal satellites that are not spin-orbit coupled to their primaries?
Anyone here at the table like to take that? Derek? No?
As far as I understand, the moons that we've seen so far are all gravitationally coupled to the planet. I have not heard of any other bodies that are not gravitationally coupled to the planet, but I'd certainly like to leave it open for somebody else to comment if they've heard more recent news than I have.
Oh. No, but Triton definitely is.
Triton definitely is, yes.
So it has the same orbital period as rotational period?
Yes.
Okay. 5.8 days.
5.8 days.
Right.
So that means that if we could stand on the surface of Neptune, we would always see the same face of Triton, which is exactly the same situation as we have with the Earth and our own moon. Yeah. We always see the same face because of the rotation.
What was the second part of the question?
Just whether this is a constant feature of the solar system. That is, if all the natural moons are spin-orbit coupled, that is, if the same side always faces the the primary, the planet, or in other words, if the rotational period and the orbital period are the same, if that's true of all the moons in the solar system.
I don't think we know enough to say so right now.
No, not enough information. Thank you very much, David in Maine. And do we have another call? We do. This is, we're going to Kentucky here on Open Phone Neptune tonight. Hello, Ted.
Daughter, Kansas.
Oh, you're in Kansas?
Yeah.
All right, and you're not Ted, I don't think. Go ahead, please. And you are?
Ted Browning.
Ted in Kansas, okay.
Yeah. I'd like to know, would anybody be sending any probes or anything over to Pluto or in around the Pluto area? And also, has any the Pioneer and that Voyager 1 satellite ever left our solar system yet?
Quickly, Voyager 1, has it left the solar system? We'll take it in reverse order.
Voyager 1 has taken a turn away from the plane of the planets of the solar system. That plane that we call the ecliptic, it has turned southward toward the edge of the solar system. Oh, northward toward...
Voyager 1 is northward.
Voyager 1 is north, toward out of the solar system. But one of the boundaries that we look for is called the heliopause. It's the interface between the distance that the solar wind reaches, those particles that are blasted out by the sun, and interstellar space. And I don't believe that Voyager 1 has passed that boundary yet.
And is there...
And the Pioneers have left. In fact, the Pioneer 10 we have just celebrated its departure from the solar system earlier this year. And the other question was whether we are planning a probe to Pluto. Well, right now, NASA's plans do not have one in the early years. We'll probably have one later, maybe in the first or second decade of after 2000. Right now, I think there are more important targets for scientists, and they probably consider a probe only to Pluto a little too expensive.
Great.
So Pluto will be visited in connection with other missions.
Thank you, Jessica. Thank you, Derek, for the answer for Ted in Kansas. And we're coming to you live from WHYY in Philadelphia with pictures from space and voices from Earth. This is Neptune All Night. Welcome back to Neptune All Night, coming to you here from WHYY in Philadelphia. And we're gathered around our table here with our cups of coffee, some decaf, some regular, cups of tea. Derek Pitts from the Franklin Institute Science Museum, could you describe to us what we might experience if there was some kind of a fly-through? Say you were in a capsule of some kind approaching Neptune. What might you experience? What's your speculation?
If I didn't have wonderful insulation and long underwear, I'd be very cold to start with. Things are extraordinarily cold out at Neptune. But if we could possibly experience what it's like to travel through into the planet, what we would start to feel is the extreme cold, and maybe we can come back and discuss it a little bit more later.
We'll warm up, and then
we'll warm up and
after our JPL Voyager update as Neptune All Night continues.
Good morning, and welcome to the 2 o'clock a.m. edition of Voyager Update. I'm Steve Wall, and at 2 o'clock a.m. Pacific Daylight Time on Friday, Voyager is 323,000 kilometers, and that's 200,000 miles above the cloud tops of Neptune, speeding away from the planet now, heading toward Triton at 40,000 miles per hour. We've just received information on the occultation that indicates that the entry into occultation occurred right on time at 1:08 Pacific Daylight Time. There was a hint of some ring occultations, signal patterns representative of an ionosphere, and strong signatures of methane cloud features in both the X and S band transmissions, the two frequencies that we use to communicate with the Voyager satellite. It appears that the signal received at the Earth is strong enough to permit the desired data reduction. We have some tape that shows this imaging sequence that we're doing of Triton. Before we roll that tape, however, let me tell you that the Triton map sequence should start coming down this morning at 3:40 a.m. Pacific Daylight Time. So for the press, the list that you have is correct. So let's look at that tape now that shows the sequence that we're going to have of Triton. So you see the little squares on the planet now show you that we'll be taking images of the limb and also coming down into the planet itself. Of course, these will be put together into mosaics. And now you see us swinging around our point of view, coming around as we go to the UVS scan across the planet, and then doing a maneuver, and one wide-angle image. So we come away. With me this morning is Dr. Peter Thomas of Cornell University, an associate of the imaging team, and we want to talk with Peter for a few minutes about what we might be seeing on the surface of Triton with these intriguing pictures, so we'll be a little bit more prepared for the sequence that should come down later on. Peter, these are exciting times, right?
Yes, we've been seeing the resolution get better and better over the last 4 days. We've had large crowds in the imaging area second-guessing each other from each sequence about 6 hours apart as the resolution gets a little bit better. And of course now we're where the resolution doubles every hour, and the final crunch is on.
I guess so. And when we finally get to the best resolution images on Triton, we'll be able to see things that are a few miles across?
If everything works properly, it'll be slightly less than a kilometer. And that is some of the best imaging done by Voyager anywhere. The best imaging on a satellite by Voyager was at Miranda, which was a few hundred meters. And this will be at least on the order of that, almost as good.
All right. Well, we have some of the latest pictures of Triton here for Peter to tell us about. What do you see?
Well, in this one taken earlier today, which is a good global view of some of the spots and albedo features, which are what we've really got a hold of so far, and not much in the way of topography. The long-term questions about this satellite have always been in terms of what role the atmosphere is going to do. Can we see it? Well, we now know that we can see the surface. Well, what is the atmosphere and the chemistry involved in methane and nitrogen doing to the surface? And we certainly see that there are local variations in whatever that has gone on with the geology or with the atmospheric influences. We have somewhat toward the north, we've been watching for several days, the darker albedo features rotate around some of the smaller dots, which are now getting larger but not well resolved in terms of geologically what the features may be, whether they're simply thin surface deposits of darker material or whether they are in fact real topography or things indicating underlying geology.
Now, let's just to orient us here. The South Pole is right down here.
Is approximately there near that dark spot.
And the equator is along here, right?
Approximately up in that region, yes.
And the farthest north we can see around the edge here is what, 10 or 20 degrees?
On this, it's probably nearly 30 degrees, I think.
30 degrees. Okay, so what we're seeing here, this border between the light and dark areas is not the terminator between day and night, but this is actually a difference in the color or the brightness of the surface.
In the brightness of the surface. And actually when you go through and look in detail at the brightness, say, in the real dark parts there, or the darker parts in some of these, and some of the brighter areas, some of which outline between the major bright and dark areas, there's nearly a factor of 2 in reflectance difference. And some of the colors of the brighter areas are quite consistent with what might be described as frost deposits, suggesting that in fact the atmosphere does have an effect on some of the things we see, but does not cover up the entire planet with snow or other things that we can in fact see a lot of geology and the high resolution stuff to be seen later.
But what I think I heard you say was these markings here are interpreted as differences in the color or the brightness of the surface rather than high points or low points.
Yeah,
is that right?
Yeah, clearly. And also this image is not processed that well to show topography. The solar phase angle, that is the difference between the orientation, the angle of the solar incident light and the viewing from the spacecraft, is only about 28 degrees in this image, so you're not going to see much in the way of topography. But even so, along the edge, there's been, it's a very smooth planet, at least on multi-kilometer scales. When we get down to 100-meter scales, it's likely to be, or it could be, very much different. But clearly what we're seeing here is differences in albedo, reflectance, and color. And so far, the color indicates that there is a role for precipitating frost on the surface and possibly seasonally moving it around.
Okay, now when you say frost, you're talking about methane frost, right?
That's one of the chief constituents likely from the previous spectroscopy to be involved.
Okay, and how can we go, let's see, talking about brightness here, maybe if we look at the color image, we can point out some of what the possibilities are here. Okay, what I see here is we see obviously light and dark, but we also see differences between sort of a pinkish orange and almost to a blue here. Are those real, and what do those mean?
Well, the actual rendition here is probably not totally accurate, but in terms of this area, which appears bluish, it is unusual among the objects imaged so far by Voyager and seen on icy satellites in the solar system that actually a spectrum that rises in the blue part is highly unusual, but it can be indicative of very fine frost or ice particles, which can be generated in any number of ways, but since there is an indication of at least something of the methane atmosphere here to be determined more precisely later by both ultraviolet and radio, there certainly is a capacity for precipitating some frost, and that is a strong indication that some of that has been going on.
Okay, precipitating, you mean direct formation of frost? You're not talking about snow?
I could not really comment as to whether it's necessarily snow or frost. That's a common difficulty, even in some cases on, say, Martian polar caps, as to whether you're really just precipitating it out right on the ground or raining it out as snow. But clearly the albedo and color of the surface are consistent with some of the things were expected before we got there with Voyager in terms of likely effects of the thin atmosphere. And the range of colors here and albedos really is rather striking. As we got in closer, the sort of lack of changes in color and brightness with rotation have been somewhat resolved in that they are sort of crudely, not exactly, but crudely latitudinally banded. So as it rotates and you see the whole thing, you're not going to see much of a change. But as we got the high resolution, we've really seen that the thing really is mottled. There are all sorts of wonderful differences here in albedo, which will probably show up as geological differences when we get in with a kilometer resolution in just a few hours.
Do you want to guess about what kind of geologic features you're going to see?
Well, just on what we've seen in this image and some of the recent ones, we can be reasonably sure that there are not rather large mountains. There may be lots of topography sort of below the kilometer scale with a great deal of variety. This mottling certainly suggests that at a variety of scales on the surface you have done by either internal or external processes, cratering or something going on internally, modified the surface, which can make topography. Now, the amount of topography may depend a great deal and may tell us a great deal about what ices are involved in the topography. If it were water ice, it could support a lot of topography, since that would be very strong, practically like steel at these temperatures, whereas methane and nitrogen mixtures probably can't support many kilometers, but certainly might make hundreds of meters of relief, which in the highest resolution imaging up in one of these darker areas with the low sun, we should be able to see almost any relief that could possibly be there.
All right.
And some of these other pictures, which I think you have hinted some of the things to come. As we get this higher resolution, the things that are really starting to pop up are linear, hints of linear features running in a variety of directions. And these things which appeared at lower resolution as sort of colored mottles are now sort of breaking up and indicating that there's even smaller and smaller scales of mottling and features to be seen on the surface. This picture doesn't show it too well, but this bright area here really probably overlies sort of different geological provinces and really may be lots of frost covering. It may only be microns thick, which can change the albedo or the brightness, but have absolutely nothing to do with the underlying topography. And we're seeing sort of things which are also sort of bent and intersecting linear patterns here, which are always very strongly indicative of internal tectonic activity.
So when you see linear features on the Earth, they're indications of things going on the inside, right?
By and large, yes.
And you think the same thing may be true here, that you're seeing some expression of something going on deep within the planet?
For these, it seems like a good bet. I mean, most of the icy satellites, or almost any other planet that we've looked at, the explanations for such things usually involve the internal activity, usually which is subjecting the crust to some sort of stresses that cover a good part of the globe and hence fracture it or cause faults or other patterns such as these. I'm not claiming this is necessarily a fault, but the patterns here are starting to outline particular areas that are highly suggestive of internal activity rather than the sort of random covering by impacts or the more general albedo coverings, say, of frost, which give you a general pattern. These rather specific intersecting things are suggestive of the things we see later, in 3 hours are going to have lots of an internal component.
Well, I know that on some of the Jovian satellites, we saw a lot of not only long linear things, but series of parallel ridges and grooves and those sorts of things. Do you think that there's any comparison to any of the Jovian or Saturnian satellites?
Well, it probably will wind up being quite different. Some of these things processed a little bit better suggest that it really is quite different from those. Although you see some linear features and think of a satellite such as Europa, they really don't have quite the same crisscrossing pattern here or the same sets of parallel members that, say, are on Ganymede. So it really does look like it's going to wind up being different from those satellites.
I know one of the things that we've talked about or we've heard talked about at the press conferences has been we want to know whether Triton has a unique history, whether it's captured. Anything you see here give you any hints as to what kind of past the satellite has?
Well, in terms of the past, the first thing you look for is impact craters, just to see how old it is. And the wiping out of impact craters can mean many things, and one of them might be tidal heating-driven tectonics or resurfacing of it, which would probably have had to, depending on when it was probably captured, might mark whether, in fact, that capture is subsequent geologic events have had a chance to imprint the surface, or whether any initial sort of melting or heating with capture has been the only thing really to go on in its history. And since we see some markings on here, it may indicate that quite a lot has gone on geologically after its capture.
But this heat that you're talking about, the heat that causes the melting, is we're not talking about heat coming from the sun now. We're talking about heat that actually existed within this body for a long time, the heat that's trying to get out. And these surface expressions are the planet trying to get rid of its internal energy, right?
In essence, yes, because in trying to get rid of the energy, one of the ways that it does that, which is interesting from the standpoint of seeing it from the surface, is the convection on the inside, either as solids or liquids convecting, and that applies stresses to the surface, which then breaks it and gives you all this record of things which you can look at. And these images that we're getting now suggest there's a lot of that. But we should also remember that it's likely to be imprinted by some other things, since we are dealing with ices, certain sublimation, either frost or even there are surface features of things, say, on the Earth, which involve the sublimation, that is the vaporization of the ices, which can make landforms themselves. And some of the better processing of these images suggest that we may in fact have some of those features on the satellite too.
Prior to Voyager's arrival at Triton, there was a lot of discussion about oceans. Because of the brightness, is that now out of the question?
The surface temperatures almost certainly are too low to support any surface liquids. You would have to go below the surface and either get quite deep and rely upon the thermal gradient from inside, or have other special effects.
Okay, I see. So what we're likely to see when we get the highest resolution pictures is a completely solid surface, probably mostly ices.
Yeah, mostly ices.
And you're guessing no more than a few kilometers of relief?
Probably very much less. In these latest images, really, the topography, which you can barely see, which you really can't see in this particular rendition, but when you put up on the screen right, indicates that the smooth terminator here, in fact, really does reflect rather smooth topography, but probably at least tens of meters to hundreds of meters of local relief.
Okay. What kinds of words are people kicking around about craters now?
The words are there any or are there not? There are a couple of candidate craters that were being discussed, but it's not really clear that we've got real craters or whether it's topography in the ice caused by other processes. So we're not really sure.
Well, we look forward to a whole lot more information in the next few hours. Then I suppose between now and 3 o'clock, it's going to be analyze the pictures that we have and look forward to what we get 3:30ish.
Yeah, we get a factor of about 3, I think, in the next set of images and the resolution, and then it goes even more. So.
So in the next pictures, we'll no longer see Triton as a disk. We'll be seeing individual pieces now of a planet that's too big for us to capture the entire disk, right?
Right, and we'll get to see things down to a few hundred meters, and that encompasses all the relief for very tiny parts of these very intriguing sort of wispy-looking markings.
Well, thanks very much, Peter, for giving us some insight into what's going on in the science area. We'll try to give you some more information about the occultation when we come back at 3 o'clock. Until then, for Voyager Update, I'm Steve Wall.
Live from WHYY in Philadelphia, and images coming from the Jet Propulsion Laboratory. And in fact, in about 20 minutes or so, there'll be signals again received by GPL from the Voyager 2. And we have tonight our panel of experts. Just like to go around the table here and introduce everybody who's keeping us all company at this hour of the morning. Jessica von Puttkamer from NASA, the Strategic Planner, Office of Space Flight, to my left, and then around Judy Moffett, science fiction writer. Jack Horkheimer, the star hustler and director of the Miami Space Transit Planetarium. And then 3 participants here tonight from the Franklin Institute Science Museum in Philadelphia, Derek Pitts, Mike Wellbacher, and Joyce Town. You know, the amazing thing about the Voyager is how long it has endured. And Joyce Town, what has gone wrong with the Voyager that's somehow been managed to be compensated for in its design?
Well, there have been problems in the past. As we mentioned, the Voyager was launched some 12 years ago. And just tonight we've gotten through a critical point in this mission, which is getting through the equatorial plane of Neptune and getting past the occultation that you may have been hearing about. But in the past, Voyager has had a number of problems, and some of the people who work with it have had to have been pretty creative to get around them. What we find is that there's a lot of redundancy in the components on the Voyager craft. There are 6 computers on board. They're reprogrammable. 3 of them are backups. And quite a bit of reprogramming was done with these computers to get the Voyager to better process information and more precisely send it back to Earth. Also, back in 1978, there was some malfunctioning of the radio receiver, and they had to go to a backup receiver in that system, and we're still using that backup receiver now. In 1981, Voyager had a little bit of a problem again with another instrument, and that was the scan platform where the cameras are located. The platform became jammed when it wasn't receiving enough lubrication. But after a while and some nudging about, it seemed to work all right again, and now that's working fine as long as it's only operated at lower speeds.
Are there any difficulties aboard the Voyager 2 that we know of at this moment? Otherwise, it seems to be working
Not that I know of.
very smoothly.
Mm-hmm.
No serious problems.
No serious
Overall
problems.
conditions, good.
Good. Just before the break, Derek Pitts was slipping into his long underwear to describe an exploration through the gaseous clouds of Neptune. Could you continue on with the voyage?
I think that actually was a result of the air conditioning here in the studio. Things were getting pretty chilly. I was mentioning that it would be interesting for us to take a little cruise through Neptune so we could see what it's like taking sort of a cross-sectional cruise through. As we come through the upper cloud tops of Neptune, first we come through an upper layer of clouds of frozen gases, and as we pass through that, we come into an open area that's sort of devoid of material, and then we pass down further into the next layer of material underneath that. The upper layer of gases does cast shadows down on the lower layer, so there's sort of like an intermediate area between these two layers of material. So it's sort of a free-flying area, if you will, for us to travel around in our spacecraft. And then we start to head on toward down the center of this mass of frozen material. It's estimated that Neptune is about 30,000 miles in diameter, which is a pretty good size. The Earth is only 8,000 miles in diameter, so we're talking about something that's about 4 times the size of the Earth, roughly. And as we start to move in toward the center, not only do the temperatures increase on our way, temperatures start to decrease on our way through. Well, actually, we get a number of things happening on our way through. We have some temperature change, but mostly we have material change where the gases start to get much more slurry-like, very much like a water ice, slushy situation of the methane and ammonia gases that are in the atmosphere. As we travel through, we probably don't come across a solid sphere as we have here in the Earth, but things again are getting much denser and still very cold, and still cold, dense water ice, sort of a central portion. And as we can manage to slog our way through, pushing through with our snow shovels and things like that, we start to come out the other side of the planet, and of course the density starts to drop off as we move higher and higher into the atmosphere out the other side.
Derek Pitts and his very quick tour to the center of Neptune.
Very quick.
The center of the planet Neptune.
The underwear isn't thick enough to get us spend much time.
Are there any seasons on Neptune, like
are there
winter and
seasons
summer?
on Neptune?
I think there are seasons, but they're the changeovers are very, very brief, and the changes in temperature are not very great.
The Neptune axis is inclined very much.
Yes, it is. It's tilted 89 degrees away from the vertical, so it's almost as if one of the poles is pointed.
No, I think that was Uranus.
Oh, okay.
Sorry. No, I think it's about more like 29 degrees.
More like 29 degrees, okay.
The Earth is 23.5.
Right, so that's much closer to the Earth.
So it's got to have seasons.
Mm-hmm. Right, but the temperature changes are not as great as what we have.
Right. We'll have to leave it there. Thank you, Derek and Jesco. If you're seeing up on the screen recorded earlier, that's referring to the pictures of the planet Neptune. We are, in fact, live here as this panel is continuing here on Neptune All Night. We understand there are large parties watching large screen televisions in different places in the country as we're continuing here with pictures from space and voices from Earth. This is Neptune All Night. You're watching Neptune All Night from WHYY in Philadelphia and images of Neptune via the Jet Propulsion Laboratory in Pasadena. And we'll have an interview with a British scientist, Patrick Moore, also in this hour. We'll also hear some more from our guests and some more from the 800 call, 1-800-FLYOVER. You might be interested to know that a season on Neptune lasts more than 40 years. Here is Jim in New York City.
Yes, just a quick question. As a prospective elementary teacher, How do you feel what Voyager has found will change the course of teaching down the road?
We have Joyce Town here, the Franklin Institute Science Museum, ready to answer that.
Well, I think it will make it a lot easier for us to teach thoroughly the solar system to students. By studying these outer planets, we learn a lot about the formation of the solar system and the evolution of the solar system, and we can speculate also on the future of planets and possibly the future of mankind, and Mike has something to add.
Yeah, I think something else that happens with what's going on tonight is that through technology we can participate in the scientific process by actually watching live transmissions from places like Neptune. So even though it's 3 billion miles away, we're all sitting up and watching images come to us from the planet itself. So there are now museums around the country who are getting images like this that they can show live to audiences, and before you know it, kids in classrooms will be watching these kinds of images live in the, right there through linking computers, linking satellite dishes, linking up TV sets. We can all participate in science.
Quick question, Jessica, are we watching a live picture at this moment?
No, that's an earlier picture and taken from last night. It's one of the new moons. Right now we don't have a picture yet from Voyager 2, so they are replacing this with stored, with recorded pictures.
Stored images. We have another call. No call here. We're listening to the comments of our guests here, members of NASA, science fiction writers, and people from the Franklin Institute of Science Museum here in Philadelphia. At the Jet Propulsion Laboratory is Ira Flato, and he has a guest, Richard Berry. Ira?
Hi, thank you very much. Yes, I have Richard Berry, who is editor of Astronomy Magazine. Thank you, Richard, for joining us. We were just discussing how this is sort of an unfortunate anniversary for Voyager. It was, what, 1986, was the last time everybody got together and watched the Voyager?
In January it was.
January, when it visited Uranus? And
Right, it was 2 days after the encounter, 2 days after this, and the press were just beginning to settle back and put their feet up a little bit, and they'd gotten the stories off, and
it was the Challenger explosion.
Yeah, there was a whole bunch of people sitting around in the newsroom, and we watched the high quality pictures come of the liftoff come over the link, and up it went, and it was just beautiful. I mean, there it
we
was,
all remember what happened.
And 72 seconds into the flight, there was a little flash up to the telephoto lens, and then suddenly, boom.
And that was the last time that we had all been in...
and nobody could believe it.
Yeah.
I mean, for about 10 seconds, we all just sat there. And this is like 50 people sitting in this room watching. Bump, bump, bump. And then we kind of, oh my.
That was it.
And people just kind of dove across tables and grabbed at telephones, and they just went crazy.
And everybody just left it.
And well, there wasn't anything we could do.
Yeah.
Quite a few people had been covering Voyager, because that was the important story, and were on planes an hour or two later on their way down to Florida. And a lot of these people, a lot of the science press, had met or knew astronauts on these things. So, in some cases they lost friends.
Now this time, we both noticed that there's a tremendous amount of press interest, but that the press interest this time has been snowballing. It's as if that people discovered a couple of weeks, 3 or 4 weeks ago, that something interesting was going to be happening in the vicinity of Neptune on Thursday night and Friday morning.
Well, they've got to notice that this is the 4th great flyby, and each one has been better than the one before it. And, the other media have got to notice Time's best cover was the Saturn flyby, and the pictures are phenomenal. And art directors got all turned on by these pictures.
Did it do much for Astronomy Magazine and for other magazines, these sort of photos?
Oh yeah,
circulation.
Yeah, because I'm not sure whether they pump circulation, but they sure created a ton of interest. We provide many pages of coverage. We're going to be running 30 pages of coverage. We'll run every good picture that comes out of this mission.
Every good picture? That could be thousands.
We're not going to... Well, I mean, every good picture that gets released.
What's your lead time? Do you have to have 6 months?
We're working on a November issue right now, and that's real tight. We'll be splitting coverage between a November story and a December story.
How do you cover something like this? As a journalist, there is so much happening, and there's so much going on behind the scenes. How do you decide how you're going to cover it?
It's difficult. For our November story, really the science results won't be out. I have to have the story in Monday morning. So what we're going to talk about is what was seen. Just what was seen. We'll describe it. Very simple terms. And December we'll start to get into what they found, what they think caused these things, how these magnificent worlds were created, to the extent that's known a month from now. And really, things like this take 5-10 years before they're understood.
Do you think because your magazine comes out later, and magazines in general come out later, that you get some more information because you can hang around a little bit longer and schmooze with the scientists and find out little tidbits that daily newspapers and TV can't get?
That's right. Also, with TV, the picture's on the screen and it's gone again, and you can't look at it. And what we give you is something you can look at and study and...
Do you ever discover something they haven't seen when you look at it? Your editors or you or any of your reporters look at a picture, say, hey, there's something there that they might have missed?
We see things that they haven't commented on. I'm not sure whether they missed it or not. During some of the flybys, I've sent little messages saying, did you guys notice such and such in frame such and such? Especially at Jupiter, when pictures came down every 48 seconds.
Yeah, they were just rapid fire.
They were just so fast that the scientists
they had a rapid transmission rate, and it was
That's right. It was just incredible then. Every 48 seconds, a picture would come in, and you'd get a 50 frames, boom, 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 one right after another.
And so you could see, they didn't have time to look at the whole thing, or all of them when they came through, and you could watch them yourself.
That's right.
And you could pick out things that they missed.
Yeah, or you could see things that, you didn't, maybe they saw it, maybe they didn't, but I would send little messages along, hey, did you see that? There's this really weird-looking thing. One of the things that on Ganymede was this very irregular, weird basin, impact basin that didn't look like any of the other stuff. That turned out to be Gilgamesh. Apparently one of the younger basins on the planet. It just looked different.
Very interesting. Well, we'll see what you can come up with in the next few months, and thank you very much, Richard Berry, editor of Astronomy Magazine, for stopping by.
Well, thanks, Sarah.
Back to you in Philadelphia.
Good morning, Discovery! Good morning, Discovery. Rise and shine, boys. Time to start doing that shuttle shuffle. You know what I mean? Hey, here's a little song coming from the billions of us to the 5 of you. Rick, start 'em off, baby. The Hulkster to you. On orbit is the place to be. Free-wheeling on Discovery. Earth rolling by so far below. Just give her the gas and look at this baby go.
H-A-R.
Are you awake yet?
D-E-Y.
Why? Because it's time to eat breakfast from a toothpaste tube.
M-U-double-D.
Neptune All Night continues now with an interview with British astronomer. Here again is Ira Plato.
Patrick Moore, a gentleman guest from across the ocean, who has been described to us as the British version of Carl Sagan. Would you say that's not true?
I think an insult to Carl Sagan, I think. Carl is a very distinguished and a very skillful astronomer, and I rank myself merely as an amateur. I'm simply an old-fashioned moon mapper.
Now, tell us about that. You have an impressive list of credentials, of accomplishments. Tell us about some of the things you've been doing. Moon mapper. What do you mean, a moon mapper?
Well, as you know, before the space age began, the moon particularly was very much the province of amateur astronomers. Professional astronomers weren't very interested in the moon in those days, not on the surface anyway. And people like myself were mapping it and drawing it and photographing it and producing maps that I think were found useful later on.
What year? What years are we talking about?
I'm talking, in my case, anything from the 1930s right the way through to the late 1950s and mid-1960s.
Did you almost beat Clyde Tombaugh out in discovering Pluto?
Clyde Tombaugh discovered Pluto in 1930, and I first remember hearing of that discovery when I was a boy of 7 at my prep school. Little did I think that 50 years later, Clyde Tombaugh, who discovered Pluto, would do me the great honor of inviting me to join him in writing the book about Pluto, which we did in 1980. And in 1980, we had the Pluto Conference at Las Cruces, New Mexico, 50 years after the discovery. And Clyde was there, and I'm hoping that Clyde Tombaugh will be here very shortly.
We hope he'd be here, too. Now, you also wrote a book about Neptune, is that correct?
I did indeed. That took a long time, the reason being that no one had ever pulled together all the information about Neptune. So what I decided to do, and this was going back several years now, was to go through all the published material and correlate and index all the papers and put a commentary to them. Also, there was the fascinating story of the discovery of Neptune, which in a way was a chapter of accidents. There were 2 people concerned, one English, one French, and I went to the descendants of the discoverers and unearthed a good deal of unpublished material, some, not all of which I could publish.
And why is it now, many of the great science programs in the United States and on public television come from the British. Why do the British have such a wonderful interest in science?
We've been at it for a very long time, don't forget. And I think we have the knack of starting things. We don't always follow them through the way that we should, and I admit that quite openly. But let's say, really, I think we've been doing it for a long, long time.
And you continue to do it very, very well. In fact, you're involved in a TV show that you're covering the mission for, right?
Well, I've been doing a program called The Sky at Night on BBC television, and I began doing this in 1957. And the BBC thought it might be rather a good idea to do a monthly program about astronomy, which hadn't been done before. So they said, we'll create a program called The Sky at Night and put it on the air once every 4 weeks for 3 months and see how it goes. That was 32 years ago, and we're still going. So
we're still testing it out, then. So you basically show people what to look for, amateur astronomers, what to look for that month?
No, it goes further than that. Some of the programs we do that way, and others we have guest experts. And many of the guest experts we've had, you will certainly know. For example, Harlow Shapley, the man who first measured the size of our star system or galaxy, was there on The Sky at Night with me, explaining how he did it. Bart Bok, another very great astronomer who's over here. In fact, I think really most of the world's great astronomers have been on the program with me. And some of the rocket men too. Werner von Braun has been on with me, for example.
You have been an observer of the space race, so to speak, for many, many years. You haven't drawn any conclusions about international competition and international cooperation?
I hate the term international competition because, in my view, if we're ever going to get very far into space, if we're ever going to send men to Mars and establish colonies on the moon, then it's got to be done, not nationally, but internationally. And unless we can learn to live together and do that, then we won't get very far, and frankly, we won't deserve to. And I'm glad to say there are encouraging signs of this now. And really, I think it begins down in Antarctica, where there are various national stations, and they collaborate to quite a large extent. And I'm very much hoping this will spread. And when we do get bases upon the moon, they've got to be international ones. Mind you, they may first be national. They may be American, they may be Russian, they may be Icelandic for all I know. But they're going to be manned by scientists. And scientists do like to collaborate. And on the moon, the politicians won't be able to stop them because they won't be able to get there.
Well, I've been to Antarctica, so I have seen the collaboration that goes on in Antarctica, and it's very, very nice. It's the only place in the Earth where you can have anybody just walk in at any time and see anything that they want to see.
But I will say one thing, that the International Astronomical Union, to which I have the honor to belong to myself, really is about the only organization I know that is genuinely international. And there are, from every race, color, creed, everything else, they're all there, and there are no bars at all.
If I'm not mistaken, the first British astronaut will be going on an international flight. Is that not correct?
Probably, I think, now. It looks very much as if it's going to be on a Soviet one.
In a Soviet one.
Seemed like
to me, that was a shock to hear that a British astronaut would be going on a Soviet mission instead of an American mission. How is that played in England?
Well, of course, I think we're all here terribly sad about the Challenger tragedy. I mean, quite apart from the human tragedy, and goodness knows, that was very much the worst aspect of it. Please don't get me wrong. The human tragedy was by far the worst aspect. But quite apart from that, it did hold things up dreadfully. No question about that. Otherwise, I think that things would have evolved differently.
I'm sorry. I was just going to say that I have found the American government very reluctant to participate in joint Soviet missions. I remember interviewing one of the astronauts before the first shuttle launch following the disaster. his name escapes me, who commander was, and he was very fluent in Russian. He had spent many years, you know who I'm talking about. He spent a long time in the Soviet Union, and I asked him at a news conference, considering glasnost, don't you think this is a good time to possibly talk about a joint mission with the Soviets? How about Mars, something like that? And I expected him to say yes, but he said absolutely not. I think it's a very bad idea. I was shocked.
Well, as an amateur astronomer, I think it would be a very good idea indeed, and the more international collaboration we have in all branches of science, the better. We've got to have it eventually, you know. And I just wonder, looking round our galaxy, there must be many worlds like the Earth, with inhabited, with intelligent beings upon them. And I just wonder whether other civilizations also have got to our stage of having the scientific know-how of how to destroy themselves and not having the civilization not to do it. And we are in that stage now. I firmly believe if we get through the next couple of 100 years without having any more major wars, then probably we will have learnt enough not to do it. But I think we're going through a crisis period now. And of course, the Moon and Mars are of equal interest to us all. I say there are no iron curtains or bamboo curtains in space.
Well, from a practical standpoint, it's so expensive for any one nation to create a mission to any of the other planets now. It seem to be more economical to do joint missions.
Expensive, perfectly true, until you compare it with national budgets. I mean, I wonder what the space bill compared with the armaments bill is, for example. Or over here, even...
we could certainly go into that.
Even the chewing gum bill. You see, it may sound a great deal when you equate it in terms of actual cash.
Right.
But when you equate it with national expenditure and national budget, and money that's spent on other things, it doesn't come to very much. And think also of the benefits. And there are so many people who say even today, what's the use of space research? And they totally forget that every branch of knowledge is now linked to every other branch of knowledge. And in learning more about Neptune, we're learning more about ourselves, about the Earth, about biology, about physics, mathematics, medicine. It's all there.
Well, thank you very much. I couldn't find a better way to end this interview. I want to thank Patrick Moore for taking time and being our guest. Thank you very much.
Nice to be here.
And the interview, I think, raises some interesting points. Judy Moffat, our science fiction writer, just before we get to some calls, what is the impulse behind the search for extraterrestrial intelligence, the SETI program on a more formal basis?
I think there's something about aliens that fascinates everybody, maybe for a variety of reasons. Partly that the exotic is fascinating always, and partly that traditionally aliens in science fiction have been a focus for xenophobic feelings, hostilities that could be externalized, so that in War of the Worlds you can imagine that the creatures from Mars are coming to attack us and do away with us. And they're represented as aliens so different from us that we don't have to have any compunction at all about destroying or attacking them. But chiefly, I think, there's tremendous mythic power behind the idea of friendship, connection between beings that are vastly different from us, but also, in some sense, like us. And it's a great, it's probably sentimental, it's certainly romantic, but a great impulse, a wish to communicate with them if they're out there. The first contact is one of the great science fiction themes of all time.
What preparation do Earthlings need for this first contact? I mean, there are receiving dishes set up to hear some signal from another set of beings. You know, are we prepared?
Well, the preparation we mostly need is philosophical, and I don't know that we are. In a material way, what we have is the Very Large Array in the desert of New Mexico, which is listening all the time for signals from outer space in case somebody is out there trying to communicate with us. There is a man called Hans Freudenthal who invented a language. The language is called Linkos, and it's an entire language which is expressed in binary numbers, which is theoretically supposed to be capable of communicating with any intelligent beings who have developed higher mathematics so that they could understand the signal. And that's, we are not sending it, but the language exists and is ready in case money is raised and machinery is built.
Well, I know that anyone who has seen the film The Day the Earth Stood Still and what happened to Gort and to Michael Rennie's character know that in many ways Earth may not be ready to welcome even benign visitors. unless, yeah, but Michael?
One of the interesting things about science fiction, both literature and film, is aliens tend to look very much humanoid. And I think what happens if we ever discover alien life or it discovers us, it's not going to be humanoid at all. And that's certainly going to challenge a lot of our concepts like God, for example. If we are created in God's image and these are aliens and are intelligent and look nothing like us, then what then does God look like? So you get into good stuff with that.
A quick comment before we go to the phone, Jack?
Well, I just have always thought it rather unique that most of the literature in science fiction treats most aliens in fantasy as being benign or friendly. And if you look at our planet and you see the species, you see the rule of life on this planet from the lowest to the highest. It's one species eats another species. I mean, intelligent life supposedly is what separates us from the other animals, and we supposedly are friendly. History doesn't indicate that at all. And if we look at all species, it's dog eat dog, amoeba eat well, not eat amoebas, don't eat amoebas, but it's basically everyone happens to be part of somebody else's food chain.
Right.
And perhaps we are.
But I would bet the
part of somebody's
biochemistry
food
of
chain.
aliens is such that we couldn't sustain an alien.
Let's go to Wayne in Florida.
Hello?
Hello, Wayne.
Yeah. Hello?
Yes, you're with Neptune All Night.
Okay. Comment on the caller earlier about sinking the satellites. One moon of Saturn, a 4-out one named Hyperion, is just tumbling. It doesn't appear to be having any one side constantly facing Saturn the way, as far as I know, all the other moons do. Also, my wife Mary has a follow-up on what's happening as Voyager goes out beyond Neptune.
Hello, Mary.
Hello?
Hello, Mary.
I don't really have a follow-up. I had a couple of questions, quick ones. One thing that I wanted to know, as Voyager exits the solar system, will it be sending back enough information to determine if there is indeed a Planet X? And also, I wanted to know if there was any correlation between the dark areas that have been found both on Triton and Iapetus. And Wayne had a question about Kraft and Cassini, whether or not they had been funded. Thank you. I'll hang up.
Thank you, Mary. A lot of questions there from.
Well, Kraft and Cassini are right now in the stage of being discussed for funding. I think the last word hasn't been said yet, but they both stand a very good chance of getting approved. As far as Planet X is concerned, the hypothetical 10th planet, I think we should preamble that by saying that the data which originally indicated that there may be a Planet X date back to before 1910. And all the astronomical measurements after 1910 do not show those planetary disturbances which could hint at the existence of a Planet X. So right now, today, most scientists are not really believing that there is such a thing as a Planet X because they don't see any disturbance effects in the outer planets. However, both the Pioneer probes and the Voyagers, of course, are being watched. They are being observed for those effects. If there is such a thing as a Planet X, it's got to be so far out or in such a highly elliptical orbit that it doesn't disturb the outer planets. And that's the only possibility of its existence, which means that Pioneer and Voyager still has to travel quite a distance in order to notice any effect.
Mike?
Planet X has, it should be pointed out, has been indicted in the conspiracy to kill dinosaurs 65 million years ago.
How so?
Oh, something about shaking up belts of comets and sending comets loose into the solar system and causing massive impacts in cycles of 26 million years.
Yeah, but its period around the sun is in the order of 1,000 years, if it does exist.
So paleontologists have an interest in finding Planet X.
And we'll be back with our panel in the next hour as we continue with Neptune All Night here live from WHYY in Philadelphia and with images from the Jet Propulsion Laboratory in Pasadena. Jesco, Judy, Jack, Derek, Mike, Joyce, and myself, Sedge, will be back as we go in just a moment to the Jet Propulsion Laboratory in Pasadena for their 3 o'clock Pacific Daylight Time update, 6 o'clock here on the East Coast as the sun is coming up here on the East Coast. So with pictures from space and voices from Earth, a reminder that this is Neptune all night.